Hello. Hello, good morning, everyone. I, Aishwarya, welcome you all to the one-day international workshop on high-dimensional data and AI algorithms with applications, organized by the School of Mathematical and Computing Sciences, SPPU. I request Professor Vinayak Joshi, Head of Department of Mathematics, to felicitate today's chief guest, Professor Katre. I request Dr. Jyoti Yadav from Department of Computer Sciences, SPPU, to introduce Professor Katre.
Good morning, one and all. On behalf of School of Mathematical and Computing Sciences, Savitribai Phule Pune University, I take pleasure in introducing Professor S.A. Katre to you. Professor S.A. Katre completed his bachelor's and master's program from University of Pune in the year 1975 and 77 respectively. Further, he was awarded MPhil degree in the year 1981 and PhD in the year 1985 from Punjab University. He specialized in number theory, and his other topics of interest include algebra and combinatorics. He has worked with SP College Pune from 1977 to 1988. He joined Department of Mathematics, Savitribai Phule Pune University in the year 1988 as a reader, and later became a professor from 1998 till 2017. To add a feather to his cap, he headed the Department of Mathematics from 2012 to 2015. Currently, he is working actively as a chair professor, Lokmanya Tilak Chair, SPPU Pune. As a part of academic responsibilities, he is the member of governing body and custodian of Bhaskaracharya Pratishthan Pune, treasurer of the Mathematics Consortium, and president, Indian Academy for Industrial and Applicable Mathematics. Related to his academic activities, he has organized many annual foundation schools of NBHM and National Center for Mathematics. He has guided 11 MPhil students and 15 PhD students. He has participated in international conferences in mathematics in Germany, China, France, and USA. He was a regional coordinator for Indian National Mathematical Olympiad for Maharashtra and Goa region from the year 1992 to 95. He has worked as a deputy leader and observer for Indian Mathematics Olympiad team, participating in international mathematics Olympiads at India in 1996, Argentina in 1997, and Germany in 1998. So with this brief introduction, let's welcome Professor S.A. Katre with a huge round of applause. Thank you.
Thank you, Jyoti ma'am. I now request Professor T.V. Ramanathan, Director of School of Mathematical and Computing Sciences, SPPU, Head of Department of Statistics, SPPU.
Good morning, everyone. Welcome to this school. So, respected Professor Katre, Lokmanya Tilak Chair, former head of the Department of Mathematics, and faculty members from all the 4 departments and participants. You know, the School of Mathematical Sciences, the school system started about 1.5 to 2 years back, and it is still in the sort of in the very initial stage. So not much activities have been done. Perhaps this is the first activity of School of Mathematical Sciences and Computing. This school consists of 4 departments: mathematics, statistics, computer science, and the Center for Modeling and Scientific Computing and Modeling and Simulation. That's 1 department now. Earlier that was 2 departments. So these 4 departments constitute this school. And the main idea of the university is to basically to have mobility, kind of, courses are available to students so that they can take courses from all the 4 departments very easily without much of difficulty. Difficulty, what I mean is in terms of timetable and other things. And then another intention of this is like the sharing of resources. So we, for example, some of our students, especially PhD students, used to avails the facilities, supercomputing facility that modeling and simulation is having. So like that, of course, it's still in the very initial stage. So the purpose, maybe in coming days, this interaction will increase, and then you will have a very strong school of mathematical sciences and computing. And this school is now, very I mean, like one of the important things these days, because nowadays data is like everything. So data is food, data is water, data is everything, and everything talks about data. I think slowly I'm in the, and then, all others give supports to that, like statistics give support, mathematics gives support, computer science gives support. So now I think the relevance of this particular school is really at a high stage. So I'm sure that in the coming days, the school will come up with a lot of programs and interactions with students, etc. Uh, Now, in good old days, like, when you have the data, mostly everything is sort of fixed. I have my features fixed because I have resources fixed. Even collecting that data, transferring them, everything was sort of limited and costly. So, and these days, it's not like that. Anything that you can think about, and that's the data. And then it's like data hungry these days. So, and then we need to, naturally, the old techniques are not sufficient to handle such situation, especially statistical techniques, and even the relevance of more mathematical techniques like optimization, functional analysis, approximation theory. All these have become, part of this whole new development. So I'm sure that today's the purpose of the background of this workshop is about 2 years back. I think exactly 2021 September 7th. The Indian Society for Probability and Statistics was conducting a conference on an online mode. Of course, still that was COVID time. And Professor Vijayan Nair was giving a talk on the similar topics. And at the end of the talk, he told, I would like to, of course, Professor Vijayan Nair has an interaction with our department because some of the faculties very, very close to him. In fact, visited Michigan also a couple of times, some of the faculties. So he mentioned that I would like to actually train students in Pune or Cochin, of course, because of his proximity to these two places. Then immediately, very next day, I wrote him a mail. We would like to organize something. This was in 2021. But due to some reason or otherwise, he could not make it. And then this is the first visit after that whole COVID incident. So he immediately agreed that, yes, I am coming to India, and this time I wanted to give a workshop. So that's actually the background of this workshop. So he has given the workshop day before yesterday in Cochin University of Science and Technology, and today it is going to be here. So he will be addressing you, I mean, the entire afternoon session. I'm sure that you will have a lot of takeaway from this workshop. We have planned it in such a way that because there are disciplinary people who may not be very comfortable with, the kind of regression techniques and the classification, methods. So we thought that in the morning section, in fact, in addition to this, about 300 students are from very different colleges of SPPU and otherwise are attending this particular workshop on an online mode. So we thought that there should be some preparatory session. So the preparatory session is basically introducing you to the model, the supervised learning concept, etc. And then in the afternoon, Professor Vijayan Nair will take you to the real algorithms and applications of ML, especially with specific application to banking and financial sector. So this is what the background. I'm sure that you will have a lot of learning. So enjoy and then learn something throughout the day. Thank you very much. Jai Maharashtra.
Thank you so much, sir. I now request Professor Katre, sir, to inaugurate today's workshop by saying a few words.
Professor Ramanathan, Professor Smita Bedekar, uh, then other teachers. Sushma Bendre Madam is also here. All teachers from the mathematics, statistics, and computer science, modeling and simulation, all these departments. So I'm very happy that I have been given the opportunity to inaugurate this uh, very important workshop, international workshop on the topic big data and machine learning algorithms. And I welcome all of you, all the students for this, who have come from various places, and they have come in large number. Many are here offline, and also many online students are there. Actually, mathematics and statistics, these two subjects provide a basic tools for these data analysis. And the other departments who are participating in this workshop, namely modeling and simulation, and also computer science, they support the application part of the big data analytics. So all these departments further use computational techniques to reduce the complexity of the algorithms which are created, which have created the models. Hence, it is in the fitness of things that the one-day international workshop is being organized today on high data, high dimensional data, and also AI ML algorithms with applications by the School of Mathematical and Computational Sciences, SPPU, which takes together all these four departments. Now, I see that there is a special session by Professor Vijay Nair on ML algorithms and applications. And these applications are mainly in banking industry that he will be talking about. So I see that there is very good response for this. And this is a first kind of workshop that I am also seeing here, which brings together all these four departments because of this creation of new Center for Mathematical Sciences. I had earlier organized some workshops jointly with other departments as under the activities of Lokmanya Tilak Chair. But now I think under this mathematical sciences, all these departments should come together, especially because data science requires all these four departments together. Now, there are so many data analytics algorithms are required because a lot of big data is created. We see even WhatsApp and emails, Google emails and other, they create a lot of data. Much of this data is for gossiping also, but as we know, a lot of data is very useful, and for even weather prediction, we require to note various kinds of data like temperature, humidity, rainfall, etc. And as you might know, earlier there used to be observations on for a grid of 20 kilometers by 20 kilometers. But nowadays, the grids are roughly 2 kilometers by 2 kilometers. That is because we have very great computational facility available, and therefore the data is also bigger, but we have very nice algorithms nowadays which can be actually used and we can analyze the data and we can do better predictions about weather. So for example, now if you go to some other city, you want to know what is the temperature there and what is the possibility of rainfall there. All that you know beforehand. And earlier we used to say that there is a prediction, weather prediction, that there will be rain today. Then we knew that there will not be actually rain. So that was the earlier understanding, but nowadays that is not the case, and we actually get a good prediction of this weather because of the advanced techniques and also advanced computational facilities. Recently, COVID predictions were also done by using regression, and people all over the world did these predictions. For example, when will COVID end? Such things. And in India also, such predictions were made, and many of them turned out to be actually correct. That is our experience. For example, my friend Professor Ullas Dixit had made the prediction that COVID first wave will end in the month of April 2021. And this prediction was not made afterwards, but it was made beforehand. It was made in June, July 2020. This prediction was made by using the observations from, say, April 2020 to June 2020. These observations were taken using Arogya Setu because, see, for any such prediction, data also is required. And Arogya Setu provided this data. And this data was utilized to give the predictions about when COVID will start decreasing and when COVID will actually end. So COVID will end means the number of new cases that is equal to number of cases cured. So that happens after that. So this is how it was done. So these are some very important applications of data science. Nowadays, various applications are there of data science, like accounts data of companies. It is used to stop production of some items which are not giving any profit. But you can increase the production provided you get a big profit in that item. So we can optimize profits. Patterns of purchases and inquiries of items in different seasons and even at different times of the day. These are very useful nowadays to create marketing strategy, and which is actually done so. There are nowadays many recommendations for you to purchase things, and combo purchases also. You purchase one thing, then immediately you get a recommendation that you also purchase this thing, you may get discount or whatever. That is because of the study of various purchases by the previous customers. So all this data is analyzed and it is used for such recommendations. Nowadays, if you go to YouTube or Netflix and so on, then you get recommendation for what to see. Depending upon your previous search, you are able to get such recommendations. Nowadays, translations of books written in, say, English language, these can be done immediately in, say, Hindi. For example, 2 days ago, suddenly, probably by some mistake, all my English Google emails, very long emails were suddenly converted into Hindi. Actually, that was some mistake, I don't know. Now, today it is not happening like that. But that was I was surprised that it is done within fraction of a second. I just type something, immediately it is converted to Hindi. So, some important letters I was writing, and then those who received my letters, they were surprised that I am writing in Hindi suddenly. But that is, the point is that it was done in a fraction of a second. And my friend told me that recently some German book he wanted to read, mathematician. And then that whole German book, earlier, we used to give some examination in German and understand some keywords, etc. And we make out the translation of that whole paper, research paper or book. But nowadays, you give that whole book and you get it translated into English immediately. Only certain technical things it is unable to actually translate. But then if it is in your subject, say mathematics, statistics, or computer science, then you can really make out those remaining things and you can actually translate. So these things are possible because of these developments in data science. Also, there is, say, speech recognition. These are some applications of data science. Many students in statistics department and mathematics department in our university have done projects. One of the projects I know is the project on boilers and pumps from the company Port Marshall. That company, so students have done a project, and that project did obtain some patterns of the data of the boilers, and then it could give some predictions, like the recent data is not matching with the previous data, then there may be some fault, and what kind of fault it is and where the fault is located. All that information you can get from the data that is analyzed, and you can obtain patterns from that. Nowadays, data science is used for customer service also, photo tagging in social media, all these things. Autonomous vehicles, as we know, AI is used there. And there are some historical examples when there was progress in AI. In 1997, for example, IBM Deep Blue chess playing system, it beats the expert Garry Kasparov. Similarly, 2011, Jeopardy experts were defeated by IBM Watson. 2015, Baidu's Minuak supercomputer uses deep neural network to identify and categorize images with high rate of accuracy than average human. Then 2016, AlphaGo program of DeepMind beats Lee Sodol, world champion Go player, in a 5-game match. It was interesting that in this, some interesting things about matrix multiplication, which we learn in the high school nowadays or college level first year, they were used. And so there, as you know, when there is such a game, then after 2-3 steps, then there are a lot of possibilities are there. And you have to analyze all these possibilities. But all that can be done by converting that problem into matrix multiplication, and how multiplication of matrices can be done in a small amount of time by some algorithms. All that is very important. So computational mathematics is also important along with usual mathematics and statistics in solving these problems of big data. Very recently, of course, you know, this ChatGPT, it has created a revolution, and ChatGPT can solve even examinations, biology examination. Very difficult kind of problem was that paper was attempted by ChatGPT, and ChatGPT gave actually, got very good credits in that, A plus credits it got. That is a very surprising. Even Bill Gates said that this is very astonishing. And recently, in healthcare also AI is being used very much. For example, Google Health and Imperial College London, the researchers from these two places, they trained a computer to spot abnormalities on X-ray images of up to 29,000 women. So if there is a new X-ray, then it is compared with all these 29,000 images, and one gets an idea of whether there is actually cancer or not. So that kind of decision is done in a very small amount of time, so that it saves doctors time. Sometimes it can be considered a second opinion, because it cannot actually replace the doctor, but certainly it is a second opinion, and therefore a lot of time of doctors will be saved. So these are very nice, important applications, and unimaginable many times that such a thing is possible. So with these few words on these current applications of data science, I now formally inaugurate this international workshop, and I wish all success to the participants in learning machine learning algorithms through practicals. Thank you very much.
Thank you, sir. We are all honored to have you here. Now, to begin the series of lectures in today's workshop, I now invite Dr. Madhuri Kulkarni from Department of Statistics, SPPU, to deliver a lecture on simple and multiple linear regression models and regression diagnostics.
I'll have to stand here, no? Huh?
Good morning, everyone. So, till the arrangements are made, I thought let us try to develop a contact with all the participants. How many are from mathematics? Can you please raise your hands? Mathematics department? Okay. How many are from computer science? Or I should ask, how many are not from statistics? Okay. So see, accordingly, I can talk. So I just wanted to know. So then I think my talk is very much familiar to you. You are, how many of you are doing masters in statistics now or have already done? See, okay. So this was the most important feedback that I could have got from the audience. So well and good. Then I'll finish my lecture in time, Bendre ma'am, so that you can start on time. So today the talk is on simple and multiple linear regression models and regression diagnostics. So I'll try to talk about something which you already don't know. So okay, I'll keep this in mind. So it's a it's a statistical technique for investigating relationship among variables. So the popular example which I usually use in the MSc class, I'm repeating here. So some of you who have already done it regression with me, please bear. Because most of you are doing masters, no? So you are familiar with the examination pattern, like internal examination, then you have final examination, and then on the grade sheet finally you get the grades. So what if you have the data on your internal scores and final scores, say for a particular course? Can you predict your score based on this kind of data? Final score, or suppose I have data of 25 students from one class. Data is on the internal scores and final score. So can I predict the final scores if I am provided internal score for the other set of 25 students from the same class? Something like this. So these are very common questions. So regression appears or can appear in so many such setups. So because I was going to address students, so I thought this could be a very good start. So how can it be done? So the simplest model or the simplest function that can relate these scores obtained in the internal examination to the scores that you obtain in the final examination is a linear approach. And so we start with the simple linear regression model. So here I have plotted the internal scores on the x-axis and on the y-axis external score. So you can, the line is the fitted line of regression. So the points are actually the scatter plot of these points. That I haven't shown all the 25 points, only 4 points I have shown here, but in all there are 25 points plotted here on this graph. So a few questions which can be answered from this by looking at this graph is there a relationship between the final score and the internal score? If that is the case, is it linear? So because the line is already there, you do get a feeling that okay, it is a kind of linear, or it can be approximated by a linear equation. So then this question I have already asked. Then now how accurately can we estimate the effect of internal examination on the score obtained in the final exam? And because most of you are doing masters, you are aware that you don't have to face only one internal examination. You go through a series of internal class tests, surprise tests, open book tests, and whatnot. So suppose all the scores are provided to you. Can you predict the final score? Have you ever tried doing this? Have you ever now, because you are already doing masters, or at least many of you have already learned this simple linear regression. Can you please tell me if you have all thought of some other scenario wherein you can apply regression? Any scenario? No? Okay, then start thinking now, because the workshop focuses on applications of statistics. So how accurately can we predict future final exam scores? Because you may want to get actual prediction, or you may want an interval, or you may rely more on an interval. Na? Okay, itne, at least itne to mili jayenge. Hai na? This is what you would like to know. So, so how does so here the response variable is student's final score. Then the variable which influences the response variable, that is the regressor, that is the internal examination score. Then this is just a review of simple linear regression setup philosophy. So this is how the simple linear regression model is presented. So epsilon represents error. Now I'll come back to this a bit later again. So what is a simple linear regression? So it is just a simplest possible approach for predicting quantitative response y on the basis of a single predictor variable x. So when there is only one predictor, then you call the model as simple linear regression model. So now a bit more about the basics of simple linear regression model. So beta naught is the intercept parameter, beta 1 is the slope of the line. So they are referred to usually as model coefficients or parameters of the model. So once we have used our data to produce the estimates, so least square estimation is used for estimating the model parameters based on the given data. So beta naught hat, the least square estimates are denoted by beta naught hat and beta 1 hat. So once you have got the estimates of beta naught and beta 1, you plug them in the formula and you get the prediction for a given value of x. So that is how it works. See, this entire talk was designed keeping in mind non-statistic students. So it's too basic, but there. So the random error now has a few properties. So like the mean is beta naught plus beta 1 x. So see, the idea is that I am trying to model expected value. So I am giving a functional form for expected value of the response variable given that set of values of that particular value of regressor. So now I am proposing a linear equation for that. But it's not necessary that, in fact, it won't happen that every observed value of y will strictly follow this equation. So there will be a variation. So that variation is here, appearing here as epsilon. So that variation we call as error, because that will denote the deviation from the model, proposed model. And so so the mean is beta naught plus beta 1 x, and variance is assumed to be constant, not depending on the value of regressor. That's why you call it as constant. Constant in the sense, as you change the values of x, the variance doesn't change. So that's why you call it as a constant variance or homoscedastic model. So so the true regression model is this. And now the height of the regression line at any value of x is just the expected value. So I have elaborated this in the graph. So the beta 1 is because it being a slope, and the interpretation is that it is the change in the mean of y for a unit change in the x. You can easily understand this by considering the interpretation of the derivative. If you differentiate, you get beta 1. No? So the common interpretation of slope that is applicable here. So now I think this will help you understand the model better. So for different values of x, here the values of y, the densities of y are indicated by the normal density curves, because in regression the errors are assumed to follow normal distribution, and the values of the regressors are supposed to be fixed. So the distribution of y is again normal, and as a result you have the normal density, but the density's mean will change as you change the value of regressor. But the variation, because sigma square is same, so the curve spread of the curve is same no matter what is the value of regressor. So as you can notice that the change in location is happening as you change the values of the regressor x, as you move from 10 to 20, but the sigma square is constant, and then the observed value of y will be in, as you can see here on this line, usually in the area under the curve, maybe 98% or 95%. If it is not, then you call it as an outlier. So okay, so now when can we apply regression models, or can we apply them when when there is some existing model available in the context? So for example, there you may be dealing with some variables or some variables in chemical reactions or some physical experiments being conducted, and you are addressing them. So there can be a built-in relationship among the variables already, or there may be an partial knowledge about the relationship among the variables. So can then still regression analysis or the linear regression be used? So it's possible that the relationship is a bit complex one, not a straightforward one, but can a linear model can give a good approximation to the complex relationship. So in such cases, in all such cases, regression model, linear regression models can be used. Now we move one step ahead. We don't have, as I mentioned, you don't give only one internal examination. You appear for multiple internals. So you have a set of internal scores. So can all of them be used to predict the final score? This is the real data I have used. I got the data from one of my classes, and I had observed that all the variables can be used here. So all the variables do matter. So how to address this? So we have a model where response variable depends or gets influenced by multiple variables. So here comes the multiple linear regression model like this. So now you have k regressors influencing the response variable. So now why do we call it as a linear regression? Because the parameters are entering, not regressors, but the parameters are entering the model linearly. And so the model is referred to as linear regression. So if the regressor is say x square, you can call it say x nu equal to x square, and can still the linearity be retained. So even if the relationship between the response and the regressor are of a curve type, still that can be used. Still the same model can be used. So when k is equal to 2, the regression model is a plane. So this I have shown. Now these are minor points. Some of you have already maybe noticed it, but I'll mention it here because here all the regressors are influencing y. You cannot talk about just, or the beta j's can't be treated as just influence of just one. Means you can say that when the rest of the regressors are held constant, then the regressor under consideration, its effect is indicated by, on the response variable is indicated by beta. And so these are usually referred to as partial regression coefficients. So this I have included in the last. I hope that the slides will be made available to you if possible. So this is the plane for two regressors. So the regression model here that is plotted is expected y is equal to 50 plus 10x1 plus 7x2. So now the second graph is the contour plots. So assume that the expected value of y is 67. Then gather all the values of x1, x2 for which expected y is 67. That is shown by the first line, the lowest line in the second graph. Then the second line is for 84. So assuming that expected y is equal to 84, gather all the points x1, x2 for which expected y is 84 and so on. So now I'll illustrate it with some other examples. So suppose you are a consultant for an advertising or for a client who is spending lot of money on advertisements and is conducting advertisements on three media, mainly television, radio and newspaper. So he may have limited budget for advertisement on each of these media. So can we offer some advice to him, suggest him which or where he should increase his budget and where he should lower his budget so that he get maximum sales? So the response variable here is sales, and the regressors are the budget for television advertisements on these three media. So three regressors. So so the first step that you do when you try to fit the model or you want to understand the data is you look at the pairwise scatter plots. So this is the matrix. So can anybody tell me which advertisement is influencing the most? Sales the most? Huh? Here, if you consider, so what you are doing actually is you are trying to see where the correlation between the response and the regressor is highest. No? So if you look at the television, yes, for radio also, but when it comes to newspaper, the values are scattered everywhere in the graph, means there is nothing, or the advertisements appearing in the newspaper aren't influencing the sales much. So so this is the output of the R program where the regression model is fitted, and if you look at the summary of the regression model, then this is what you get. So I think most of you are using R for, so you will be able to understand, see that the television variable is coming out to be significant by the, if you follow the last column of p values, then the radio is also coming out to be significant, but the newspaper, the third variable, isn't coming out to be significant. So now I had mentioned the earlier situation. So here 3 exams were conducted, internal exams were conducted, and final scores were modeled on the basis of these 3 examinations. So actually I forgot to include the matrix plot of the same data. There it was clearly visible that third internal mattered the most. When it came to modeling the final score, I don't know whether it makes sense. I feel that it makes sense because by the time of the final third, that is the final internal examination, you get a good idea about the subject being taught. So you are more familiar with the course content. And so you are, in a way, you are better prepared for the final examination. That is not the case with the first internal. And so maybe that's why the third internal score comes out to be the most important or influential variable for this particular regression model. So these are the model assumptions. Errors have constant variance, sigma square. Then errors are uncorrelated. Then errors are normally distributed. So now how do we see everything here? You can say mu y given x is equal to beta naught plus beta 1 x is the model for the population. You have decided that you are going to model the final score on the basis of internal scores, but you haven't actually got the data. Suppose you are trying to do this exercise for a class of 50 students. So you haven't yet got the data. You don't know these parameters also, beta naught, beta 1. What you do now is you get the data. So it's like realized or observed values of the response variable and the regressor you have got. And now you will try to estimate the model parameters. This is how it goes. So, but how do we verify these assumptions which talk about the errors? Error is again a random variable. So how are you going to get the realizations of errors? So one way to do that is look at the residuals. So you have got observed values of response variable. You have got from the model, you have got fitted values. So look at the difference, that will be the residual. So from the residual, so residual is a kind of estimate of the random error So whatever assumptions you have about the random errors can be verified through the residuals. So how is it done? So I'll show quickly. So what I said I have mentioned here now. So how do we verify the assumption of normality? So through QQ plot, the assumption of normality can be verified. Then other test like Shapiro test can also be applied to check whether the residuals are normally distributed. Then the assumption of uncorrelatedness of errors can be verified by looking at the time sequential plot of residuals. So if there is no pattern exhibited, like indicating any positive autocorrelation or negative autocorrelation or any kind of correlation, then you can say that the errors are uncorrelated. Then when it comes to verifying the other assumptions, the plot of residuals against regressors is useful, or the plot of regressors against fitted values is also, it serves multiple purposes, in the sense if there is a, okay, I'll show the graph. See, the first four, if the values are the first topmost figure A, it indicates the plot of residuals against fitted values. So if the values lie in a horizontal band, then there is no abnormality. The model assumptions are fulfilled, model assumptions. And then if there is an opening funnel kind of pattern as shown in the figure B, then it will mean that the variance is not the same. Now, what is the meaning of this opening funnel pattern? So if you are at the lower side of the regressor values, sorry, when you are at the beginning, see the variation among the values of the residuals is less, but as you move towards the right side, the variation is increasing. This is what we mean by the opening funnel pattern. Then the second, the figure C, the double bow, that also indicates that the linearity isn't there. No? The linearity isn't there. Then the third one also indicates the same. And now the figures at the bottom, they indicate that now these are the time sequential plots of residuals. So as you can see in the first figure, there is an increasing trend till a point, and then it's decreasing. So it means that there is an increase. So till say 0.4 or 5, there is an increasing trend. So it's like there is a kind of positive autocorrelation among the residuals, and maybe of lag 4. So those who are familiar with time series, they will understand this. Then in the second one, again, there is a pattern. And so you can say that then the residuals are not uncorrelated. So, so the same exam data, which I mentioned earlier. So here, this is the QQ plot. So as you can say, or if the values lie on the or around the line, then you have normality. So some amount of deviation from the line is all right. So how much amount of deviation is okay and how much is not okay, that we don't have that much time to dig deeper, but you do take into account this. So that's why when people are in doubt, they go for the Shapiro test, or otherwise also you can always go for the Shapiro test of normality. So clearly you have p value here indicating that the assumption of normality isn't getting rejected, and so you can safely assume normality of residuals, at least for the exam data. Now this is the plot of residuals against fitted values. So there is no pattern, so you can say that the variance is constant. And then the last one, sequential plot of the residuals, again doesn't show any pattern. So all the assumptions related to the model are fulfilled for the exam data. Okay, now I'm finishing before time. So now the question arises. See, all this discussion is for quantitative type of response variable. But what if the response variable is qualitative? Whether it will rain today or not, whether the laptop will work or not, whether all the, so many things are there, na? Where you don't have, you have answers of the type yes, no, or categorical like good, bad, ugly. How, what is your mood right now? Bored, very bored, huh? Something like this. So it's qualitative, it's not quantitative. So then can we come up with a regression model for such setup? So what if it is binary? So the answers will be revealed in the next lecture. So thank you.
Thank you so much, Madhuri ma'am. I now invite Professor Sushma Bendre from Indian Statistical Institute, Chennai, to deliver her lecture on logistic regression, generalized linear models, and classification.
I hope you all can hear me. There's going to be a little bit of an issue because we were told that there's going to be an audience which is mostly non-statistical except for 20 statistics students, etc. So the slides are prepared assuming that the slides are prepared more for the non-statistics audience. Okay, so most of the things which I'm going to discuss, good number of you who are doing MSc already know possibly. Okay, we'll be talking about logistic regression, classification, that's the topic. But what I'm going to do, okay. What I'm going to do is basically go in this line. I'll just talk about the concept of generalized linear model and then talk a little bit about logistic regression model. Okay. And then we'll basically be talking about logistic regression as a classifier, which is what many of you have already done in your in your machine learning course. Okay, so yeah, before I begin, any question, any doubt at any time, please stop me and ask. Okay, all right. So we are going to start with the we always start with the data. So what kind of a data we have? I'm just taking few examples, modeling the available information. The first one is about the body fat, and the body fat is an important component, etc. We all know about it. And then the question is to investigate whether there is a relationship between the percentage body fat and these other components like age, height, weight, abdominal circumferences, and etc. Okay. You realize that the question here is about finding a relationship between the body fat and other variables, but the body fat is in the percentage, which is a quantitative variable, something we all understand, though I did not prepare the slides for that. The second question is about the gender discrimination with respect to wages. This is, of course, I have the actual data, which is coming from the Western countries where this is a big problem. It's known that women end up getting less money for the same job they do. Okay, so there is a question about gender discrimination with respect to wages, and men get higher wages than women with the same characteristics, such that education, qualification, age, etc. So the data is collected on the wage, age, gender, education, qualification, and the years of education. Okay, so both these examples are actually talking about multiple linear regression. Okay, because the second example, the question is about the data collected is on the wages, and you want to talk about the wages, which is again going to be a continuous or a quantitative random variable, and therefore you can just go for multiple linear regression. What I am talking about now is once again we are modeling the available information, but the information is something like this. This is the data I have. The success of surgery based on gender, age, health condition of the patient, hereditary factors, etc. Okay, so you have a good number of variables or the issues which are giving you information about success of surgery, and you really want to decide whether a patient, because finally for a patient, he or she does not care about the data. What is important is whether the patient will survive or not survive. So the issue is about whether surgery is successful or not successful, and that is what is going to be the problem there. I took this banking example because that is what you're going to discuss in the afternoon session, where you will have Professor Vijay Nair talking about all these things. Okay, I don't know how many of you know about it, but then typically what happens is a good number of customers apply for loan. Okay, it could be housing loan, it could be vehicle loan, whatever kind of a loan. Okay, and then the banks go through your, and you have to give a lot of information about yourself. The banks go through your information and then decide whether you are eligible for loan or not. Okay, so the idea is to basically decide whether anybody who's applying for a loan is eligible or not, and that's going to be just a dichotomous quantity, either yes or no. Okay, the same thing is happening with the credit cards, whether somebody can be given a credit card or not, whether the credit card limit, there is always a limit on the amount on the credit card, whether the limit should be increased or not. Okay, anytime we are talking about yes or no, okay, we can talk about a dichotomy. Okay, binary data kind of a thing, and that is what is really happening. So the capacity to repay depends on various factors such as steady income, source of income, other commitments, etc. And this is the kind of an information banks ask us. Okay, what are your other loans? How much money you earn? What is the number of dependents? What is the, who are going to be the surer in case you are not going to repay the loan and things like that. So all those things are the information, background information you collect from the customer, and then you decide whether the customer should be given a loan or not. Okay. There is something else. I'm taking that example because that is something we really have used many times. There's a question of churn. It's a problem of churning. Okay. This is what I'm sure you all use mobile phones, and you all have some mobile service provider you have subscribed to. Okay, but then something else comes in the market which everybody, your friends, say is better, and you immediately shift to that. Okay, for instance, Aircel was one of the companies at one time, and it's not there anymore. Aircel went bankrupt and closed down because Jio came in the market, and a lot of people shifted to Jio. Okay, so that is what is called churning. I'm just giving an example of mobile service companies, but then it can be even for your grocery store. You're going to some grocery store and suddenly somebody else gives you better service and you move. Okay, for the service provider, it's going to be a problem if too many of you move away. So, and they also always want to know about this problem of churning, the customer leaving and joining other service provider, and then it is important to understand which aspects of service influences a customer's decision in this regard. And you know that sometimes they offer us certain deals. Okay, those deals are offered to sort of ensure that you continue being with that service provider. Okay, so all such things get decided based on the kind of an churning they experience. Okay, attrition is another issue. The resignation of an employee typically affects the particular work or project that the employee was engaged in. But in IT companies, attrition or leaving the job is a very, very common phenomenon. If you continue with the same company for longer, it does not reflect very well on your CV, right? That's a very common thing. So you generally try to leave the job and move to another job after 3 years, 4 years, whatever. All the companies are aware of it. They call it attrition. And then there are two things. Firstly, they do not want too much of attrition at a given time. And second thing is they also always have to be ready about the certain percentage of individuals attracting to a different job. Okay, so is it okay? Yeah. So employee attrition, that is the kind of data we have. And then what really affects the the organization prefer to know how various factors such as age, gender, qualification, location, type of job, type of incentives, etc. affect the attrition. Now that, I'm not going to come back to this, I'll just tell you that I was doing this attrition analysis for one of the companies, and I'm including type of incentives because it turned up that the type of incentives really mattered. And, if it was for the freshers, okay, if the freshers are sent for some training courses, the chances of attrition were reducing, right? So that naturally helped the company in deciding that, they will try to send a lot of people. They won't send the same person again and again to different things, but they will keep rotating and then keep sending a lot of people for different kind of training courses and so on. Okay, so this is again for an insurance company. The interest is in predicting the number of claims. This is again a very common example. Insurance companies want us to insure, okay, and do not want us to claim. Because if everybody who insures claims, the company is going to run into bankruptcy. You understand that, right? So their interest is to naturally make sure that the number of claims is less and number of people insuring anything, whether it is a health insurance, whether it is vehicle insurance, whatever, the number of insurers is lot more than the number of claims. Okay, so their data is on the predicting the number of claims that an insurer will make in 1 year from the third-party automobile insurance. Again, I'm just considering only automobile insurance, but it could be any kind of an insurance. You can have home insurance, you can have health insurance, individual insurance, and so on. And every company is interested in sort of figuring out the number of claims and whether they can predict the number of claims depending on the different variables. Okay, so in all these examples, this is something which is again written for non-statisticians, but you all know this. There is a random variable, there is a variable of interest, there is some information we want to have based on other things. So whatever information we want to have, that variable is called the response variable. Why? Okay, I'm saying this because non-statistics people come to me with the data and they have no idea what is the response variable, what are the information variables, etc., and so on. So whatever is the variable of interest is our response variable. That can be a numerical variable such as percentage body fat, or a binary or dichotomous variable such as whether surgery is successful or not, whether a customer is given loan or not, if the customer is churning or not, etc. And then the third situation where I'm talking about the number of claims, it is a count variable because number of claims is always going to be an integer. So the variable of interest is essentially a variable which is going to be see for in our example is going to be number of claims. So once you say number, it's going to start with 0. It's never going to be negative, and it's always going to take integer values. All right. So that is called count data. Okay, and then you have different models for that. So it can be a binary variable or a discrete integer value random variable, and that is where the problem comes because you cannot really have linear regression models. Okay? So additional information is provided on other characters such as age, height, etc. Age, weight, hereditary factors of a patient or steady income, source of income, other commitments, personal and financial, credit score, customer background, etc. When it comes to the loan approval. Okay, the amount insured, this is about an insurance claim, the amount insured, the make of the car, the non-claim bonus received last year, age of the insurer. The insurance data always, something which is important for you people because the age of the insurer really matters. Okay, and it has already been discovered that the younger people, less the age, higher the chances of accident, and therefore higher the chances of claim. Okay, so that is the kind of variables. I am not going to talk about feature selection, but the kind of variables we are listing here are all informative. Okay, you have already talked about informative variable in your earlier talk. I'm just talking about the examples all have informative variables. Okay, so these characteristics are believed to have additional knowledge. I'm saying believed to have, but in the examples we already know that they have additional knowledge on the response variable and can affect the value of the response variable. And then the information on these characters act as regressors for explanatory variables, and they are denoted by x to XP. That is what we'll be using. Okay. This can be regressors can be numerical, categorical, and need to be handled appropriately. I'm just going to move on to the next slide. What is our aim? Our aim is to build an appropriate model to use the information available on the regressors or explanatory variables to make better prediction about the response variable y. Okay. But then that's what I'm going to talk about initially. We always try to model the information available in the regressor variables as a function of this regressor variables or explanatory variables, and that function is the expected value, or you expect your response variable y to be some function of exponential. That is what we are doing. So we will be always talking about the mathematical function expected value y is equal to function of exponential. We are of course assuming that
expectation exists, etc. Since you're all statistics students, I'm just going to specify that. And then the interest is to provide a mathematical function based on given values of exponential xp, and it helps in predicting the expected value of the response variable. It helps in predicting the expected value. Okay, not really the exact value which we will never know. Alright. The function involves the unknown parameters to be related by Greek letters, alpha, beta, etc. And then what we are going to do is immediately we started with a function, but we are going to treat it as a function of linear function. Okay? A linear function of what? It's a linear function in the parameters, unknown parameters, beta naught, beta 1, beta p, which are the unknown parameters. X1, x2, xp are the explanatory variables or regressors, which I can have anytime I want. And therefore, I'm going to talk about the function of the linear functions. And then this is what is generalized linear model. Okay, if my function of linear functions is a linear function itself, it's an identity function, for instance. Okay, then I get the multiple linear integration. Okay, I depending on different values of y, I get different kind of models. But this basically this. Anyway, this is what is a generalized linear model. Okay, this is where you begin as far as generalized linear model is concerned. This leading to y equal to the expression plus epsilon actually involves a lot of assumptions. Okay, I did talk about it in the basic course while we were discussing something else there. But for the generalized linear model, this is the basis. Okay, and then why do we do the modeling is the issue. The predictor model expected value response variable for a new case based on the data on the explanatory variables for that case. This is also supervised learning, so I just put that in the bracket. To study the impact of one explanatory variable and the response variable keeping other explanatory variables fixed, that can be really be done using this, because you can keep other variables as fixed. I'm not saying constant, which is fixed growth. Okay. To verify whether the data supports certain beliefs. We test of hypothesis where we are basically checking whether the certain beliefs which we have are satisfied or not. So that is what it is doing. And then the fourth one is to use the model for transformation of a unit based on explanatory variables. And that's exactly what we're going to be discussing at the end. Okay. So this is all about generalized linear model, but then I'm just giving us the one slide on different models. Your setup is response variable y, explanatory variables or regressors exponential xp. The objective is to model expectation of y in terms of function of exponential xp. We are going to talk about the linear function of exponential xp, linear in the parameters, of course, and then the model ideally depends on the type of response variable under consideration. Y is continuous and y can be assumed to be normal, then we go for multiple linear equation. If y is continuous but it cannot be assumed to be normal, we have other models. Okay. I'm just talking about gamma. Okay, but then there are a lot of other possibilities which exist as a particular cases of generalized linear model. Okay. Because I am talking about expectation, I am not talking about y is equal to the mean plus epsilon. Y equal to mean plus epsilon does not work for gamma distribution, because we know gamma distribution is not symmetric around its mean. Okay. So once I talk about mean plus epsilon, that epsilon is going to take plus minus levels. We're going to make the assumption that epsilon is normal. You make an assumption of epsilon not being normal, but even then it does not work for many of the continuous variables, continuous distributions. So we are not going to, the second case, we will never be talking about the kind of a model we talk about for multiple linear regression, y is equal to linear function plus epsilon. That is called an additive model. And then this is the situation where you cannot really assume an additive model on y. Okay. If y is binary, we talk about logistic regression. That's also a particular case of generalized linear model. If y is long data, you can talk about Poisson, negative binomial regression. That's also part of the generalized linear model. I don't know whether you have done this, but then this is an example. The earlier lecture your madam was mentioning also. Okay, you can have multiple categories: good, bad, ugly. Okay, very good, very bad, okay, kind of a things. Okay. You can have, that is your response variable, and then you are going to have a lot of predictor variables or explanatory variables. So based on these explanatory variables, you can decide you can come up with a model which will give you expected value of y as one of those categories. Okay, typically we take odd categories. Okay, and then that is what is called multivariate regression. I think you all know. You already talked about binomial distribution, right? You already know multinomial distribution. So this all is basically just as I can talk about binomial distribution for logistic regression, I can talk about multinomial distribution and then have something like this multi-category data model. Okay. So these are the different models you can think about. And then I have taken an example. I took this example, though it is nothing to do with banking and loans, etc. But one of the reasons I took the example is because there is only a single regressor here, or single experiential variable, which is age. Okay, so the records are from surgery on 40 patients where y equal to 1 if the patient died within 30 days of surgery and 0 otherwise. This it is about survival or death. It's not even whether surgery is successful or not. It is much more severe than that. Age in years is recorded for each patient, and then of interest is the effect of age on the chances of survival. Okay. You would be particularly interested in knowing whether age is associated with survival rate, and if so, what is the relation between age and the chance of survival. Okay. So note that yi equal to 1 stands here for death. Okay. So success is death, and naturally you realize the success is death. If I am a doctor, I wouldn't really be treating success as death. Okay. Whereas if I am an pest control person, for me, death would be a success. Death of a pest would be a success, and so on. What is of your interest and how you define it definitely matters. But what is important is you appropriately change your whole model. Okay? So y equal to 1 here stands for death here. Death, so success is death and needs to be interpreted appropriately. That's what I am saying in this case. Okay, this is the scatter plot of surgery data. Okay, so it's age versus success, or death or survival. 0 is 1 is death, 0 is survival, and what it is showing is basically the data is going to be just something like this. You have age on this side and you have yi on this side. Your yi is going to just take two values, 0 and 1. Okay, I have defined it with the dichotomous variable y. The outcome of interest is to the experimenter is called a success, and we define y equal to 1 if the outcome is success and 0 if the outcome is failure. Okay, so what we have plotted here is nothing but the values of y which are either 0 or 1, and then age of the patient. Okay, and that is where the whole problem comes in. We want to really talk about the relationship between age of the patient and y, but then we are going to model it as expected value of y. Okay, so we want to express age of the patient as the expected value of y as a function of age of the patient. Okay, that is the only single regressor here, or single response. And then what we have is something like this. We have a binary response variable taking one of the two values, 0 and 1. And then I'm going to talk about pi as a probability of success. Okay, anything which is dichotomous, we don't really have to question about the underlying distribution. But binary Bernoulli random variable is dichotomous. Okay, so you have any variable which is taking two values, you can always convert it to a Bernoulli random variable. So unlike what happens with normal distribution, when you question the normality and you try to check for normality, you do not do that for such situations. Okay? You only have to appropriately define your variable to be 0 for certain values and for certain situations and 1 for certain situations. That's what we have done. And then once you have y at 0 or 1, you can talk about probability of y being 1 and y being 0. There are only two possibilities. And then with that, you essentially end up having a Bernoulli distribution. Okay? With a parameter pi. Pi is your probability of success. That is your parameter of interest. And what we are going to do is, of course, we know that for a Bernoulli random variable, the expectation of variance is going to depend on pi. Okay, you are talking about a particular generalized model. So you're going to model your expectation of y as a function of x, which means you want to model pi as a function of x. But your x is changing, so as a result, your pi will also change. Okay, so this is the situation where your expectation of y, yi is going to be pi I, will change with different use of XI. That is fine. That is what happens with multiple linear regression also. But in addition, you have a lot of other assumptions for multiple linear regression. You assume normality. There is no normality here. Okay. You assume equality of variances. You see what happens here? Your variance is a function of pi and 1 minus pi. So if your pi is going to depend on x, your variance is going to be different for different kinds of x. Okay, so you cannot have an assumption of homoscedasticity. You cannot have assumption of normality. You don't have assumption of linearity. You only have the assumption of independence of the variables by x. Okay, and that is easy to understand. That's easy to check because you have n variables. Typically, you have much larger data. Your n is very large. But then given the n variables, it's not very difficult to really figure out whether the response or given the data on n units, whether this data can be treated as independent data or not is not really very difficult to figure out. Okay, so the rest of the three assumptions you don't have here. This is just the simplest of the example of generalized linear models, but you will understand that for all generalized linear models, we come out of those assumptions which we made for multiple linear regression. Okay, so we have, of course, this is for the binomial random variable. You all know that. I was going to skip, and I have really skipped much of the discussion on binomial variables because, as I said, I was treating it like a discussion for non-statisticians. Okay? But then the point is this: we had said we want expectation of y to be a function of linear function. Okay, so I have a linear function now. Okay, but then the function of linear functions is fine, but that original function is not linear anymore. You understand that? It's of the type e raised to something divided by 1 plus e raised to something. Okay, that is what we do for logistic regression. And then, of course, you can have, I don't know, you must have done probit regression also. See, the idea is very, very simple. Your pi is between 0 and 1, right? Which essentially means that you're going to talk about a function of linear functions. Linear function part is fixed. Okay? That function should be taking values in 0, 1. You understand that? Expectation of y is a function of beta 0 plus beta 1 x1 plus beta 2 x2 and beta plus b. But that function should be taken between 0 and 1. Now comes the question: what is the typical function we all know which is between 0 and 1? Distribution function, cumulative distribution function is always between 0 and 1. So you can take different cumulative distribution functions. Okay, and you can show that this actually is a cumulative distribution function corresponding to a logistic distribution. So one of the reasons it is called logistic regression is also related to logistic distribution. You understand that? Okay. You can talk about a normal cumulative distribution function of a normal random variable, and you get what is known as a probit regression. Okay. But you do not necessarily need to restrict to that. You can treat this function to be some f of. You just take it to be f of the linear function. Your f is going to be the CDF, and that will always be between 0 and 1, and that's what you really know. Okay, so this is something you got all statistics students. Now I can talk about it. This is same as converting it pi is equal to this. So log of pi over 1 minus pi can be written as a linear function. Okay, and that is what is known as a logic link. I think you all know about it. You know what a link function. So the whole idea is to have a link function which is relating the linear function with expectation. Okay, and then that basically instead of treating the function of the link function, you take f inverse of that function of the link function. That's the only difference. But in the generalized linear model, when we talk about a generalized linear model, in general, without really going for the particulars, we just talk about expectation of y, which is mu. Okay, the linear function has some eta, and then you link this mu with eta through the function. Okay, and that is what is called the link function, and then logic link function becomes the canonical link function. I think you all know about that also. I don't know how many of you know that. It becomes a, once you talk about generalized linear model with independent variables, you talk about exponential family. How many of you know about it? You've done statistics, right? Many of you are doing second year of MSc, first year of MSc. How many of you are not MSc students? Okay, so only 3 of you can be excused, but the others should know about the family of distributions. Y is a random variable. So we are always going to assume that every time we have a random variable, we have uncertainty. Okay, we have a cumulative distribution function, but we assume that the density exists, or density or mass function exists, and we assume certain conditions on that probability density function, probability mass function. We assume that it belongs to the exponential family. Right? So that is, it all comes, and therefore this becomes a canonical link function because of the properties of the exponential family and link functions and so on. Okay? That's something we can always show, but then once you have this, because you see what is going to happen to beta naught, beta 1, beta p, and x1, x2, xp are not going to give you a function which belongs to, which is in 0, 1. Okay, your y is going to be 0 or 1. Your expression of y is always going to be between 0 and 1. And you need something which is between 0 and 1. Okay, so taking an f function helps you, and in particular, we take the cumulative distribution function of the logistic distribution. That is what we have. So you have which ensures that y lies between 0 and 1. And then I'm just talking about fitting your integration model. I think you all know this. You all used R. This was a slide for, again, non-statisticians. I deleted the slides on odds ratio, assuming, but I suppose most of you know about odds ratio, something which we can discuss here. Okay, the odds, log odds ratio, etc. Because the logistic ratio helps us in talking about all those things. And those things, basically whatever we can talk about using logistic regression, we can generalize to multi-logic regression. So the idea is basically, you have linear model, then you go for generalized linear model, trying to make sure that the kind of properties you are talking about are not exactly same, but parallel to what you have for multiple linear regression. Okay. Then you try to generalize it to multi-logic. Multi-logic is not a generalized linear model, but multi-logic regression, you try to copy, or you try to have similar conditions and similar properties which you have for binary kind of data or logistic regression. So you use iterative derivative least squares. I don't know how many of you know about that. If you are statistics students, you need to know what R does, not only how R does. Okay, so you need to, I just wrote the command GLM, but that is for non-statistics people. For statistics people, what does the function GLM do? You must know. Okay, so it uses, it is inputted using the built-in function GLM bracket in R packages, and calculate used for classification also is what we are talking about. So I just have fitted model. I'm going to say something. Okay. Every time you go for R output, it gives you something after this. It gives you something after this, 1 star, 2 star, etc. I have intentionally removed it because you should not be looking at that 1 star, 2 star, etc. You should be looking at this column, which is the column of p-values. Okay. I'm saying this because p-value is something which is important. P-value is something which talks about the available data. The 1 star, 2 star only talk about level of significance, which is a very ad hoc procedure. And lot of, most of the people now, non-statisticians, have started using p-value. Okay? And then they tell me, or people like us, that what is this? Your students don't know anything about p-value. Okay? So just get used to not talking about accept something, reject something. See, the point is, who are you to tell me, if I'm giving you the data, who are you to tell me what to accept or reject? You tell me what my data is saying, is what will be the reaction of anybody who is providing you the data. Okay? And then the p-value talks about the data. You don't come in the picture, you are only via media. So never say accept H0, reject H0. You have no business to tell me whether I should accept H0 or reject H0. You only tell me what is the p-value based on my data. And then that's what is going to be the case. So I have removed those stars. I have removed that line which talks about what are those 1 star, 2 star, etc. Try to ignore it. Okay. our views, that's I would treat as an some kind of an drawback of R. Okay? We should be aware of p-value and we should be looking at the p-value. Okay? And then you can see that the p-value is significantly small. So the constant as well as the age is the age significantly affects the success or failure of the. Okay? I've just given the fitted values. Okay? And then of course, that's what I'm saying. P-value is small, so age variable significantly contributes to success. The data is on the patient with age greater than 50, and hence the interpretation holds only for such patients. This is another important thing. Anytime you are modeling, you try to see what is the range of your regressors. Okay? Whatever else you do is always going to be extrapolation. And extrapolation is always unreliable because you do not know what is going to happen beyond the data which you have given. Okay? Here also the data is given for greater than 50. The patient with age greater than 50. So we are going to use it to interpret something about the patients with age greater than 50. Somebody of the age of 25 comes to me and then has to be recommended this kind of surgery or not. This data is not going to be enough. Okay? This is something you should always be aware of anytime you're doing the data analysis. Right? Okay, this is about the fitted values. Okay? You get the estimated values of the parameter to be something like this, and then you end up getting the fitted values of yi, which are given by this for a given age. Okay? So your yi hat is going to be the hat of the expected value of yi given xi equal to age. Right? So I have not written given something, but that was something the real lecture Madam had already given also. So we just really showing something. And then this is where the classification actually begins. Okay? What you get is something like this. The blue value is the blue curve is the curve corresponding to the fitted values. Okay? The fitted values are going to be the expectation E hat. Okay? So what we have, I hope you can all see it. I'm talking about expected value of yi, which is actually expected value of yi given xi equal to. That's what it is. Okay, I'm putting an hat on this. I'm estimating this. I'm putting a hat on this. But this hat is going to be my expectation is pi, so I'm just going to get pi I hat. Okay, and my pi I hat lies between 0 and 1. But think about it, a patient comes to me, I have to recommend surgery or I have to either recommend surgery or not recommend surgery to the patient. The patient is not interested in the expectation. The patient is interested in whether he will survive or die, right? That means any one of us is only interested in 0 or 1, but what we are getting is something which is between 0 and 1, and that's what it is showing. So now what we need to do is talk about some kind of a threshold. The value below that threshold is 0, values above that threshold is 1. Okay? But logistic regression is the only classification technique which helps you doing all this. Okay, and now what I can do is, I couldn't really make the slides of that, but what I can do now is think about, so I have a curve like this. You can all see this. I have 0 values, I have 1 values here, I have 0 values here. I just want to have some kind of a line separating them. Okay? This side of the line, whatever are the responses on this side of the line, that means I want to really talk about some value which is sorry, not here. The line will be the other way. It's y. Something like this. So all the values of expectation of y below this line are treated as 0, and all the values above this line are treated as 1. Okay? Because finally what we are doing is we are going to talk about classifying y into 0 or 1 given the data. Okay? And that is where the classification using logistic regression begins. Okay? And then I can generalize it to the multi-logic situation also. I can have multiple classes. Okay, and I can talk about splitting it into multiple classes or predicting which of the class the response will be based on the given set of explanatory variables or indices. Okay, so what I'm going to do now is talk about something like this, okay, the classification, and then the aim is to decide based on the fitted model whether given the age of the patient will survive or not. So given the age, to let the model predict whether the response is 0 or 1, and that's what is the classification for us. Okay, this leads to classifying the patient into two classes, survival or death. Okay, and then of course, typically what we would do is you probably wouldn't tell the patient the chances of death or something, but then if the age of the patient is beyond something, you would just not recommend surgery because you believe that your data for that particular age is giving you value of YI hat much larger than whatever is your threshold here. Okay, so the chances of the patient dying are more than the chances of patient surviving. Right? That's what really happens, and that is how you use logistic regression. Okay. So for any classification technique, I think this is something you all know. Splitting into training data, validation data, and test data. Okay. You always have very large data as the as you heard from Mr. Also, we are in an age where large data is not a problem. The proper modeling and proper analysis is a problem, and as statisticians, it is our duty to sort of address that. Okay. So we are going to be talking about splitting the data into training, validation, and test data. Validation is cross-validation, which you call it. Okay. Typically, you have a much larger proportion for training data. So the split is 70, 15, 15, 80, 10, 10 kind of a thing. Okay. You never talk about equal training and test, training, validation, and testing. You always have a much larger set from the training data. Okay. And then for a logistic regression based on the training data, we need to decide which values of the predicted, because the logistic regression is going to give me something like this. Okay. The line which I had earlier. Okay. After I do the fitting, I'm going to get something like this. Now, where to draw that line? Okay. I use cross-validation as well as testing data. Okay. Making sure that what I get in the process is within a threshold, and what I do is this is just for two classes. So we have something called confusion matrix. I'm sure you're going to have a talk on machine learning later on where it will be discussed in more details. So I haven't really talked about it. But what you do is that there is a fact the patient survives or does not survive. If it survives or dies, and then your model-based prediction is going to be whether the patient survives or dies. Okay. These two stars is the correct decision, and the other two are errors. Okay. You try to optimize the errors. Okay. So your prediction, your threshold is going to depend on your confusion matrix. Okay. So what you do is that you basically try to see different predictions. That is, you try to take different values of this pi, this line, move it. Okay, it's possible to do it using any package now. I'm talking about R because it's very easy. You don't need to do anything. And then you look at the classification matrix. The classification matrix also gives you various measures. Classification or confusion matrix. There are various measures based on the confusion matrix to decide the appropriateness of a classifier. So you decide which measure you're going to choose, or which measures you have considered in deciding on the threshold. Decide the threshold and then appropriately with the classification. Okay. So the logistic regression model as a classifier is going to give me something like this for any given set of experimental variables. The model gives the predicted response using the predetermined threshold value. One can classify the predicted response into one of the two classes, and then you have a choice of threshold. You have a statement about the probability, the sense of probability of becoming. You actually get the estimated probability. Then you talk about the threshold. You can also talk about the misclassification probability. Okay. It becomes really difficult in many other classification techniques. You end up having only empirical estimates of misclassification and classification there. Okay. Here you actually end up getting estimates based on your model. You have statement about odds ratio, etc., and so on. Okay. So as far as my discussion is concerned, I was going to stop here with anything about, these are the references. My references are of course going to be more for statistics students. Since you're all statistics students, I think I can just share the references with you. Okay. You don't need library anymore. Everything is available on the internet. So do have the references and put slides if they're available to you, so there won't be any problem. You can always do that. I think there are these references definitely give a better discussion on segregation. It talks about the linear model, it talks about multivariate models, and so on. Also. Okay, so I think I will take the questions at this stage. If you have any questions. That's what I'm saying. The criteria for decentralized threshold will be based on this. What I want is 0% for this of diagonal and then full percentage for diagonals. You understand that ideal situation? I would want to have correct classification. So those who will die, my model should say they will die. Those who will survive, the model should say they will survive. That never happens. Understand that? No data set you are going to get. This is a matrix. What I need is diagonals should be adding up to 100% and non-diagonals should be 0. That's the ideal setup. But I'll never get that. Understand that? For the very simple reason that you see this here, I'm going to have some threshold, but then the values beyond threshold, I will say are 1. But there will be some zeros. Understand what point I'm trying to make? Okay. So your data is never going to be, and then the data will never give you the perfect classifier. Data is always going to be, there is going to be randomness. That's the reason why we call it data. Otherwise, there will be randomness, there will be statistics also. Right? So you decide on your threshold, and then many times, look, I have used logistic regression and multivariate model. What I have done is use the threshold and try to discuss it with the people who brought me the data, saying that this is the threshold for which I'm getting something like this. This is the threshold for which I'm getting something like this. What exactly do you prefer? Okay. The threshold which is decided doesn't necessarily have to be what is giving me the optimum. So for instance, I have talked about 0.38, I talked about 0.42, and then you decided we just take the general threshold to be 0.4. 0.4 was not giving us the optimal thing, but we still decided on 0.4. Okay. So yeah, I think I hope it answers your question. You have
Hello. My question is, you have calculated or estimated betas there. So how we have to interpret those betas?
okay, yeah. These are my betas.
Yes.
These are my estimates. What really happens is, now that you are a statistics student, the integration, and it is only 2 classes, the failure and odds of success. Simply odds of failure here, because failure is my survival. But I just talk about odds of success, and then I can talk about odds ratio when age is 51, say, odds with age is 51 and odds with age is 52. What does it mean? I have increased my age by 1 year. Okay, so 1 year increase in age, what happens to the odds ratio? I can look at it like that. Okay, so if my odds ratio, and then you know how to measure odds ratios, right? Whatever you get, you subtract 100% from there. So whether you get less than 100 or more than 100 and so on. Okay, what has happened here is that my odds ratio is something like I think 22%. Okay. So 1 year increase in the age increases your chances of death by 22% is what is happening. And that's how I interpret it. That's the reason I took this data, because what really happens is that it's, given an age, of course my age has to be more than 50 because that's the data. But given an age, I can talk about the chances of death. Okay. And then I can say that if you increase the age, instead of this year, if you come next year for the surgery, the chances of success of the surgery are reduced. That's what it is saying. Okay, and that is what it helps in telling you. Okay. Anything else? No other questions? you can stop them.
Think you should ask maximum questions because basically what we planned the morning session is a kind of preparatory session for the afternoon. So some of, as Madhuri ma'am and Vendri ma'am mentioned that some of the statistics students might have learned this, but you make the points clear as well as the others also you should try to ask questions and make the things clear because we have planned this in such a way that this is the kind of an informal thing. Whereas you have more ML applications in the afternoon, which requires, the basics of recursion and other things. So that's how it is planned. So if you have some difficulty, please ask and clarify.
So probably you don't have any question. I'll only make some statements about, what is going to be covered in the afternoon. The speaker knows the slides are there and so on. But then when we are talking about banking or finance data, there are two possibilities. One is that the data is taken every day, etc., which becomes time dependent. You know that, right? So for instance, shares data is time series data. What is going to be discussed in the afternoon is not time series data. It's going to be basically the IID data, the kind of a thing. So one of the situations which I discussed was about loan sanction. Okay? I actually have, now I can take the name also because it's long before, but from Shanghai Bank, you heard about it, right? It's international bank. They had come to me for some data. They wanted to know, the whole problem was this, they had all those huge number of, you can think about an Excel sheet, your columns are your variables, explanatory variables, and your rows are your number of observations. It was a huge data they had collected, because when we are applying for any kind of a thing, they ask us too many things. And all that information they had sort of tagged, appropriately put in the variables kind of a thing. It was a huge data, and then the problem, one of the problems they had was whether to sanction credit card or not. Okay? This was at a stage where initially when the credit cards came into existence, everybody was given a credit card. Then they realized that even the person working on the street would have a credit card. Then they realized that that's not going to be profitable because there are a good number of so many banks had problem with getting the dues recovered, right? So then they started putting conditions on whom to give credit cards. So the data they had was about, one of the problems they were having was whether to give somebody credit card or not. The other problem was whether to increase the credit limit or not, whether to give loan or not. It was a big data, but then their response was basically just dichotomous in the sense that it was about yes, no, they never thought about a third possibility. You understand that, right? So it was mostly logistic, but then there is something else I must tell you. That's what we will learn in the afternoon session. Of course, once you have binary data, logistic is the only thing you don't question, etc. But my experience tells me that logistic does not always give you a very good classification. Okay. Often, for whatever reason, I personally feel, that's my personal opinion, but neural network I don't treat as a statistics problem. Because neural network, it does something, there's a black box, we don't know what it does. Okay. But then I have had data sets, not just numerical, I have had data sets of pictures, unstructured data as we call it. Pictures, answers, replies, telephone talks, and so on. And then the neural network often has worked better than logistic. So when it comes to classification, we will learn it in the machine learning lecture as well as in the afternoon session. What we try to do is do many methods. Okay? We are talking about logistic classification using logistic regression right now, but you just try, you given the data, you try different methods and then try to see which one is most suitable for a given problem. Okay? That will be decided by your test data. Okay? So only after you decide, you can sort of recommend that. Right? Okay, so I think I will stop with this. If there are no more questions.
Thank you, ma'am, for such an insightful lecture. We'll now be taking a 15 minutes break, tea break. Tea is being served outside the lecture hall. Many of you are MSc first year students. And those who are in MSc second year, how many of you have already had, or not had, perhaps would be a better thing, have not had any exposure to data mining or machine learning models? From second year, almost everyone knows. Hello. Is it okay now? Okay. Okay, so we are going to have a small retake. So we were talking about differences between the classical setup and the machine learning setup. So as I said, generally, if I want to say that my model is performing good, in some sense, if my model is good, then it should be able to do whatever it is supposed to do on a new data also. Either it could be predicting a class of something or predicting a continuous value of some variable. Okay. Typical classification exercise which we study from BSc first year is classifying an email into spam email or a useful email. Nowadays, in fact, the technology is further advanced. We have all those fancy tabs in Gmail, so social, promotion, everything. So classification. So if a model is doing classification, and if I have given a data set, a corpus consisting of 1,000 emails, then if the model correctly predicts those 1,000 emails, it's not enough. When a new email comes, it should be able to classify. That's the real test of a model. Okay. Hence, in the machine learning setup, we divide the data into multiple parts. We could call it the data which we use for model building is generally called as train set or training data. And the data on which we actually examine the performance of our model would be called as test set. Sometimes we talk about something called as validation set. Why validation set? Because many a times we need to do some sort of parameter tuning in a model. For example, you saw the regression examples. So in regression, we have something called as best subset selection. So I have 10 regressors. I may not need all of them in my model. So how do I choose which regressors would finally give me best model? So if my aim is purely prediction, then I should be interested in computing prediction error, and I should choose a model which gives me minimum prediction error. Now the problem is, again, if I compute prediction error on the basis of the same observations which I have used for fitting, that is not good. Because again, that is like testing only the memory kind of thing of the model, not the understanding of the model. So I need to have some sort of validation set, which I won't use by building my model, but I have Y responses for that data also. So once I have a model,
I will use that model to predict my response and then compute prediction error. That will give me first, okay, this is the best possible regression model. Then I might compare it with, so this was in multiple linear. I might do some transformation for either xi's or yi's and I might get another model. In that also I will choose in some sense best model. And then I'll compare performance of these models on the basis of the test set, which is third completely new data, where I could see which model is learning better. Okay. In fact, that's why we have the concept of cross validation also. So what we can do is, instead of simply reserving one subset as a validation set, we could give every observation a chance to be in the validation set. Why do I need that? Because we know in statistics, randomness is a key. So if I am unlucky, it may turn out that my validation set consists of only one type of observations and my training set consists of different types of observations. And then my results may not really be generalizable. So people came up with the concept of cross validation, or more generally k-fold cross validation, where what we will do is we will divide our data into k groups. Every time I will keep one group aside. I will fit the model on remaining k minus 1 groups. So suppose I have 100 observations and I am dividing the data into 5 groups. Then I will randomly choose 20 observations first. I will keep them aside. I will fit a model on 80 observations. Try to predict those 20 observations. I repeat this exercise again. Okay. Now, this is called as cross-validation. Is it completely a new concept? Did statisticians never think of that? No. Statisticians did think of that. We have something called as PRESS in classical regression set of prediction error sum of squares, which is actually equivalent to n-fold cross-validation. So basically we leave only one observation aside. It is also called as leave one out cross-validation, LOOCV. Okay. So statisticians did have this concept, but now because of the huge data, people are feeling the need to use it more often. And the second reason is, nowadays, many a times focus is more on prediction than on inference. What is the difference between prediction and inference? Prediction is getting the outcome right, whereas inference is understanding how I reached that outcome. As Vendreman was saying, neural networks are black box models. They don't tell me really how I reached that particular outcome. But many a times people are happy as long as the predictions are good. I don't really care how I reached there. Okay, so in that prediction type of setup where you value predictions more, test error, validation error have more importance than maybe the usual measures like R-square. Okay. So this is just a schematic. So you have original input data. You randomly select few parts of it. So some random observations, the green ones, they are now clubbed into a validation set. The red ones are now clubbed into a test set, and the remaining observations are in the training set. That randomness is important. Okay, you cannot say that, okay, I will take first 50 in my training set, because unless you are very sure that in that particular domain, first 50 don't show any special pattern compared to others, you cannot really take first 50. It's better to have things random. Now, what is there is no way I can do that. Okay. So then we realize that, okay, we need to first predict their votes and then rank them and then classify them. Okay. So there is no way I can do that. Okay. So then we realize that, okay, we need to first predict their votes and then rank them and then classify them. Okay. So So in case you missed the sentences, you got the reason. So if someone was yawning, sneezing, you got it back. Okay. Okay. So as I said, it is not really classification. I mean, the decision between classification and regression need not be black and white. We may have, it may be a judgment call in some sense. Okay. So yes. So we have, in the morning, you have gone through all these things: linear regression, logistic regression, and some of you might be familiar with Poisson regression. What I'm going to focus on squares remains the same, correct? So if I am here, then I will choose this point instead of this point, because that point is closer to origin. Okay, so I am in a sense shrinking my estimates and bringing them towards zero. Okay, so as I said, lasso and ridge both do this same stuff, just with absolute penalty or squared penalty. Okay, so this is one thing. This is the modification of our traditional regression, which can be used in a high dimensional setup. But as I said, there are other variants which we would like to study. So one of them is k-nearest neighbor regression. Pen drive. So what we have is k-nearest neighbor regression. So what is k-nearest neighbor regression? So in a regression model, in a linear regression model, there is major constraint that my model should be linear. And what are we trying to model? So our model actually says that the condition of y is a linear function of x. So I have expectation of y given the particular value of x as some beta naught plus beta 1 times that particular x. Okay. So basically, when I say that I am fitting a model, I am trying to estimate conditional expectation of y for a given value of x. Okay. But we are putting a constraint that my conditional expectation is linear. So if I don't want that constraint, then I have to go for, if I don't want any such. So k-nearest neighbor regression would give me one way of doing that. So what it would do? So what I am interested in is conditional expectation. I don't want to assume any model form. I don't want to assume any parametric form. Then how do I estimate some expectation? Generally in statistics, we know any expectation can be estimated or approximated by corresponding sample mean. Correct? Here I want conditional expectation. So conditional expectation of y I want. So I would need, in some sense, conditional sample mean. What do I mean by that? So for example, if I want a model for, say, height of children with respect to age, then for age 10, I need an estimate of height. Okay, so I need conditional estimate of height, given that the child is of age 10. So what do I do there? So I want sample estimate. So what I would do in my data, I would see how many children have age 10 years. I will consider all their heights, and then I will take average of only those heights. Okay, I will will take average of heights of all children who have age 10. So that would be my estimate of conditional mean given that age is 10. Everyone with me so far? This looks like a nice estimate, but the problem is if I'm unlucky, in fact, in most of the cases, I may not exactly have x equal to 10 and especially replicated readings. I might have 9 years, 8 months and then directly 10 years, 2 months. I may not have a kid who is exactly 10 years old. Then what do? Approximation. I go to the neighbors. So what I do is, okay, I don't have exactly x, but I will consider an acceptable neighborhood of x, and whoever is in that neighborhood, their yi's, I would consider as my sample, and I will consider sample mean. Okay. So next. Yes, one more step. See, for example, this is a relationship which is non-linear. So if I go to a linear model, it won't really give me a good approximation. So even a quadratic fit is not doing any good. So what I do is, I go, okay, so I want something for minus 5 mm, and I don't have exactly the data for minus 5 mm in my data set. So I'll consider a neighborhood. So I'll consider 3 closest point. For example, if I'm in 3 nearest neighbor setup, I will consider 3 closest points. So these points can give me good approximation for the point in which I am interested, and their sample average will be a good estimate of conditional expectation for my given x. Okay, so k nearest neighbor regression is simply that. So instead of modeling the conditional expectation as a linear function like in linear regression, now I am modeling it non-parametrically. So what I am doing is I am just approximating it by a sample mean, but not an entire sample, of course, because I want conditional. So I am taking everyone who is in some sense a neighbor. So we choose k by minimizing test error, etc., etc. So I choose that k, which gives me good predictions. Is it okay? So these are the advantages. It is non-parametric, it can capture non-linear patterns, and it has in some sense local nature. Whether local nature is an advantage or disadvantage, it's again open for debate. Now, next model that we have is a decision tree. So decision tree is a very intuitive model. It's actually how our thinking process works. The picture I have here is an actual tree, but what we fit is an inverted tree. Urdhva Mula Madhya Shakha. Okay, so the root will be at the top and the branches will be at the bottom when we fit it. So for example, you want to decide what to do on a weekend. Now there are first 2 possibilities. Are your parents visiting, assuming you don't live with your parents, are your parents visiting you on weekend? If yes, then they are not interested in doing anything else. So you just have to go watch a movie that they recommend. Okay. So one branch is yes, cinema. Done. Parents are not visiting, then your calendar is wide open. You have multiple possibilities, but then the climate is suppose a hindrance. Suppose you live in a country where climate actually matters, not in India. So you have 3 possibilities. The day is going to be sunny, rainy, or windy. If it's going to be a sunny day, then you would like to have some exercise. So you would like to go play tennis so that parents know, and then weather sunny, that branch lands up in the tennis leaf. If it's going to be rainy, then you cannot really go out. So you have to stay in, no choice. And if it's windy, then you cannot play tennis, it's windy, but you can go out and do something. Now what do? You want to either go for shopping or you want to watch a movie. Of course, depending on what day of the month it is. If it's near month end, then you don't have enough money with you. So you have to go watch a movie. But if it's just Aaj pehli tarikh hai, then go for shopping. Okay. So if you are rich, then go for shopping. If you are poor currently, then go for movie watching. Okay. So this is exactly how our thought process works, and this is exactly how a decision tree works. Okay. So what we do is we divide. So if I am in a bivariate setup, so I have one variable, let's say experience, other variable, let's say salary, then we divide that regressor space. I am making bivariate because I can show the pictures. Okay, in multivariate setup also it will get extended. We divide that regression space into many rectangular subsets. Basically, what do they represent? So this set would be x1 less than 10 and x2 less than 30. Correct? So these were sort of my dividing criteria in my tree. So every line I always have what is called as a binary split in a decision tree. So always yes, no. So this line represents left side x1 less than 10, yes. Right side x1 less than 10, no. This second line is again x2 less than 30, yes, no. So and if I add many criteria, for example, this x1 less than 10 can further get divided into say x1 less than 3, x1 more than 3. So these rectangles could get further subsetted, okay, as I increase complications of my model. Then what we do is finally, if suppose I am happy with just 3 rectangles, then for all the observations in that rectangle, I give average response as the prediction. So again, this is in some sense similar to k-nearest neighbor. The only difference here is there I was deciding the number of neighbors. How many neighbors I am considering to take the average of y. Here I am not deciding number of neighbors. I am letting my binary splits choose the neighbors. So basically everyone who lies in the same leaf node, so who has gone through the same binary splitting and landed up in the same leaf node, will be considered as neighbor. So one more. Yeah. See, for example, x1 less than 10, no. x2 less than 30, no. Then you land up in this node, the leftmost node. So anyone who lands up in your node becomes your neighbor. So your prediction depends on everyone in that node. Average of their values is the prediction. Can you see the similarity between k-nearest neighbors and decision tree? So again, here also I am trying to estimate the conditional expectation by, in some sense, a sample mean. But now, which sample I am considering? My sample consists of all those which land up in my node, my leaf node. Okay, so the end point is called as leaf node and the top thing is root node where everyone is together. Okay with this? Now, the problem is decision trees are intuitive, they're easy to understand, they give very nice intuition explanation, but the problem is they're very sensitive. They're not really robust. So if you change even a few data points, your predictions might change drastically. And as a result, their prediction power on a new data set, testing data set, is not that great. So people came up with many variants of them. One of the variants is called as bagging. So what is bagging? So bagging basically stands for bootstrap aggregating. Okay, so you do two things. You do bootstrap and you do aggregation. What do you mean by that? What is bootstrap? Bootstrap is basically a resampling technique. So I have one sample and I want multiple samples. Why do I want multiple samples? Can you just go one slide? Yeah. Why do I want multiple samples? See, as a statistician, all of us know that the variance of sample mean is much less than variance of individual observations. See, the first graph is histogram of individual observations. Then I have histogram of x bar when sample size is 5, then 15 and then 30. So we know that as my sample size increases, my distribution of sample mean becomes more and more concentrated. We study in BSc first year, variance of x bar is sigma square by n. So as n increases, my uncertainty decreases drastically, and I'm happy because I want predictions. I want to be certain about it. So if I could get in some sense an average prediction, then that would have less variability than single prediction back. So bagging actually works on that. Somehow I need average prediction. If I need average prediction, I first need multiple predictions. How do I get multiple predictions? I need multiple data sets. How do I get multiple data sets? I do bootstrap. I have single data set. I generate many samples of the same size from that data set with replacement. I do sampling with replacement because then only I can get distinct sample. Otherwise, I'll get exactly same sample. Okay. For every sample, I fit a model. Okay. So you can see here. So this is 1, 2, 3. So I get B such samples coming from my original data. For this sample, I fit a model and that model is suppose F1X. For this sample, I have f2x. For this sample, I have f, it should be capital B, f capital Bx. Okay. And so I have many predictions. Now for a new x, I can get prediction from this, everything. And I will take average over all these predictions as my final prediction. Okay. So individually, we saw that the tree is bad. So individually, every tree is a weak learner, but overall, it turns out to be a strong predictor. Okay. And as I said, the rationale is variance of this prediction will be much less. So the main problem that I had with trees was they are not robust. They are very sensitive to change in the data. But because now I have averaged them, that sensitivity is reduced and they become slightly more robust. And what we did for trees can in principle be done for any model. In fact, it can be done for even our usual regression setup. Okay, you can do bagging in regression also. Doesn't harm. Is it okay? So this is bagging. But when I explained this, there is a small problem. I mean, not in my explanation, but in applying it practically. So variance of x bar I said is sigma square by n, but that is true only when my xi's are independent. If the covariance, identical of course I am assuming, if the covariance comes into picture, then I can not be sure. Okay. And the problem is when I do bootstrapping, many of the observations will be common in the two bootstrap samples because everything is coming from the same data. So the models that I fit would be correlated and hence my predictions would be correlated. Okay. So this problem actually causes some decrease in accuracy. I mean, it doesn't give you as much increase as you would expect. Hence, people went for random forest. So what does random forest do? It is basically bagging, but with an additional constraint that I don't really use all the predictors in my model, because if I use all the predictors, then on every data, I might get almost similar model. So what do they do in random forest is, okay, when I'm choosing the predictor for the first split in a tree, so I want to decide the first split. So ideally, first split is decided on the basis of which is the best division in some sense. Best means it should give me good heterogeneous classes. Okay. Now, as I said, if I use all the predictors, then on almost every data, I would get almost similar division. So what we do in random forest is, suppose I have t different predictors. At every split, I first randomly choose m predictors out of p, purely randomly, nothing else. Okay, I completely randomly choose only m predictors, and then I will say, among these m, choose which one gives you the best. Don't use all p. Among the m predictors that I have randomly chosen, select the one which gives you best prediction, then do your division, then move ahead. At the next step, you have to again choose, so again randomly choose m and then do the prediction. So instead of using all predictors every time, we are going to randomly choose a subset of predictors and we are only using that. Because of that, what would happen is my models will be much more different than in the bagging scenario. And hence they would be less correlated. Is it okay? So, for example, if I am giving you a set of tools, okay, if we have multiple groups and if I give a set of tools, and I ask you to create some object. So I tell you the object also. So you want to create, suppose, a bullock cart out of it. Now, if I give exactly same set of tools, then it is quite likely that the final models that I get are almost the same. Whereas now what we are doing is, we are not giving same set of predictors every time. We are randomly choosing different set of predictors. So to one group, I give one set of objects. To other group, I give other set of objects. Then the models will look different. And then the correlatedness will decrease and my estimate will be, my prediction will be better. Okay, next. One more thing that I have is boosting. So boosting I'm introducing because in the afternoon, Professor Nair will be talking about XGBoost. So what is boosting? So boosting, again, the idea is same. You have many weak learners and you combine their predictions to get a strong model. So how does boosting work and how is it different from bagging? In bagging, what we did was every time we used a bootstrapped copy of the data and we fitted an entire model. Okay. Now in boosting, that's not what we do. And in bagging, every model was fitted kind of separately, okay, independently. Boosting is a sequential process. So can you just go one slide? No, next. Yes. So in boosting, what we do is, initially I start with a very small tree with just 2 branches. Okay, so a tree with just 2 branches, only one split, and I give prediction. Of course, I know that prediction is going to be bad, but I'm okay with it. Then I take residuals from that prediction. Residuals everyone knows, right? I take residuals from that prediction as my response, and I fit a new model, again a small model with just 2 branches to those residuals. And I go on doing this sequentially. So basically what I do is, initially I have a weak model which explains something. Then whatever is explained, I don't care about that. Whatever remains unexplained is in my residual. So I try to explain that part with a new tree. Again, I get something explained. The remaining part I try to explain again with a small tree and so on. Is it okay? So I have multiple trees. Every tree is small and they are sequential. Output of one is used to compute residuals, and those residuals are modeled by the next tree. So they are not parallel. They are sequential. And from each tree, we will get a part prediction, but ideally we could add all those predictions up, but we don't add all of them directly. We get a part prediction from them. So that eta there is called as learning rate, because people have mathematically proved that if the tree learns slow, then it learns better. We have all experienced it. Studying before the exam might give you marks, but it doesn't give you understanding. Whereas studying throughout the semester hopefully gives you better understanding. So a model which learns slow learns better. So that eta is the learning rate which controls the speed at which your model learns. So eta is generally 0.01 or 0.001, something like that. Okay, back. So what I have is, so initially we fit a tree with yi as response. Then next step we update the residuals. Okay, so I fit a tree, but then we compute residuals, and those residuals are used as response. Okay, those residuals are used as response, and finally I have final prediction as shrunken version of all the predictions, where that shrinking in diagram it was eta, here it is lambda because the sources are different, but assume n eta equal to lambda. So it is this. Okay. So this is boosting. This is basic gradient boosting, and then many versions are there, and in fact many of the Kaggle competitions are won by boosted models. Okay, but principle is this, that you build a tree sequentially, it learns slowly and hence it learns better, and because it is learning slowly, the chances of overfitting are also comparatively less. Next. Okay, then what I have next is support vector machines. Okay, so but before going to support vector machines, the idea comes again quite intuitively. So if I am lucky, suppose, so now I am in a classification setup. So I have to separate these blue dots from the pink dots. Okay, so I can have any line, for example, all these 3 lines separate the blue dots from the pink dots. So if I estimate equation for any of these lines via any method, because now we know line estimation in regression, then I'm happy. But the problem is, which of these 3 lines, and not just 3, there are infinitely many. Which of these infinitely many lines should I choose? Okay, so that I could get something like this. One class on this side, one class on this side. Next. So there is a concept called as maximal margin classifier. So what we do is, we try to find a line which is in some sense equidistant from both the classes, and that distance is as large as possible. Why do I want that? To avoid misclassification. If that line is closer to one class, then it's easy to misclassify. Here I want both misclassifications to be equally serious. So I try to put a line exactly in some sense at the middle, so that the chances of misclassification are less. Okay. So this part from what do you call this? Solid line to dotted dashed line. This part is called as margin. Okay, this is like a margin. It's a buffer kind of thing. There are no observations in that part. So you try to maximize that margin. Okay, hence it is called as maximal margin classifier. But of course, I am in a scenario where everything is very good. I may not get such a separation in real data. Okay, for example, here I have observations which are inside the margin, and I will have to allow for such violation if I have any hopes of modeling real data with it. So a modification of that became support vector classifier, where you allow some disturbances in the margin, and not just that, you allow for some misclassification also. Okay, for example, here this blue observation number 12 is on the opposite side. It should have been here in the blue class, but it is here. 11 should have been here. So support vector classifier allows for some violations of the margin and still tries to estimate a line which in some sense maximizes. So this estimation is again a regression kind of estimation. Okay, why? Because this is a straight line. So I'm basically trying to estimate a straight line which maximizes distances from the two classes. Okay, so in higher dimension it will be a hyperplane in that dimension. In 2D it is line, in higher dimension it will be a hyperplane. Okay, next. What to do if line is not enough? Okay, I can't be lucky to have a linear pattern everywhere. I might have something like this, but we have support vector machines which extend this idea to nonlinear. But you don't have to really learn very fancy nonlinear stuff. The thing is, you just increase your dimension. So if I want quadratic, just like we do in polynomial regression, I will say it is multiple regression with 1x and x square as my predictors. So I can still use all the linear regression theory, and I can still get the advantages of being quadratic. Exactly that is what support vector machines do. Okay, in that sense, the kernel idea in support vector machine is similar to your polynomial regression. So what they introduce is something called as kernel function, which can take care of higher powers of regressors or interactions between the regressors. I could have a product term x1, x2 in it. I could have a x1 square, x3 in it. Okay, so all these can be taken care of via what are known as kernel functions. So basically you try to increase the dimension. So even though I have only 2 regressors, if I want quadratic, I will call it as 1x, x square, 3 regressors. I'm assuming intercept as a regressor. So 1x, x square. Okay. So you increase the dimension. In that dimension, it becomes linear and you get what you want. Okay. So that is support vector machines. And the last one that I would like to talk about is fancy stuff, deep learning, artificial neural network. So basically everyone knows it tries to mimic human brain. Artificial neural network is also at its heart a regression problem. Okay, in fact, there is something exactly similar in statistics called as projection pursuit regression, which is nothing but an artificial neural network type of thing. So what I have is, okay, I have these xi's and I have a y. I want to reach from these xi's to y. Linear regression model is not doing the trick. What do? I complicate stuff. How do I complicate stuff? Instead of directly feeding xi's in a model, I first get some complicated functions of xi's. I start calling them AIs. Then I get some more complicated function of AIs and I try to model it as Y. Okay. So I have equations here in case you like to see equations. So what I do is, so can you see this is actually similar to regression. The only difference is instead of x, I have some function of x. Okay. That function of x, hkx, is actually the activation function. So that could be some weighted, again, that x is a vector. So it could come from all the xi's. So this is a linear function of xi's first. Then you apply some function to that linear function. That becomes your h. And that h you input as a regressor in your final model. So basically you have two non-linear kind of functions in between. And other than that, it's a linear regression. Okay, so what is the difference is instead of having xi's directly as regressors, you have some complicated functions of xi's and regressors, and you allow every AI to have a different functional form. That's actually the beauty of it. That's actually what makes it flexible. Okay, you allow all these AIs to have their own forms. Okay, because the coefficients get estimated in the process, and finally we don't understand anything. That's a different story, but it does give prediction. It's a black box because it estimates so many functions, so many weights that we can't understand. But because of so many weights, it becomes flexible and it gives the predictions that we desire. Okay, so next. So I think that's all. Thank you. If anyone has any doubts, please raise your hands. In the interest of time, we won't take doubts because you all must be hungry. We have one more lecture before lunch. So thank you, Akanshana. We now invite Professor Ramanathan to introduce us to high-dimensional data.
Good afternoon. So, just reminded of one thing. In 2012, there was an Indian Science Congress I was attending, and I was supposed to give an invited talk. So the session was going on. Professor Rahul Mukherjee was chairing the session. And then, every speaker sort of, took more time. And finally, there were only 4 minutes left. So and I was the final speaker. What I did, I went to the presentation. I opened this is my title, and I look at the last slide. Thank you. No, I'm not sure this. Actually, I did like Rahul Mukherjee was laughing. I was like, oh, Rahul, you did a good job. Because hardly any people were sitting there. So I can do that. Of course, it was not an online thing. Yeah, so now let me come to that. I'll try to wind up the thing as early as possible so that I don't want to stand between you and that. Yeah, now, of course, I'll cut down a few things, what I'm supposed to. Can I have the first slide? So basically, I start with this. If you are asked to, if you are asked to say shape game and then put them according to shape based on a shape grouping, that you will do the left hand side. And if you are asked to do it according to the color, then you will do that other one, right? Now, suppose if I bring more things into that, then the life is more complex. Okay, so 2 features. You could actually, but then there is a problem. I mean, I'm not actually worried about the takeaway from that. But what I'm trying to say that when you bring more and more feature into that, the things have become more complex. And that's where many a time happens in the real data sets. In fact, Akansha was also talking in the morning also, most of the speakers mentioned about that. Vendriman was talking about logistic regression, and she was talking about how to estimate those parameters. Now, imagine the case, she was just handling with a one predictor age. Suppose I have 100 predictors or maybe 200 predictors, and then if you are running a regression, then you can see the problem that you face, because many a time this iterated reweighted least square uses an inverse of the matrix, and then you will have a real problem over there. Why is the real problem over there? Because if you have more number of predictors than the number of observations, then the simple linear algebra theory tells you that the inverse and all will be in trouble, and your least square estimators is like x prime x inverse x prime y. So that's where the actual problem starts, and that's where the high dimensional issue starts. Okay, so yeah, next slide. Yeah, so this kind of things were not there when statistics started. I mean, statistics started, what I mean is in the 20th century, where all the statistic theory sort of developed. Because people, as I told in the morning, that data were very scarce, very costly. So most of the methodology were developed for fixed number of features and fixed number of dimensions, where all the time you have more observations. Try to make sure that you have more observations than the number of parameters that you have or the number of dimensions that you have, so that things were developed in a much better fashion. But once you are in this era of technology, you might have experienced just now. I want to have live stream. I want to have a presentation. I want to have this to be sort of Zoom working on that, and then the trouble starts. Naturally, because you want several features, want to bring it together, and that's what exactly happened.
Isn't it? I mean that, so half an hour we lost. So this is what exactly happened when you try to bring in more features into the picture. So new source of data that search for RFID, like radio frequency identification, sensors, which collect a huge amount of data, like sensors from satellite thing. Even nowadays, cars have insurance based on your way of your driving. How it is known to the car, the insurance company? Basically, the sensors are put in the car that how you accelerate, how you change, how you change the lane frequently. I hope not in Pune. So for such data, traditional ideas, so what happened to traditional mathematical ideas of testing hypothesis or confidence intervals is not going to help. That's where the problem actually we have with the high dimension. Next slide, please. So there are some of the examples. Actually, there are so many examples. One can look at that because I just prepared this for a financial talk. So I just put those examples. We can find it in any area. So, like for example, if you want to integrate a lot of things, being some financial background, you want to integrate macroeconomic banking, monetary and financial data, huge insights, large number of predictors. Recently, we have been hearing decisions. And then there is a bank failure in US. All this can spill out to various different countries and various different markets, and then they have to be prepared for that. And if you really want to have such kind of data to be analyzed, the kind of features that you have is humongous. Large number of features. Another thing is risk management, which almost all, I think, Vijay Marapan was also talking about banks giving credit. Banks giving credit, based on the loan. So there is a lot of risk involved. How do you decide this risk? So there are different types of risk. So basically, these are where modeling is vector auto regression. That simple auto regression that all of us may be knowing, like xt equal to some pi xt minus 1 plus epsilon t, which we even learn in the undergraduate class, where fast observations can actually add some with an error. But now think of the situation where this xt is a vector. If xt is a vector, then that phi has to be a matrix. And that matrix means that so many parameters. And if there is a lag of p, you see, all the p coefficients are matrices. How many parameters? So that's where, now another problem that you face when you have so many parameters, every time you estimate a parameter, you're adding another error to that. So accumulation of errors. So these are some of the issues that we face. This is there in a simple example. Like if you are if you are basically a investment banker, and then you have a kind of portfolio with 1,000 assets, and if you have 1,000 assets, and if you want to study them naturally with the past data, maybe in a year or 2 years or 5 years, you see that leads to most of the risk management is dealing with various matrix, and 1,000 by 1,000 matrix. 1,000 by 1,000 matrix is because it is symmetric. Half side only we require. So it is 1,000 into 1,000 plus 1 by 2, about 500 million parameters. So I have to estimate about 500,000 parameters. And then if you have 2-year data, and then it's about 200, 500 and some days where you have observation about this particular financial company or what. So what I'm trying to say, the situation is quite natural. This was not the case earlier, where such kind of dimension has increased. So portfolio risk optimization is one of such issues, and of course market microstructure duration modeling, where you have high frequency data. Well, there rather than dimension is one issue, but you also have numbers also is another issue in the high frequency data. We had actually done a project also. We have a PhD recently 2 years back completed on this topic. So I'm not getting into details. Let's move to the next slide. There is one important result. Bellman. Those who have done optimization, they may be knowing Bellman's optimal dynamic programming. And dynamic programming, if you have learned dynamic programming, you know Bellman. So Bellman has another thing, what is called curse of dimensionality. So what it basically tells you that in an optimization, if you must minimize a function f, of D variable, and we know that if that function is ellipsis, then we need to have the order of 1 by epsilon to the power of D evaluations on a grid in order to approximate the minimizer with an error epsilon. I'm not giving the proof at all, which you can actually find it in internet. So what essentially happens is that if you are asking for a good approximation, which means small epsilon with a high dimension, you see that how many how many ordering that you require to have that comparison. So that's what the curse of dimensionality is basically. So if your D increases, it really creates problems. Next slide, please. Yeah. Okay. Now I want to actually. This is Bellman is actually a optimization manager mathematician. So you can see that the application actually starts with the theory in mathematics. And now you see, if you consider the same thing what Akansha was telling just now, that if you don't want to assume a parametric model, consider non-parametric regression. So non-parametric regression is something like xi1 is equal to f of that functional equation. And then you want to now fit a function. I mean, like you don't want to have parameterize that, and you want to actually estimate f. And then suppose you consider, just assume that your f is a ellipsis function. And then if you try to estimate f, and then there is a result which is proved by a famous book, Ibrahimov and Kosminski. You can see that supremum of f belongs to that this theta. Theta is the class of all functions where it is assumed to be ellipsis. I'm not assuming that it is a parametric function. Simply say that the nature of the function. So it's like if you consider that, you can see that the lower bound of that is something like c n to the power of minus 2 upon 2 plus d. This is used to sort of, we do in statistics what we call determination of sample size. So we wanted to know for a given epsilon how much sample size that we need. But if you look at that very carefully, that actually depends on the dimension, because you can see that the sample size increases as the dimension d increases. So that's where these are another problem. So this is actually the curse of dimensionality in the case of non-parametric. Next slide, please. There are some blessing also, like you can get some good mathematical behavior in the high dimensional case. Because if you don't know anything, then you can say everything looks good, isn't it? That's roughly the translation. So this is like a theoretical benefit due to probability theory. The regularity of having many identical dimensions over which one can average is a fundamental to something like a stationarity. Okay, next slide, please. So I'm just explaining that little bit, what is called as a concentration measure. So the concentration measure of a phenomenon is about probabilities on product spaces of high dimension. And again, I assume that f is a function in the d-dimensional space, and then let p be the uniform distribution on the sphere Rg, and let x be a random variable with the probability measure. Then you can have, well, you might have seen this kind of a thing, what is called Markov. So you can see that fx minus expectation of fx can be bounded with that, and then now you see C1, C2 are constant independent of f and dimension d. So now what it means that it behaves almost like a constant, the Lipschitz function in that particular. Of course, we have treated this random, so don't just confuse it with the real, the function generally that I'm talking about random. So in other words, the Lipschitz function is almost like, because we can sum this with the finite things, that this behaves like a constant, almost surely. Next slide, please. Another use is that we can obtain, so I'll come to this slide a little later because I have another one which is connecting the dimension n and the connecting p, the number sample size n and the p. So at that time I will explain this. Next slide, please. This we can skip, let's skip this. But if I skip this, then I may not be able to skip this. Well, basically, see what is happening is that when you have some complex processes or complex, can we go back? Let me explain. Some high dimensional data arises because underlying objects are really in a continuous space or continuous phenomena. So there is an underlying curve or image that we are sampling, such as functional data or image processing. I think one of the speakers were talking about, Khatri sir only, he was talking about the X-rays or even ECGs. So you can see that these are functions, and then try to, as the measured curves are continuous, there is an underlying compactness to the space of observed data, which will be reflected by approximate finite dimensionality and an increasing simplicity of analysis for large D. Well, we are using a lot of conceptual mathematics, idea of compactness and all, try to see that whether that is going to help in the high dimensionality. So that's what basically this all about. I can immediately apply this to a simple example in statistics, where you, next one please, consider a Brownian bridge, and then Brownian bridge is of course, if you don't know Brownian bridge, think that a Brownian motion or a Gaussian process, and then tie down to 0, 1. Okay, instead of considering that. So tie down to 0, 1, that's called the Brownian bridge. So if we have a d-dimensional data, xid is b I upon d, and then suppose we are interested in maximum of this, maximum of y xid. So what happened that obviously you know that this tends to this kind of a thing for large d. So here we know, so we are still in a functional setup, but then some theorems actually in statistics help us to have a control of that. You can use the maximum t belongs to 0, 1 bt using the ideas of Kolmogorov-Smirnov that we can actually use. So what I'm trying to say that even if d is larger, there are some advantages also in these kinds of setups that you can actually bring into this kind of theorems or this kind of results. It's possible to apply. Next slide, please. Yeah, so basically, I won't be touching on anything on computational right now. I'll be saying more on statistical. So high dimensionality brings noise. The three things that it brings: noise accumulation, which I already told you. When you have more number of parameters, when you estimate them, more and more noise gets added. That's one thing. A second thing can happen is spurious correlation, in the sense that when you have more features or more data or more dimension is there, what can happen is that there can be, we may think that there some of them are correlated, but actually they may not be correlated, or vice versa. Okay, so spurious correlation can be there. Another problem that you may face, what is called as incidental endogeneity. This endogeneity is something which is very serious. Now, perhaps nobody stressed that in today's talk, even though we have regression, various types of regression discussed. Like, for example, can the epsilon depends on those predictors? That epsilon depends in the sense that statistically depend on x. So we always assume that they are independent. So if that, but you know, this was true when we were collecting data in a very nice manner. But now that data is actually accumulated, and you really don't have a control on any of them. So there is possibility that you can have epsilon need not be independent of the x that you are taking, which is very strong assumption. Which of course econometricians are very careful about this endogeneity. So they have a lot of theory on exogenity and endogeneity. But however, statisticians were not worried about this thing for quite some time. But now they started worrying because it's all big data, high dimensional data. They have to be really worried about it. So that's where incidental endogeneity. Incidental in the sense that because you really don't know whether it is there. Because you are mixing all the data from various sources, it can happen. Okay, next one, please. Yeah, so this is what I think I mentioned all these things. Basically, we need to dimension reduction and variable selection to address noise accumulation issues, need for high dimensional classification, new regularization method, need to tackle spurious correlation. And so these are the basically what I mentioned are the theoretical development on what statisticians or probabilists have been doing in the context of data science. Because you may wonder that data science is only the kind of computer application. No, that is one side of it, where you try to come up with the algorithm and implement it as Akansha was telling, maybe it is a black box. But behind that, you need to have strong theoretical underpinning, because when you have high dimension, many statistical techniques which we have right now will not simply work. So that's where we need to develop a lot of things. So of course, these are all pretty new. I mean, last maybe 10 years, because we never We are not used to it. Statisticians are never used to such kind of phenomenon. So we slowly start thinking, what happens if P greater than or equal to N? Where P is the features or the dimension, and then you have more features than the number of observations, and then start addressing problems one by one. So need to tackle incidental heterogeneity unrelated covariates may be instantly correlated with the residual noise, creates biases and model selection. Can we go to the next one? Yeah. Yeah, I think I'll go to the next one. There is not much in this. Yeah, I'll just give, these are some of the examples now to show you that how this is actually arising. So for example, well, if any of you have a difficulty in just understanding the notation, please raise your hands. So basically what I have is, I have a p-variate normal with the mu naught. IP means identity matrix of order P, so that you can see that they are all independent normality. So uncorrelated. Similarly, in NP mu1 IP, where P is 4,500, mu naught is equal to 0. Now, mu1, we are saying it's like with the probability 0 with the probability 0.98, and it's a double exponential, standard double exponential. Standard double exponential will be moving around 0 only, but it can have larger value because it's more, tails. So it's double exponential with probability 0.02. And now most components have no discrimination power. Now what happened, even then some components are very powerful in classification. So of course 2% of that is 4,500, that is about 90 realization from double exponential. And then let's look at a distance based classifier. So I'll consider a distance based classifier, which is given like this, where beta is given minus mu naught. And then, well, we know we all learn in multivariate analysis what is the probability of misclassification under the normality setup. It's very easy to calculate. So if you do that, you can see that the probability of misclassification turns out this is the cumulative CDF of normal distribution, standard normal. So you get something like this, and if you choose this for these chosen values, you can see that this is approximately 9.48, which means that C of minus 9.48 and then P of minus 9.48 is very close to 0, right? So this is like when we estimate beta. Now what happened that this phenomena get affected when we estimate beta, because right now I just given the value, but if you estimate beta, it's not necessary that it will classify in this way. So the resulting classification rule behaves like random guess due to accumulation of noise, because my beta is of dimension 4,500. So you are estimating that, then the error is huge, and that's where actually the problem starts, and it affects how it's going to affect your classification. So when you have high dimension, you need to be really careful about that. Next slide, please. So next slide is basically a demonstration of this. For example, if I consider x1 x to xn and y1 y2 yn, which is from mu1 and mu2, and then classify z to one of these populations. Take p is equal to 1000 and n equal to 100, mu1 equal to 0. So mu2 is the first 10 entries of values 3 and all other entries are 0. Well, I did not go for a double exponential now, but arbitrarily taken it as 3 and rest of the values are 0. Now, if you try to plot the principal components using the first 2 or 40 or 200 and 100 features, 1000 features, so you can see that the discriminatory power get lost by the time you reach maybe around 40 or 200. Of course, with more than that, you really can't even discriminate. So when m equal to 40, the accumulated signals compensate the accumulated noise, so that the first two principal components still have reasonably good discriminatory power. But when m equal to 200, the accumulated noise exceeds the signal, so that need for sparse model in high dimensional classification. That actually shows. Next slide shows the picture of that. So now you see this, the one is for 2, 40, 200 and 1000. You see that you are unable to actually classify when you go for higher features. Next slide, please. So a feature of high dimensional variable that are not, now this is what, yeah, I have 5 minutes. Yeah, we have spurious correlation. Now this next, what I'm going to do is basically try to say the similar problem that happens in the case of high dimensional data as regards spurious correlation. Now, spurious correlation means we really may not have, even if you take correlation to zero, but when you start estimating, you can see that that shows concentrate somewhere away from zero. Okay, that's what the problem happens. So that leads to false scientific discoveries and wrong statistical inference, and then impact on variable selection. Variance will be seriously underestimated, bias will be very large, etc. These are some of the consequences of the spurious correlation. Go to the next slide. Yeah. So here, what happens that this example is taken from Fan, Han, and New. So basically, there are a sample of size 60 and 3-dimensional. Population correlation between any two is zero because we have IP, which is a identity matrix. Now, in this case, suppose you compute this small r and capital R. So small r is like the maximum of the sample correlation and maximum of the multiple correlations. That's what is given here. And R hat is nothing but the correlation between x1 and its best linear predictor that you know that using this particular x's. So suppose we simulate this data for p equal to 800 and p equal to 6,400 for 1,000 times. Next slide, please. So now you can see that where it is concentrated. This is for the red is for 800 and blue is for 6,400. You see that actually it should be concentrating around zero, isn't it? Because your correlation is zero. You have IP, which is because all covariances are zero, and you are in a normal setup, so the correlation is zero. But you see where when you have d equal to 6,400, you go and sit here. So where this is 0.5. So this is what the problem with the high dimension. So you can see that, and that's with this. This is with maximum absolute correlation, and that's with maximum absolute. Maximum absolute correlation. I think the title is wrong. The one is with the small r, and the other one is with the capital R. So that's what it is. Next slide, please. I think this we can skip because this is actually a continuation of the whatever I just mentioned. Skip. Yeah. Now I will not go through the detail, but I'll tell you what is actually there. Basically, what happened that what I shown you is how this is affecting the correlations. But not only correlations, it can affect the entire inference also. So basically, what will happen is that if you are estimating the variance, if you are trying to estimate the variance in this particular context, the variance estimate is given by this, or to make a particular thing, something like this. So the variance is getting inflated by this amount, and ideally this should be concentrated around zero, but that is not the case. So if you take the distribution of this gamma n, you can see that it actually creates a problem and actually away from that. And that's what, so sigma square is underestimated by a factor gamma n square. So basically, you know, most of our estimation and all, you have sigma square estimate, whether it is standard kind of procedures. And if you are not doing a good estimate of that, your confidence interval, everything is shaky. So that's what happens in this particular case. Next slide, please. Yeah, so this is what the picture of that, how it move away from zero, which is basically the distribution of that gamma n. So gamma n should be ideally concentrated around zero, but that's not what happens. So you can actually, various choices, you can see that for different choices of p. These slides will be put on our workshop website, so you can have a look at that, close look at that. Next slide, please. Yeah, so I'll spend just 1 minute on endogeneity. So endogeneity, I told you, is another issue that one need to tackle because you can have a relationship or a statistical relationship between the error and the x, and then that's what can happen. So you see, this is what the usual assumption that we make in the usual. So nobody even mentioned that in our linear regression class, but actually that is something which is very serious. And when you have data accumulated from various sources, especially in big data, etc., or the current way of collecting the data, this cannot be guaranteed, and that makes every estimate even inconsistent. In fact, there is a paper in Annals which prove that even penalized estimators in this particular case is failed to be, of course, a particular type, failed to be inconsistent. So next slide, please. Yeah, so endogeneity causes endogeneity causes the inconsistency of penalized least square method and possible. Once your estimator is wrong, you are actually saying false scientific, advice to people, because basically it is based on the beta. Like somebody asked, what is the interpretation of beta to Benjamin? If your beta is wrongly estimated, somebody who may be living for under 10 years, if the beta, the wrong interpretation is given, you say the odds ratio. It's wrong, isn't it? So you have to be really careful. So those estimations of beta has to be really proper in such case. So the consequence is endogeneity causes inconsistency and penalized least square method and possible false scientific discovery. Now these are about parameter estimates and the sigma square. You can also have problem with suppose there is another issue, like I was talking about the variance covariance matrix. Suppose you want to estimate the variance covariance matrix when you have large dimension. Now we may think that, oh no, we have a wonderful theory which shows that sample variance covariance matrix estimate. And sample variance covariance is a very good candidate in this context. I can show you that when your dimension increases, that fellow is totally useless. Actually, absolutely useless. I have go to the slides below. In fact, below endogeneity, I just skip. I want to skip all these things. Skip further. Maybe you can just go to the last 2-3 slides. I think that's where you can see the last. Yeah, I skipped all. Yeah, it's here. It's here. Just previous. See here. This is what. So we consider that the usual estimator, which is in the class we prove that you have AMD, everything is very good. I mean, like the estimate of the variance covariance. Now I'm talking about matrix, not a scalar variance, because we have dimension is larger. So we are talking about variance S, the sample variance covariance matrix. And if you consider this simulation, now if you see the ijth element of that ER is basically the norm of that, and then you just ER ij square equal to 1 to etc. p. Next slide, please. So you can see that where does this concentrate? For a simulation sample size 200, you can see that it actually, if your p is 100, it goes and sit here actually. This is where the concentration. In the case of 5, in the case of 50, and in the case of 100, which is much away from this. This is actually the difference. I'm not estimating S. I'm finding the difference between S and sigma inverse. So that's what it is. So you see, it has to be 0, but it is far away from that because this is a dimension create problem over there. So that's what happens as dimension increases. This is actually go away from that. So what it shows that the usual S estimate is not a good candidate, and S is required everywhere. For example, the portfolio optimization problem. To calculate the risk, what do you require? The sample variance covariance matrix. So you require sample variance covariance matrix, and if you can't estimate them properly, then you have it actually, because you will be giving wrong advice. You cannot give a wrong advice, especially when you are in a financial domain. So it's worth millions of dollars. Okay, so that's where you need to have different methods of estimation for S, and that's one area which people have actually contributed substantially. One of our students also did a PhD from Michigan on the same topic, Professor Paul. I think 2008 batch. His topic was how to estimate the variance matrix and then apply automation learning problems. So we can see that, of course, how to estimate is not just one question, because there are various methods. In fact, I have one slide. Can you go to one slide where some data or some numbers are there? Go below, go below. Last but one. These are I'm discussing 4 different methods. Here, yeah. So here, these are some of the. If you look at, don't worry about the name. There are some different types of estimators for S. Just understand that. And if you look at the sample covariance matrix and the realized risk is like mean square error kind of a thing. And if you can see that this risk is more for the sample covariance matrix as compared to any other method that what we have actually considered. So this is basically a comparison. This was done by MSc projects. This calculation. So this is where you have much better estimates. And problem I already discussed with you that what can contribute. I mean, if you wrongly estimate S, what kind of problem that you're going to face? Because if you are giving advice to in a financial sector, then your risk is not calculated properly. And if you know what will happen if your risk is not calculated. So risk is related to the variance covariance matrix, and if you don't estimate them, and this problem basically comes in high dimensional scores. I think I'm stopping at this point. You can go to the last slide. Thank you. Yeah, okay. This may be useful to some of you. There are 3 books which I mentioned. Yeah, this there is one more, right? Yeah, this is by Wainwright, and then the another one is I think yeah, this is Christopher Girard, and there is one more. Yeah, this is Goldman. This was the old book actually, 2002 or something. The Girard book came in 2019. So maybe if anybody is interested, you can look into that. In fact, we can find a lot of information. But it will be really mathematical, highly involved when you are in the high dimension. Yeah, thank you. Do you have any questions? Or you can shoot me a mail anytime, because after seeing the slide, we think that what this he was telling may not be correct. Yes, I would like to suggest. I think another solution is for higher dimensional data. If we take alternated statistic, I am sure that there is no relationship between the variables. There is no correlation between the variables. These will be all independent. These variables will be all independent. Just you use alternated statistic. It is published by Leone and Costa. That is in the finite dimension. No, it will go. It may be used. You cannot make a orthogonal transformation when you have a infinite dimension. No, but it may be used. I am just this is my suggestion. We are actually like see all your quality control problems are in finite dimension. It is not related to the particular. What happens that in the real application, the problem is that this V is quite large, and then coming up with of course, that way we have learned first thing that we learn how to write the density of the normal. How do you do that? You actually make a transformation and then start writing like this. I don't know how this starts. And we were doing MSc. We start with that and then make a transformation of that and then start writing the quantitative. So orthogonal transformation is one thing that one can do. But what happens in these kinds of situations? It's pretty difficult to come up with that. That's what I will try for that. For alternative, I will try for that. Yeah, okay. So what I was talking is like if you have any kind of difficulties after going through this, this could be available on the workshop website. Please read them very carefully when you go back, and then please send mail.
So much, sir. We'll now be having a lunch break. Lunch is provided outside the department on the left side.
Please try to be back by 2 so that we can make up for the last time.
I'm going to be making a prayer, skipping some slides and only focusing on the bigger topics. Okay. If you have any questions that are more clarification questions, please do raise your hands and ask me. Not sure how we're going to handle the people who are online. But if you have any deep philosophical questions or questions that challenge me, then let's hold them to the end. I gave this talk at Cochin on Friday, Cochin University of Science and Technology, and one of the participants, they started challenging about why is machine learning useful. You know, it's just essentially claiming that it was a lot of nonsense in machine learning. So how do you answer a question like that? So I'm not going to try to answer questions like that, but please do hold off at the end and we'll have a good conversation. All right. This doesn't seem to be working. Can you hear me? Is it working? Okay. So this is the outline for the first part of the presentation. There are not very many actual worked out examples. I have one case study, illustrated case study, that I'll talk about towards the end, the second part of the module. So most of this is introductions and then talking about what the algorithms are, how they're trained, what are the architectures, for example. So let me just everybody has these slides. Yeah. Okay. So if these references that I've put here, there are two of them that I think are very general. The first one is a paper written by my colleagues and myself. Supervised machine learning. It is really it's an overview and applications for banking. Some of the material is taken from there. Please take a look at this article that appeared in the International Statistical Review. Now, if anybody has any trouble downloading it, I can give you a link to archive, and you can get the paper from program. The second one is a very interesting paper by one of the big giants in this field, is Leo Breiman. Leo Breiman was a professor at Berkeley, He got his PhD in probability. He's written a very well-known probability book, and then he became an applied statistician. And toward his later years, he became a machine learning person, right? And that's a good article that talks about the two cultures of modeling. One is what we used to do in statistics, and the second one is what the machine learners do. And I'll touch on that briefly. Then we have several, the middle ones all talk about introduction. The original papers on the algorithms, random forest introduced by Leo Breiman, who was at Berkeley, is not with us anymore. Jerry Friedman talked about gradient boosting machine. He's at Stanford, retired at Stanford. And then the next few, there is the last one is a book on deep learning, which is really based on neural networks, right? So I don't really know, once you have gone to deep learning, what is there to do? Everything is deep learning, right? So it seems like everything else we do is shallow learning, right? All statisticians. So we should try to come up with something deeper than deep. Okay, so let me start with some introductions about the terms, or at least my introductions. The term machine learning and the terms machine learning and artificial intelligence are used interchangeably by all. And that's simply wrong, because machine learning and artificial intelligence are two different things. Machine learning is a set of tools that allow you to do some tasks. And often these tasks are part of artificial intelligence, right? So the term itself was coined by a man called Arthur Samuel, who was in IBM in around the late 1950s. I like this second definition here. study and construction of algorithms that can learn from data, identify features. Now, what has happened to me is that as you get older, you get all kinds of ailments. And I had my cataract surgery done. And so what the doctor did was I made my eyesight. Oh, so I can barely make up your face. So let me try to wear my glasses. So study and construction of algorithms that can learn from data, identify features, recognize patterns, make predictions, and take actions. There's a lot of stuff, all right? But most of them are aimed at a particular task. Okay? And we'll see some of these tasks, right? So I think called supervised learning, unsupervised learning, and things of that nature. Okay. Now, machine learning is one of the key pathways to accomplishing goals of artificial intelligence. Now, artificial intelligence itself is much, much broader, right? Now, the canonical example that I think for us to really anchor our ideas on is autonomous driving. Think about a car driving by itself. What are the different tasks involved in this? It's not a single task, right? And what are the different things you have to do? You have to collect tremendous amounts of data about the things that an automobile will see, right? Traffic patterns, stop signs, other vehicles, turning left, turning right, okay? A cat, and an animal, and a human being crossing the road. All of these things are data that go into training an autonomous driving scheme. Right? And then once you have this data, you're going to analyze it to recognize patterns. You've got to recognize a human being, a child, a stop sign, a school sign. All of these things need to be recognized and in real time, and actions have to be taken depending on what those things are, right? So there are a whole bunch of things that go into that, right? Optimization, right? Pattern recognition, decision making, something called reinforcement learning, right? That forces the algorithm to make real times in practice. Think about the simple thing, right? Here, I can never get it right because I was born in Malaysia and I lived in the US. I don't know whether to turn right or left. But one of those stop signs when you come to the road, you're going to make a decision, okay? T-junction, turn right, okay? That is another car. If it is a machine and a machine, it's very easy to make a decision because the machine, one machine tells the other one, hey, I can do this, right? So I get right away. But suppose a machine and a human being, who decides? It's a conflict, right? Okay. So if you're a human being, how do you drive? If you're a passive driver, you just wait and wait. An aggressive driver, you try to see move, and there's a game that goes on, right? But how does the machine handle that, right? So those are the kinds of things that goes into artificial intelligence, a whole bunch of things in order to do some major tasks. Similarly, things like, for example, in medicine, suppose you are actually going to rely on an algorithm and robots to do surgery, for example. Think about all the things that happens, right? So there are a whole bunch of things that go into artificial intelligence. It has, the area, of course, was really dominated by philosophers. For a long time, people asked, human beings can think. And are there any other animals, other living things, or even non-living things like machines? Can they think like human beings? What does that really mean, right? So this has been a stuff of long history, reasoning and philosophy, logic, and so on. AI itself has had what people call several winters. So the ideas came up, the latest version of AI algorithms came up in the, can't hear me? Good. Is this on? Okay, this is not working. Both are okay. There's no interference. Okay, so AI, artificial intelligence as we know it, using neural networks, started off again in the 1940s. For one reason or another, people decided, well, it's too much, too hard. Everything that they were promising won't work, right? So they've gone to what's called AI winters, where the whole idea of AI is came up. What's happened recently is the so-called deep learning of neural networks, with very, very complicated processing machines, if you will. And they have really led to a resurgence of artificial intelligence in many, many different things, right? The most recent example that we all have heard about is chatbot, right? Okay, GPT, right? Everybody is now thinks that problem of speech has been solved, right? Unfortunately, I'm going to be sweating, but I'm okay with that. But it's a little bit wrong. So, and ChatGPT is trained on a network called GPT, right? That is a transformer network. And it's trained on very large language models. And there are literally billions of hyperparameters. Billions of hyperparameters. This time? Can this one be turned on? It's awesome. Thank you. Okay. So, when you have an algorithm with billions of parameters, what does it really mean? It's just kind of amazing to people like me, right? But that's not going to go there. Okay. So, as I said, there are many supervised, many machine learning tasks. I'm going to focus on what's called supervised learning. And for the purposes of statisticians and data scientists, it's nothing more than regression and classification. So what you have is your data, you have label Y, and then you have independent variables, covariates, predictors, whatever we call them, X's. And so the Y's and X's are associated with some training data. And we use the training data to train our algorithms to figure out what is the relation between Y and X. Let's call it F of X. And then when a future point comes, X comes in, we just apply the F function, we get F hat of X. That's our prediction. So almost all predictions. And I'm not going to talk about the others in red. So let me now talk a little bit about these two paradigms or two cultures that Leo Breiman talked about. So this was an article that received a lot of attention among statisticians and data scientists and machine learning people, created some controversy. Leo Breiman, who was at Berkeley, actually, when he gave this talk at Stanford, which is about 2 hours down south of the Bay, there were a lot of people who got upset at him because he was particularly trying to be provocative. So he claimed, sometimes if you have a message, you have to be provocative. So what he basically said is the following. All these years, we as statisticians have been focusing on what I call here traditional statistics. In traditional statistics, you have some underlying population. Okay, it can be a real population like in a sample survey, or it could be a hypothetical population, like, for example, I'm interested in contamination in a river and the water flowing, and I can think about some population about which I'm going to take a visual inference. So I got a sample. I take a sample, and all of your professors will teach you this thing called IID, independent, identically distributed. It doesn't exist. There's no such thing as IID. Okay? So they're fooling you. Ask for your tuition back. Okay? Ask for your money. There is no such thing as IID, but we all live in a hypothetical world where we pretend, and these professors like Ram, he spent 4 years of reserve work, and he decided it was too hard, really. So he decided to come to the university and teach you that and trick you into believing there are such things like IID. Okay, so we have a sample that is somehow representative of the population, and I want to use the sample to make some conclusions about the population. Okay, in particular, I want to know how was the model generated. Are there some underlying, is the input-output relationship between the axis and the Y is linear, quadratic, are there interactions, all kinds of things, right? And over the years, going back to people, our founders like Carl Pearson, Neyman, Fisher Neyman, all of those, we developed an extensive set of models and tools and diagnostics, right? To draw this inference. There is a hypothetical population. There is a population. I'll take a sample and I want to draw conclusions. Okay. Now, machine learning people, what happened in the machine learning community, right? Machine learning community dominated by computer scientists, starting on the 80s, they were collecting data because they had access to computers. And there were computers, there were all kinds of data repositories, collecting data and all of that. And they were scratching their head. What am I going to do with this data? Now, statisticians, and I put myself in that group, right? I went to one of the most theoretical schools in the US, Berkeley. There was not a single regression class, by the way, when I was taking statistics. Okay, no regression. So statisticians said, somebody will collect the data and give it to me. They might even clean the data and give me some pristine RID data that I can go do. I can do whatever I want. Nobody's doing that, right? Computer scientists said, I have this data, what do I do with it? They're not modelers. They don't think about how the data was generated, why it was generated. So I have this data. What do I do with it? Let me throw some algorithms. Okay? And what are the algorithms? They're all mostly prediction problems. Okay? Prediction problems. Like what? Think about Amazon. You buy a book. Okay? You buy one book. They make a recommendation to you based on your patterns. This you might like this. Right? It's called recommendations. Okay? You go to a store. You buy milk. So the store might want to know, people who buy milk, most of the time, what else do they buy? If you buy diapers for kids, they might want to put diapers next to it. If you buy beer, they might want to put beer. This was called association mining. In the 1990s, run by a man called Rakesh Agrawal, started this area called association mining. It was the beginnings of the term data mining in the 1990s. And that's when people started using terms like data. Okay. So what they said was, I have data, I want to make some sense of it, right? And they said, let me predict this, let me predict that, and all of that stuff, right? After they were started to predict elections, and they started to predict weather, and one of the things that at the same time, what was happening was lots and lots of data were becoming available, right? For example, you're driving a car. The car has sensors, right? And your car goes over a pothole. Your sensor detects that, sends the message, information to somebody. That this particular location, there is a pothole, right? Another one, you are going in, you're stuck in traffic. Signals are being sent to all the other cars, there are traffic jams, right? So the automobiles are not really mechanical systems that they used to be. They're much more electronic systems, all talking to each other, okay? Biosurveillance is another example, right? Biosurveillance is people wanted to know very early on, before some flu hit, is there going to be an onset of flu? So what do? They track what kind of medicines people are buying in pharmacies. They're buying mostly flu medications. That sends a signal. So these are early warning systems, right? So these are the ways you can take social media data or other kinds of data and use that to come up with early warning systems, detection, prediction, and so on, right? In the US, if you get fired, unemployed, you've got to file for something called unemployment insurance, okay? And it takes 6 months from the time you submit it, right? Of course, you lose your job, takes you a month and a half to submit it. By the time the government figures out what is the unemployment patterns, it's 6 months too late. Okay, so what can you do? My colleagues in Michigan, they actually were tracking social media. Okay, Twitters. Through Twitters, look to see what are the things that are going on. Fire. Increase in layouts, right? Because these data are not very clean. To take these kinds of billions of tweets and clean it out and make a decision is going to be very, very challenging. Not only that, keep in mind, statisticians or data scientists, whatever you call yourself, they are very much interested in estimating things very well. Well, no bias, no, almost no bias, no variance. With these kinds of social media data, you cannot estimate this very well because there is bias, tremendous amounts of bias. People who use social media data are not typical of other people, right? So all you can do is you can estimate trends going up and going down. You cannot estimate the actual levels of something very well. But that's the price you pay for doing early warning systems. Okay. So that is really what machine learning people focused on. And what they said is, I don't have any hypothetical population out there. Okay? That you guys can imagine that if you want, but there is no such thing. What I have is a set of data. I'm going to take the data set, I'm going to split it into one piece called test data set. I'm going to hold that out. I'm going to hold it out. And I have a bigger piece called training data. I'm going to train my algorithms on that data set. When you train an algorithm on that data set, it's going to overfit. That's the nature of the beast. Okay. But now I look at it, how well does my algorithm do on the test data set? So it's training test paradigm is what they have settled on, unlike confidence intervals, hypothesis testing, under some assumptions of whether normality or sample limit, very little of that happens. Now, one thing that Anil reminded me yesterday was the following. These kinds of machine learning tasks are typically used with moderate size data, 10,000, 50,000, 100,000. Sometimes you will get millions of observations, right? Millions of observations. So if I make a prediction, P hat, probability of something going wrong, probability of default, P hat of X, and I have a million observations, what is the standard error? What is the uncertainty associated with P hat of X? Anybody wants to take a guess? If it is binomial, right? If it's just simple binomial, variance is what? P times 1 minus P over N, right? Correct? But this is not binomial. So, the actual variance would be much larger, but let's think about that. P times 1 minus P over N. That's the variance. But if N is 1 million, 5 million, how big is that? P times 1 minus P over N. Very tiny, right? Very tiny. So you can claim that I pretty much know everything, so I don't need inference. That's one way of looking at it, right? But the reality is much more complicated. That's because P times 1 minus P over N based on what? Independent identity distributions. Your data are never independent identity distributed. They're very heterogeneous. Okay? Think about this. I don't know how it is here, but in the US, they invariably get the population, the president's election prediction wrong. Invariably get it wrong. Why? Because the theory suggests to me, if I have 20,000 sample size, 20,000, I should get it well. The reason because the population is dynamic, it's changing. There is no such thing as a constant P, right? And the other thing is what people don't tell you. You go and ask them what is you're going to vote. Some people say, I'm going to vote for Trump, but it's very highly unpopular. So I'm not going to tell you. So I will say something else, right? So that's the problem. The kind of variations that we as statisticians are concerned about is under the set of assumptions. That set of assumptions never hold. Never, never, never. So that's why that variability you get is really an underestimate. It is what called statistical uncertainty under some models, okay? But there are all kinds of other things that are happening, okay? In particular, the model is changing over time, right? Data are also changing over time, right? So, but nevertheless, the point I want to emphasize is the uncertainty that one has to worry about in machine learning is not the uncertainty about the data, the variance. Uncertainty is about all the other things that are going wrong. Okay, that's really very, very hard to quantify. That's really why you still have to worry about uncertainty. Okay, as usual, I'm taking a long. Ram, you need to give me some 20-minute warning before the first one, okay? So let me talk about applications in banking, right? Which is an area that goes to my own heart for the last 6-7 years. So what we do basically, typically is there are two kinds of activities that goes on in banks. One major one that is handled by banks like JP Morgan, which is the largest, JP Morgan and Chase, largest bank in the US, this is what's called investment banking, right? They do the investment banking and they trade. They basically trade, they have to look at options and derivatives and commodity pricing, interest rates, all of that stuff. They're interested in those kinds of models, okay? Now there, you have some data, but not a lot, right? So they use mathematical models, partial differential equations. They write down very complicated equations. God knows if they're correct or not, but they do. They say server purposes. They continue to do that, okay? And you all have heard about things like Black-Scholes and formulas and all of this, right? So that's one area. And then there's another area which is more data centric. And that's really the area that my bank, Wells Fargo, is big in. And most of that has to do with customers coming in and opening accounts, checking accounts, savings account, mortgages, taking loans of various types, right? And then when you take a mortgage loan, the bank will take that loan and package it and sell it to somebody, but they'll still service. So they can serve money there, they take one cent on the dollar or something. Okay. So there are lots of things, and most of them are what we call loan products. Okay, mortgages, home mortgages. When you buy a home in the US, most of them go to a bank and borrow money. Right? That's typical. Young people don't have it, right? You buy a car, you get a loan. Credit cards, small business loans. Even big companies, they want to build a factory, build a mall, they borrow money, hundreds of millions of dollars, right? Banks will get together and give this one. So that's really the biggest part of the banks that the data center areas. So credit risk. Credit risk says we have trillions of dollars out there, trillions in loans to people. Now, how much money are we going to lose over the next quarter, second quarter, third quarter, right? Because people who don't pay off the loan, that's a loss. Even if people pay off the loan, not just not pay or default, even if people pay off the loan, we lose revenue, right? So customers not repaying debts or loans. The second thing in big area is credit decisions. You apply for a loan, one of the many loans, right? Credit card, that's it. Somebody has to decide whether you're going to be a good risk or bad risk. And there has to be a decision made regarding that. That's called credit decisions, or sometimes called credit scoring. That's a term. Okay. Then, of course, a whole bunch of things, revenues, transactions, various kinds of payments that banks make money. Another big area is financial crimes. Okay, fraud. You'll be amazed at the amount of fraud that goes on in banks. Okay, credit card fraud is a big deal. There are a lot of people out there trying to set up accounts and steal your accounts and make your money, right? And I'm going to skip file ending. A new area that has come up is called text and speech, right? So text data, right? Text data is data that is communicated by email, or customers call the banks, they talk to our agents, they transcribe, they write these things down and they transcribe it and then they submit it, right? So the things that we're interested in is, are customers happy? Are customers complaining? If they're complaining, what are they complaining about? So those are the kinds of things that we need to do in reasonably real time. So within the last 6 years or so, the so-called text analytics or text analysis has become a very big area in machine learning, right? Now, speech and voice recognition systems have been around for a long time, okay? Big places like IBM and when I used to work at Bell, they've been doing speech and voice recognition, for example. You know about all kinds of speech recognition systems. And similarly, chatbots. We have chatbots now, like Siri and Alexa, which you talk, it recognizes what you're saying, and then sends it someplace. tries to retrieve that information, right? But if it doesn't recognize it, what you say, then it sends you to somebody to talk, right? So a whole bunch of things like that. So all of those things have become very important. And one of the big areas in my team and also in the quant area is modeling text data using language models, like you hear about ChatGPT, and then using that to automatically classify them as complaints, with the complaints, what kind of things. Okay. Now, on the left-hand side, the traditional techniques that I have written down, statistical and econometric techniques. Now, one of the nice things about machine learning people these days is they're very generous. Anything you did 150 years ago called linear regression, they call it machine learning. Everything is machine. They're very generous. Come to me. Join my family. Machine learning, right? So that really irks the heck out of me. Even some of my team members who are not statisticians, they call it linear regression, right? But in my terminology, machine learning is a class of non-parametric techniques. And I would put 4 of them in that category. Support vector machines, which I'm not going to talk about. Ensemble learning algorithms, which consists of random forest and boosting, and neural networks. Those are the 4 things that I would talk about, right? But there are a whole bunch of other neural networks, autoencoders, variational encoders, a whole bunch of things that I'm not going to talk about, right? Because this is just a 3-hour presentation. Now, the other thing that I should mention is that the computing landscape has changed, right? It used to be everybody in this area was using SAS, which is a big company in North Carolina. My daughter used to work in that company. But now people, and then there was R, but R does have a lot of machine learning capabilities. But now people are moving into Python, a lot of open source libraries. And what is the real action in this space is really algorithms. The techniques themselves are not that big. What is the action is coming up with very fast algorithms, okay? And along with that goes infrastructure, like what people call TensorFlow, PyTorch, and all of this. And some of you have heard about GPUs, graphical processing units, that are developed by a company called NVIDIA in Taiwanese company that's not very big. So it is very, very important that you have the right computing infrastructure. You want to be able to do a lot of machine. I've mentioned natural language processing already. So some of the techniques are summarizing text, translating from one language to another, chatbots or what people call conversational AI, classification, sentiment analysis. These are just some of the examples of what happens in natural language processing. Okay. So what is happening in machine learning and why just the big hullabaloo? What is so exciting, right? One of the things is the so-called big data movement, what that it made lots and lots and lots of new sources of data available to us, right? Social media data, right? Sensor networks, things, machines talking to machines, cars talking to other cars, right? So lots and lots of data available. And our traditional algorithms in SAS and others don't scale up. They die when you have like 10,000 and 20 billions. They don't move. So our algorithms do not scale. Okay. That's one of the things, right? And then there are also this whole area of text data, for example. Very, very large scale image analysis. Okay, looking at recognizing images, especially dynamic images, right? And also large models like text data, right? Statistical algorithms are very simple. They cannot handle this. So in comes neural networks and so-called deep learning, right? The deep neural networks. They were really, really very good at analyzing and extracting information. So the machine learning things that I'm going to be talking about are not on that scale of huge image analysis, huge pattern recognition problems, right? I'm talking about data, say, million observations, 10 million, at most 100 million observations in our case, right? And almost all of them are time series. All time series. responses will be typically univariate, binary, or continuous. They can be multivariate, but usually people analyze multivariate data, so response of one. So these are problems in which we can use random forest, that's boosting, rate boosting, and simple feed-forward derivatives. And that's all I'm going to be talking about. And handling time series predictors, very, very long. Because modeling a time series data over time, and it goes back to 20 years, as long as the account has been around, and it can be daily or even monthly or weekly. That's a long time series. So you need to be able to summarize that time series. There are lots of techniques in the statistical literature, but they're not good enough. So machine learning algorithms have come up with what's called automated feature recognition. It's a fancy word of saying summarizing time series and extracting features that are very good in summarizing and modeling the data. But that's really one of the areas. All right. So I have a lot of other things that I've covered in okay, so let me now jump into this area of structured data. And so we have n observations, p covariates, they can be static, time series, repeated measurements, or what have you, right? So in examples, for example, in banking, transactions over time, deposits, withdrawals, right? And loans, and then you get whether you get a loan or not, or whether you default, you don't default. So a whole bunch of data of that type, right? And I'm going to actually I'm going to skip a lot of the slides because you had these summaries this morning, right? So we have responses that are either continuous, or binary, or multinomial, right? What we are interested in is modeling expected value of some function of that, which M is a type of x, and G is often called a ring function. We are interested in estimating f of x if it is parametric, or you're interested in prediction. And so you want to do this, given a set of data, you want to find the predictor that minimizes some loss function, right? The loss functions can be on the right hand side with continuous responses, binary responses. Okay, so these are all things that you're either familiar with or you heard a review this morning. Okay. Now, one of the big things that we have to be careful about in fitting machine learning algorithms, which are in some general sense nothing more than non-parametric functions, or non-parametric estimation. So what is non-parametric estimation? Non-parametric estimation is really, when we talk about non-parametric, let's talk about its parametric. Parametric means that I have an input-output relationship, f of x, f, the shape of f is known. So it can be linear, 1x plus beta 2 x1 plus beta 2 x2 plus beta 3 x3. I don't know the betas, but the shape is linear. Okay. Parametric says the function f is quite arbitrary. Can be anything you want. Okay. And that's really what we want to estimate. Okay. And we want to estimate that without making any assumptions. That is makes it non-parametric. Non-parametric estimation is not new in statistics. Okay. What is new is really the particular architectures that have made the estimation fast, the algorithm very fast, right? And scalable and dealing with lots and lots of things. And we're going to be, so one of the things that happens when you are dealing with non-parametric estimation is you can very easily overfit the data, especially the data set is small, right? Because you can actually find a function that goes through every point. Right? That point fits perfectly, but it's of no use. It's not a model. That's a function fitting. You got to separate between a function fitting and a model. A model must not be able to fit everything perfect. Because when you extrapolate it, then it's of no use, right? So what happens is, as the model becomes more and more complex, the bias red curve goes down, but your variance will go up. The model will become more and more unstable. So what you want is some kind of a point where there is, the bias there is trade-off, right? That's really what you want. Okay. So in this region, you're underfitting the model. In this region, you're overfitting the model. Suppose you want to be operating here. And that's the $100 million question. How do I do it? Right? That's why we do lots of different things, like, for example, regularization. Okay? You all are probably familiar with regularization. Regularization says if I have some function or loss function, my predictors, my y, and I may have some data. I want to minimize this, but I'm going to minimize it subject to some penalty. I'm going to pay a price. This function should not be too arbitrary. We have some kind of, I should penalize the complexity. The more complexities, the more penalty I'm going to pay, right? So you penalize by having a penalty function, and then the lambda is what's called a tuning parameter, right? And you tune this parameter, make it big, this becomes big, the penalty is too big. Small, the penalty is too little, so you have to find some kind of compromise. Okay? And there are different kinds of penalties that people have developed over years. The first one is called either ridge regression. In the old days, it's called L2 penalty. L1 is sometimes called lasso, from my tips Ronnie and Stanford. But L0, by the way, is the first one, which says I want to be able to figure out, look at the number of variables in the model. Theta J is the coefficient. And I'm going to say my model should be no more than K variables, right? But it turns out that is computationally very hard problem, right? It's NP hard. So people have actually approximated that by this, but now there are more and more algorithms that can do L0. All right, so I'm going to skip all these. So one class of models, we call them semi-parametric models because they're not fully non-parametric. Because once you specify the number of splines, it becomes a parameter. Okay? Spline is a term that came up in applied math. It's a sort of a flexible way of fitting a function. And there are different kinds of splines, linear splines, truncated power splines like cubic splines, B-splines. These are all ways of approximating a function. You can use these as the basis function, and any arbitrary function can be approximated by a linear combination. Okay. So these have been around since the 1960s, actually, due to people in applied math, but also a lady called Grace Warner, who was very well known. And that theory has been developed, but it turns out it is not as good as the machine learning algorithms that we talked about. Okay. And then there is another class of models called additive models, like Hasty and Tiptrani, that basically says, I'm going to take a function approximated by additive functions. This one depends on the next one, x2, x3. There are no interactions. It's an assumption that there is no interactions, but the f itself can be estimated. Right? So this was developed by Hasty and Tiptrani in the 1980s. Okay. But I'm going to be using this particular class of model called regression trees. Okay, they are going to be fundamental to two classes of machine learning algorithms. A regression tree, it was called classification of regression tree, popularized by Bryman and company. But it was actually called, Anil, I don't know if you know this, it was developed actually in Michigan by the sociologist Morgan and Sanders. It's called automatic interaction detection. So the guy Morgan, when I was at Michigan, would come to this talk and sit next to me and say, complain all the time. I don't make credit to us. We did this long time ago. So what that is, in this context is, what you do is that you have a set of data, right? Let's take a look at this, 4,000 observations. I'm going to look at all possible covariates, predictors, and I'm going to start splitting according to these predictors. And I want to find a split that makes the inside the node variation as homogeneous as possible. So you're trying to, there's a lot of variation here. Let me find the first split. Okay, so in this case, I'm going to split, you're going to look at all possible splits and how do you reduce that, make it manageable is a hard problem. So I'm not going to talk about that, right? But let's suppose you said, I'm going to split on x1, less than 3, bigger than 3. So I get these 1,500 observations here, 2,500 observations. So this will be within sample variation, will be less than that. Now I'm going to start looking at where to split this. I'm going to split this at x2, and I stop This one, I might split again on x1 less than 4, x1 bigger than 4, I must stop. Okay. Now that's what you do. Now, once you've done this splitting, how do you estimate the model? Inside each node, you fit by an average. You take all the observations here, you compute y bar. And if these are proportions p 0 and 1, you take p bar, right? So every node is estimated by a simple mean. Okay, and that's what you see here, right? So it's a split these things into 1, 2, 3, 4 regions. And each region, the estimate is just a simple mean. So it's called piecewise constant regression. Okay, and what you will see right now is everything we do is going to be built on this, on top of this. Okay, right? It turns out you can fit more complicated models inside, which we have done, but that's really not what people do in the business. All right. Okay. Let me. I'm supposed to stop at 3:30. Yeah. No chance. Try my best. Okay. Any questions before I jump into this algorithms? Yeah.
So in the advantage section, you have written that it is robust to outliers and predators, right? And disadvantage, you have written that it has high bias for shallow trees. How does that work?
High bias for shallow. Okay. Robust to outliers and prediction, all that means is that it's piecewise constant. Observations that are very large would get the average value. Why? No, but I'll tell you what. But let's focus on my first point. You got that one, right? I'm taking a big area, right? And I'm replacing observations by extreme. You can argue, well, mean is not so robust. I can replace it by mean. This one says the following: high bias. A good question. So it's a piecewise constant model, right? So, but suppose my relationship is linear. Okay, right? How is it going to approximate a linear relationship? It's going to cut it, right? But if I only depth of 2, I'm going to cut it only 2. That's a bad approximation, right? So linear is not good. Even quadratic is not good, right? But if it's piecewise constant, it's good. But piecewise constant is an attempt to approximate any function by like this, right? So there are many of them I can do. So deep trees have low bias. Shallow trees have high bias. Okay, in the traditional way of doing modeling, what do? We have a set of data, right? A sample that we call it. And then I'm going to fit a model to that data set, right? I'm going to fit a model, right? A model could be linear regression, logistic regression, Poisson regression, whatever, right? And that could have parameters, whatever. So then I have a fitted model, right? A FAT, beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 and all that, right? That's my fitted model, correct? And then I can do whatever this, I can look at the standard errors, p-values, whatever, I can do model selection. But after all of that, I've arrived at a model. Then I have this f hat, and you come in, and you are applying for a loan, and you're going to give me your attributes. You say, this is my income, this is my savings, right? This is how much money I'm going to put into buying a house, a car, all of that, okay? I have a model, right? So I'm going to say, plug it in, and I'm going to get my y hat. That's my prediction. What is my prediction in this case? Is the probability that you will default. Probability that you will not pay back. If it is low, you get the loan. If it is high, you don't get the loan. Right? That's how we operate, right? One set of data, we go. What happens in this ensemble algorithm, the term ensemble means it's a collection of tools and I'm going to combine them, right? Collection of techniques, I'm going to combine them, and I'm going to talk about some of them. So you take the original data set, from there you create multiple data sets. And I'll talk about how these data sets are created, okay? Different algorithms create the data set differently, okay? So I'm going to create one data set, and then I'm going to develop a model. I'm going to create another data set, another model, another data set, another model. So many of them, okay? Now, it turns out, most of the time, these fitted models here are trees. These piecewise constant trees. These are usually the fitted models. You can ask yourself, why don't I fit anything else? It turns out there's no reason to fit very complicated models. You can actually take these simple models and combine them to get good answers, right? Okay, so you create many of these models, which are piecewise constant regression trees, and you somehow combine them to create the combined model somehow. Okay, and I'm going to talk to you about what that somehow means. Right? So then you have a model, H, which is a combination of these individual models. Now, Anil comes in and applies for a load. I look at it, plug it in here, and create my prediction. Okay, and my prediction is high probability default because he's retired. There's no money. So anyway, but think about this for a second. This model itself can be complicated, right? If you do splines, you do things. But when I combine them, they're impossible. And that's why machine learning is hard. Interpreting machine learning is a college. It's become very, very, very okay. Because I'm getting ahead. So let me just give you an example, right? Oh, I skipped the slide. Random forest. Random forest is a technique that was originally proposed by Ryman. And the idea is as follows. Oh, I know what it is. It's not my latest slide. It's the old slide. That's why I was having a disconnect there. What happens if the slides are not in order? But this is the old one, right? So so what you do here is you have an original data set, right? Now you take a bootstrap sample. So let's suppose I have 100,000 rows, right? Each row is an observation, an account, and there are covariates, right? So I now select these rows, sample them with replacement. That's what Bootstrap does. Bootstrap samples the rows with replacement. So from this 100,000, I might take 50,000. Some of them may be repeated because I'm doing something. Okay, and then I get another Bootstrap sample, another Bootstrap sample, right? Okay, and for each sample, I fit this piecewise constant regression tree. Correct? Now, all I do is I take the average of those trees. Okay? Average. And that's my final. Now, each tree is easy to see. But when I take 100 of those trees, take the average, it's very hard. Because we don't really know, the observations can fall in different partitions, different segments. So it's hard to, right? But what is the rationale? The rationale is, as I said, the original trees, I was responding to you, the shallow trees are biased. But what people typically do is they grow deep. Okay, for a single tree, you try to grow deep because you don't want too much bias. But deep trees are good because they take care of the bias. They are unstable. You shake them a little bit, the trees change. Change the data a little bit, the trees will drastically change. Very, very unstable underlying. So what do? This is why Brahman came up with the idea. Let me grow many deep trees and take average. But the average is much more stable, right? It makes sense, right? For statisticians, it should make sense, right? So the trees, average trees, on the average, they give you a more stable prediction. But of course, the price to pay is incomprehensible. Don't understand what the heck it's doing. It uses some number, but you have no idea what. Okay. And then there are many examples, many hyperparameters. How many trees should I have? How deep should the trees be? How many minimum sample size in each node? All of these things are considered hyperparameters, and you can tune. Okay, and I'll talk about tuning. Yeah.
What are the other choices for pitch?
Pitch?
What are the other choices than variability?
Oh, what you can do is, in the case, this is the case for regression, continuous regression, but you also do what's called pick the winner. In the case of binary responses, you pick how many maximum number of times something happens. But this without number of choices. Okay, I'm going to now talk about boosting. Boosting is a different algorithm, also based on trees, and it's also called an ensemble. This idea of boosting actually came out in Bell Labs by a man called Shapiro, a computer science person. And the idea was different. Idea was, let me start off with what people call a bad or poor algorithm. I'm not going to pay much attention to the algorithm. A simple algorithm is start, right? Can I do something repeatedly to improve the algorithm so that it gets great? That's called boosting. So the idea is, can I somehow reduce the errors by doing something in order to improve the performance? The term people use in the area of machine learning is weak learners and strong learners. Okay? Weak learners, you start out with some simple algorithm, keep on boosting it to get a strong. Right. So it was there is a technical other boosting, adaptive boosting, that was developed by Shapiro, who was at Bell Labs, like at Princeton, and a student from Yale Farm. Then Bryman in 1998 came along and said, look, this boosting that you guys in the science are doing is nothing more than gradient optimization. It's just an optimization. It looks like boosting. It's a fancy term, but it's nothing than an optimization algorithm. It's gradient descent. That's what he showed. So once that was established, the connection with gradient descent was established, Jerry Friedman came along and came up with a new algorithm that, because AdaBoost was only for categorical responses, binary responses, and he did something general, extend the concept with gradient boosting. So it's a general way of minimizing a loss function. So for example, you have continuous response, square error loss for regression, or deviance for binary classification. Then what you really want is you want to find an algorithm that minimizes the loss, and it does that sequentially. Let me just show you here how it works. You take the original data set, okay? You first of all, you fit the overall mean. This is very similar to what we do in regression and analysis of variance, right? We always say, look, the model has to be better than the overall mean. So I'm going to fit the overall mean, take that. Then I'm going to work with the reciprocals. Okay? Overall mean is comfort free. Okay? So that's right. So I'm going to take the overall mean, remove it, right? So you fit the overall mean. And then you take the residuals, right? Yi minus f and naught, the residuals, right? And then what you do is you take this residual to fit a tree model, piecewise consequent regression. Okay, hoping that that would actually improve. It will look for the structure in the residuals, take out at least some of the structure. Okay. Now I call this I have one. I'll have to combine the two and then look at another set of residuals and fit another tree model and keep on going. So essentially, what you're doing is you're taking the residuals right? And you're saying, look, the residuals, let me look for any structure on the residual by fitting repeated models. And then I'm going to start reducing the residuals and start improving that. That's really going from a weak learner to a strong, right? I haven't really tied this to boosting, gradient descent or derivatives, right? But I can paint you. Now, once you've done this, what you do is that your final model is original mean plus a weighted combination of these guys. That's it. Not an average anymore, but it's a fitted linear combination. Okay? And that is the gradient boosted model. Okay, and what you're doing here is nothing more than solving the original problem, minimizing the loss function through gradient descent. It's just an algorithm to actually achieve that optimization. So there are lots of questions here, right? What type of parameters, right? Type of parameters. How many trees? How deep should I have these trees, right? And then learning rate. Right? Minimum number of leaves for a leaf tree, right? A whole bunch. Then there are a whole bunch of implementations that I'm talking about soon. There are a lot of libraries. Scikit-learn, for example, is an open source Python library. If you haven't used it, it should be a good learn. Okay, that's really right. Everything. Pretty much everything. Okay. Right. R also has a GBM package for. And then there are some variations of implementation. It turns out the original variation that Jerry Friedman came up with wasn't very fast. Okay, he's a folk. The guy codes in Fortran. He's older than me. Codes in Fortran. And people look at the code and say, oh my God, who wrote this? Okay. But it works. But then a lot of other people come and clean up the code and done much better implementation. Okay. The most common one is XBoost, extreme gradient boosting, right? And then there's live GBM and cat boost. So I'm going to skip all these slides, right? So a whole bunch of things that talks about. By the way, they also do they optimize it with some penalty to regularize. Regularization is a big thing in machine learning. You don't regularize it, it'll overfit the training data like crazy and will not do well. Okay. So regularization of various forms is the key. And we have to take credit for it, right? Do you know when ridge regression came up? Not before you guys were born. 1974. Okay. Developed by 2 people in a chemical. Not even studies. Okay, I'm going to skip all this. Then I'm going to now take a few minutes to talk about neural networks. Okay, and I'm not going to go into deep the machinery of neural networks because it's very, very complicated to explain the inner guts of neural networks beyond it. Okay, that's why I think like that. I was telling Anya yesterday. You know, I'm an ancient man. You can see that. Right? I'm a dinosaur. So why do I still work? I have a team of young people like you who just graduated. Okay, they come and teach me everything I know. Everything I know, I've learned from them. Of course, you know, because I'm old and wise, somebody comes and tells me, I think so, but we can improve it here, right? But I also, one person comes and tells me, I learned from them, and I tell the other guy, why don't you try that? No, but it's fun. I have a lab, you know, like a university research lab. And I have almost 40 people. I don't have to get them money. I don't have to get them grants. They are fully paid, you know. And it's nothing like that, I tell you. It's absolutely wonderful. That's the ideal job. And we get them a job. Okay, so I've learned a lot. I've learned absolutely a lot. I've learned in the last 6 years a lot more than I've ever learned in my any 6-year period, including PhD in my graduate school. Okay, that's a lot of fun, right? And this area, by the way, there is a lot of promise There's a lot of hoopla. There is a lot of stuff people say and exaggerate. Going through that, figuring out what is the right thing, what is not the right thing, not the right thing is the fun stuff. Really, really fun stuff. Okay. So as I mentioned earlier, right, neural networks, the recent incarnation of neural networks started around 1940s. People were trying to say, can we understand how the brain functions? And let's try to come up with some algorithms that would mimic how the brain functions. Okay. As you can imagine, that didn't go anywhere, right? I want to tell a little story. My son did his undergraduate in neuroscience. Okay. So I said, hey, do you want to do a PhD in neuroscience? And he said, look, Dad, these guys don't even know how a fish brain works. Okay. Now they're talking about modeling a human brain. They don't know anything. So what did he do? He became a doctor. And then he didn't like being a doctor either. But anyway, you know, the problem with a human brain, of course, is very, very difficult. And nobody really knows. But still, I think we should applaud them for the attempt. So they were trying to model how the brain works, and there are lots and lots of different attempts. And the latest way, the visual explanation of a neural networks is following, right? This is a very, very simple, low-level, right? So you have, let's say, a neuron in the brain. The neuron fires if neighboring connected neurons fire, and they feed something. Okay? That's activate. They activate these. So let's think about this in our data set of inputs x1, x2, x3. They get combined, you weight the W1, W2, W3, they come in here, right? And then that's Z, weighted combination, Z. And then there is what's called an activation function. Okay? If G of Z, you take the Z, you apply something, and if the threshold is higher than some level, that neuron fires. If it doesn't, that neuron doesn't. Okay, I've told you 110% of what I know. But basically that's true, right? So now on a neural network, and I'm showing you what's called a feed-forward neural network, where everything goes forward. Right? And this is nothing more than this in many layers and many layers. So your input, this could be 100,000, 200,000 X's, right? X1, X. I'm sorry. 100 X's. Like each X1 is a predictor, right? Like income, unemployment, right? So you know, many of them. And each one of them goes into these neurons inside. Each one is a linear combination. And then you apply a function G, and then you get an output S. But each one, then you know, it's all possible combinations. And then same thing, it gets all of these inputs from here. You apply another function G, and it is higher than threshold fires. Ultimately, there are many such layers and many such neurons, and you get it back. Okay. The inside of this looks very complex, right? Very, very complex. Now, this G function, there are many choices. That's what it's called something called a symbolic function. Looks like an exponential logistic function. Hyperbolic tan. Value is values as the rectified linear units. It's just a hockey stick function. It's 0 and then it goes up. Where it goes up depends. You know, it depends. Right? Now, if you look at this, right? If you look at G, what goes in Z, W1, X1, W2, right? That's just nothing more than a what? A linear function. So that's called an additive one. It's called an additive index, right? And some of you may have heard the term projection pursuit. Projection pursuit was developed a long time ago. So that's a really simple model, right? What you're doing here is taking linear combinations, applying an application, and you're doing it repeatedly. And every neuron is connected to every neuron network. Okay? And so-called hyperparameters, how many neurons, how many layers, and how long do I train, and a whole bunch of very complicated parameters. Right? Okay, learning rate, number of layers, neurons, regularization, batch size, and all of this. That's what happens to neuron. Okay? Now, the hard part of the neural network is weights. What you do typically is you want to optimize the network to get the best neural network, because what you really want is you want to get a y hat minus y so that the error is small. Correct? So what people typically do is you have the inputs, initialize the inputs, take these W's to be random. You randomly choose these inputs. You propagate these data through here, and you get a y hat. Look at y minus y hat. That's typically very large. Right? So what you do is that now you compute the derivatives of these errors with respect to the weights. Okay? And then you optimize them by going like this. That algorithm is called back propagation of errors. And then you keep on it, right? Until you get something better. Now you can do other ways of optimization, but it turns out this was a simple way of using computing the overall whatever using chain rule, right? That's what they came up with. Yeah.
Question. So, is there a theoretical condition that guarantees that y will be linear combinations of x's?
Y will not be linear combination of x's because G is not linear.
So, so effectively you're predicting y f of x is the G of G, which is a linear combination. G is a linear combination of x.
Now, this is a linear combination, right? But that's not.
Yeah, but my question is there a guarantee that a simple linear combination would just work?
No. I don't want to guarantee, but that's just linear question. Superposition of linear functions become. But what happens is the following. I do want to, what you said is actually has a sense of correctness. And let me tell you what that is. So if you take something called rectified linear, right? The G there, it's not linear, but it'll be 0 and then different types of things. So what this would do is it takes the Y and it takes the X space and partitions them in very complicated ways. Okay? Remember, it's a partition of this type, right? So that's an oblique partition, right? Oblique partition, right? W1 x1 plus W2 x2 plus W3 like this, like this. So what it ends up doing is taking taking the x's, breaking them into very complicated partitions, and inside each partition, fitting it by a linear mode. So it's piecewise linear, but it is not total. So people have tried to say, well, this was linear model, like I interpreted and so on, but it's not. Yes. Say that again.
You are proposing, you just said that, I mean, as you said that we are using the back proposition to optimize the model.
Back proposition.
That means we are optimizing the weights, right?
Optimizing?
Are we optimizing the weights or are we fixing the weights because of that back proposition?
Fixing what?
The weights.
No. The whole idea there is to find the right weights.
Right weights, right. But then in gradient boosting, we are talking about weights again. We are having a model where rho were the weights. In gradient boosting, we had that linear model only where rho were the weights.
Which way?
Here. Rho m is the weight.
Rho.
So is there any specific pattern for rows that as the residuals get older, the rows will be bigger?
Yes. Rho gets smaller. And actually that is I think a hypothesis. You choose over gray to see what rho does. It should, right? Because as the residuals get smaller.
Thank
you. Okay. Any other questions? Okay. I'm going to skip this, a whole bunch of things. Okay. All right. Let me just wrap up this part of it with a very simple example. So this is a data set. We'll come back and take a look at it. So the idea here is I have home mortgage. As I said, in the US, right, pretty much everybody who is a starting person gets a job, wants to buy a house, you can't afford a house. I mean, this more and more you can't afford houses in the US. Housing prices have gone up like crazy. My son and his wife made an offer of 3 houses. 3 houses. One of them was $100,000 more than what the asking price, and they didn't get it. That was how hot the housing market was then. Now, of course, interest rates gone up, so the housing prices have come down. But in any case, so what you do, you go to a finance company like a bank and apply for loan. Okay, and they will now take a. You got a. Well, this is I'm jumping ahead. That's another example where I'm going to talk about who gets a loan, who doesn't get a loan. This is people who have gotten the loan. And remember, I said that we have more than $1 trillion tied up in loans, right? And so what we do is that we have to, every quarter, we have to figure out what is our exposure. Who's going to default on the loan? Okay? Who's going to bankrupt? Who's going to pay early, right? So there are various ways you can lose money. You pay back your loan early. And that happens when interest rates were high, then interest rates goes down, people refinance things. Okay? So they'll say, okay, your interest rate was 6%. Now I can go and get interest rate 4%. But of course, I don't pay it up right away. You know, if I have the loan for 20 years, it doesn't make sense to do difference. But I have a loan only 2 years, that makes sense. So there's some actual calculations. So refinancing, or what we call payoff, default means that you haven't paid the loan first month, you haven't paid the minimum, second month, third month, and after some period, like 180 months, we say that this case is a gone case. You're not going to get it more. So we'll send it to collectors. Collectors are people who are trying to figure out how much money can I make out of this person. Okay, so they would say, well, they're going to sell the loan, 30 cents on the dollar, for example, but depending on how bad the case is, right? And then people go bankrupt, small businesses go bankrupt, and big banks go back, big companies go bankrupt, right? So this is what I call in trouble. In trouble means that it is in trouble for one of several things. Okay. Now, if you have taken a course on reliability or survival analysis, you know what competing risk is. What are competing risks, right? Competing risk means you can die of one of many causes, right? Heart attack, car accident, stroke. So when you're trying to model that different causes, you got to be very careful. There are a whole bunch of assumptions. And I'm going to skip all of that and just talk about just some kind of problem, right? So in this particular portfolio, we have more than 5 million observations. The response is the binary, was it is in trouble or not? We can predict the loan is in trouble or not. And I'm actually sweeping a lot of things under the hood. Whether somebody is going to pay off a loan is very different from whether somebody is going to bankrupt. So you really shouldn't put them together, right? But since this workshop, and I'm in the academia lab, I'm going to pretend like the professors who pretend that there is such a thing as IIT. So I'm going to not distinguish between somebody is going to pay out the loan and somebody is going to default. Because if you're paying off the loan, you get money. Pay out. And then defaulting, you don't have. So the latent variable that is driving these two causes of failure are very different. Nevertheless, my last variable is and we got a whole bunch of so-called predictors, right? And in this example, we have more than 100. I have just used 20 in this. So we have credit history. Credit history means what kind of credit you have. When was the first time you got a loan? Have you been paying off your loans? Do you have homeowners loans? This is, did you have credit cards and all, right? And then what kind of loan are you talking about, right? In a mortgage, you might take a 30-year loan, 15-year loan, It's called a balloon loan, which is after so many years you pay off over. Okay, how much it is, and loan to value ratio. Suppose your house is worth $500,000. Are you putting in $100,000 down? $200,000. Those things matter. Right? What is the interest rates? Okay, origination. And then interest rate changes over time. And how much money have you been paying over time? All of this. Right? So that's the kind of modeling that we have to do, right? So in our bank, remember we have hundreds of millions of customers, accounts I should say, because one account can be, multiple accounts can be the same person. And we are modeling all the time. We're modeling how much money we're going to make, how much money we're going to lose, who is a fraudster, right? And when I'm making a loan, am I discriminating against a male versus female, young person versus old person, a black person versus a white person? All of these things we have to use. Whole models. Okay, we live in a sea of models, thousands of models. Okay, and I live in a quantitative modeling community. I'm a research and development team, but most of my colleagues are developing models, looking at models, or this models or problems, are the assumptions correct, are the data correct, did they miss any data? Can we take something that happens now and extrapolate it to a completely different condition? Now think about this, right? COVID happened in 2020, right? Nobody think about the impact of COVID on banks. Completely changed the world. Interest rates drop like crazy, right? So models develop over a period of time that something was happening, cannot extrapolate. Same thing with the financial crisis in 2007, right? Landscape completely changed. So you have to put some faith in your data, historical data, right? But you also have to challenge them. So one of the things that people do is they do what's called holdout in time. So I have data over the last 10 years. I would now hold out my last 3 years data, and I would develop a model in the previous years. Okay? And then I would now apply my model to the latest 3 years and see if that model is useful. If it doesn't do, then I have to figure out why. And invariably something is changing. Correct? So you got to figure out what is changed. Is it unemployment? Interest rates? That kind of stuff. Right? So it is very much a decision making under uncertainty. Right? But these are important things. If you can make an application loan, I don't give you money, you're devastated. You're a young person. And you may go to another bank, but it's going to live with you forever. The first bad experience. Right? So regulators, we're regulated. So regulators constantly asking us, hey, is your model any good? How did you make this decision? Why does this variable come into play? Why not this variable? And invariably, 2 variables are correlated. Which ones do you choose? These are not easy problems. Okay? And the people we hire are young people, we train them, right? But these are not economists, these are data scientists. They're never going to learn all of that, right? Because by the time they learn that, they're on to a different problem. Right? Nobody stays in job all the time. So it's a difficult problem, right? But let me just tell you what one modeling framework looks like, right? So we are here, March 2023. Law originated in 2015, July. Okay. So, and I am trying to predict if this person would default, right? 3 years ago. So look at the time dimensions, 3 different time dimensions, right? Origination time, current time, and time at which the person would default in the future, right? Now, lots of things are changing, right? House price here, okay? That house price now might be worth a lot less. Interest rates here. Interest rates are changing over. So this is what we call time varying covariance. Covariance are varying over time, right? And that's not an easy thing to model. right? I'm going to and then I'm here, and then I'm going to predict, 1 quarter, 2 quarters, 3 quarters, 4 quarters. How do I do all of that stuff? How do I make all of these predictions make sense? I'm not going to get into all of this stuff, right? And a whole bunch of variables. So let me just show you a simple comparison of the several algorithms that I've talked about on this case. Okay? So for machine learning algorithms, we chose 22 almost predictors. Okay? But we also did a logistic regression model. Of the 22, the people who developed the model carefully chose 8 of them. Okay? And the 8 of them is FICO. FICO is a company in the US that puts up credit scores. So FICO is really a synonym for your credit score. How good is the credit score? Higher is better, lower is better. Okay, loan to value ratio. Okay, how much is the loan compared to the value of the house? And that is actually going to change over time. Indicator of financial crisis. Was it before 2007-8 or after 2007? Okay. Now you could argue that you couldn't use an indicator function to model before and after. You might actually produce 2 different models. One could argue that. It's a very recent one. Okay. But if I split it, I want enough predictors, enough variables, right? So this basically makes an assumption that the effect of financial crisis is additive. There's no interaction. I'm not another word, but I'm not. Let me skip that. Okay. Unemployment rate. Okay. And delinquency status. Has this person not paid off the loan in the last two years? Okay. That is because if I haven't paid off my loan from last 3 or 4 or 5 months, that's an indication that I'm struggling. That I'm not like. So that's a very useful. So these are the things that we use in this model and some interactions. Now you can see that this is the ROC is something called a receiver operating characteristic curve that is used for binary responses to assess the algorithm models. Okay? So basically the idea here is that you fix the thresholds or you fix the false positive rates and you compute the true positive rates, and then you get a curve like this. And ideally, in an ideal world, the curve should jump up to 1, stay flat. Okay? But it never happens like that. And if it's a random guess, the curve will be 45. So anything above that is better, but of course you want it much, much better. So if you look at the blue curve, that's what the logistic regression is. And the area under the curve is considered a summary of the overall ROC, and that's 0.8. If you look at the 3 machine learning algorithms, area under the curve is GBM is 0.87, 0.86, 0.86. Okay. Now this improvement is of 3 to 4%. That is nothing known to right. It's not evident. Right? So why am I showing this example? The reason I'm showing you this example is if you are dealing with a mature problem like credit loss, something we've been studying for the last 20 years. We know the variables. We know what the interaction should be. We know how to transform those variables. Should it be like that? Should it be log? Whatever. Right? There's a lot of knowledge. If you have that kind of knowledge, machine learning is not going to teach you that much. It's not going to be, because that lot of knowledge is encoded in what you've done. Okay? So that's why you see some minimal improvement. However, if you're dealing with a new problem, a problem in which you don't have a lot of subject matter, remember, to do the variable selection, take a problem, understand the subject matter, decide what are the important variables that are available to you, and which one have been collected, and which ones should I use, and understanding should they be linear, should they be nonlinear. All of that requires a lot of knowledge. right? It's sometimes it takes 3 months to 6 months, right? And once you work on a problem, of course you can do it again, repeat it, right? And you can improve. But when you're dealing with a new problem, particularly in kind of fraud detection, you don't have that kind of knowledge. So that's really where the machine learning offers the opportunity. It offers the potential saying, don't worry about feature selection. Throw all the variables in there. We will under the hood do the feature engineering for you. Okay. And we will try to identify what are the top variables. We will look at interaction. Now that is the topic of my next model. Okay. So that's really where, when you don't have enough knowledge, you're starting from scratch, you want to be able to jump that learning curve. Machine learning offers. Okay. But it is not without its problems. There is no free lunch, right? So we'll talk about problems in the next minute. Thank you.
We'll be taking a 15 minutes break, short break, tea break. Everyone is requested to return to the hall within 15 minutes.
चाय वगैरह आना सर चाय
हा असा कधी कामा बसला का दिवसभर काय काम करतो.
Okay. We started. So the second part, I have lots of slides. So I'm going to skip over most of the second part of this module. And we should aim for something like 5:30. Okay. All right, I'm going to now talking about some of the challenges associated with modeling using machine learning algorithms to model data. And I'm going to be focusing on tabular data, which means numerical data or numerical and categorical responses, right? Not text data, not images, or things like that. See that I have the date wrong. What date is it? March 1, 27? Okay, let me just repeat some of what I said earlier, right? So what is the attraction with machine learning? It offers very flexible models. Let's call it non-parametric modeling, but underneath the hood is very flexible. And so it's particularly useful with large data sets, right? With small data sets and equal to 10, we can't do much that is flexible. Okay? But n is equal to 100,000 or 500,000, you can actually start relaxing the usual assumptions of linearity and all of that stuff we do, and try to fit model, let the data drive the model. Okay? And one consequence of fitting flexible models is that you get better predictive performance. Prediction performance is usually very good, and we'll talk about that. The other one aspect, as I said, is because these algorithms do under the hood feature engineering. What do I mean by feature engineering? Tries to look at the variables and which ones are important. It doesn't really worry about selectively important variables. It does, under the hood, do variable transformations, and it looks at all possible interactions and picks the important ones. So it does automated approach to feature engineering, right? And this is particularly useful when you're dealing with new applications where you don't have a lot of subject matter knowledge, and so you don't have to spend months trying to develop a model. The challenge then, of course, is that it's a complex model predictor. Is implicitly defined and is high dimensional, complex. God knows what happens under the hood. So you can't interpret the results. If you're only dealing with this prediction and you don't have anybody to justify the results to, then it's fine. It's your problem, your model, you do what you want. But that is usually not the case, right? Usually, you're dealing with applications where you're regulated by regulators like in banks. You have customers to whom you have to explain the results of the model. All your safety critical, right? You're flying a plane or a rocket or doing surgery or driving a car, autonomous driving. So they're safety critical. Something goes wrong, you can't just say, oops, right? You got to figure out what went wrong and you want to improve the algorithm and make sure it doesn't happen again. Right, so particularly in an organization like ours, banks, you have the dual goal. You want to get good predictive performance, but you also want to make sure the results make sense. I can interpret the results, I can explain to you and to my customers, right? So there has to be somewhat of a compromise, right? So as I say here at the bottom, why do we need to understand and the model develop results? We have multiple stakeholders. The model must be consistent with subject matter knowledge. And if you fit some models that there's no meaning to the user, then you'll be challenged, right? Then the models must be fair. As I said earlier, you cannot discriminate against certain protected groups, right? Model must be generalized. It may be very, very flexible, but it doesn't generalize to reasonably close situations of interest, then it's not a useful. Right, so a whole bunch of areas where we had to worry about the attributes of the model. Okay, so I have put in here some selected attributes of a model. What models should do. There are many things here that I have not included. Right. So some of the things I've included are, as I said, the model must make sense. You have to be able to understand and explain the model. It might have good predictive performance, but not only overall, but also in bottom regions of the data. Must be generalizable, and the model must be fair. There should not be undue bias, right? So these are the three things that I am going to focus on, but I'm going to focus on mostly on this. Unfortunately, I don't have time. I'll just briefly touch on this. All right, I have already talked about this, so let me not spend a lot of time on this. Model makes sense. Performance must be good, model must be robust, must not overfit your training data, right? And then fairness is mentioned. Okay. So there are many ways of trying to understand the results of a model. And the thing that I'm going to be spending a good chunk of this afternoon, the rest of this afternoon, is what's called post hoc. Post hoc, I will talk about what post hoc means. And then I'll talk about global and local interpretations. And then I'll spend a few minutes on what people have come to call inherently interpretable algorithms. Okay, and I'm going to skip the last one. Okay, let's start taking a look at the model, the home mortgage model that we did, right? That I showed you. One of the things that we want to know is, okay, I fitted a model, but what are the important variables? What are the important features in the model, right? So here is a technique that is very commonly used. It's called permutation-based model of variable importance. It's model agnostic in the sense that it doesn't matter which particular machine learning algorithm you use, random forest, XGBoost, straightforward neural network, it can be applied to all of them. Okay? There are many others that I'm not going to be talking about here because it's the literature, machine learning literature is worse than the theoretical statistics literature. People write papers because it gets them promotion. You don't care it's useful. All kinds of junk. So I think we were talking with somebody just now, right? What you need is an AI machine learning algorithm, goes through all the papers and classifies them as junk and no junk. That would be very useful. Huh? Research, Okay, the permutation-based algorithm, the idea is simple, but let me just show you the results first, right? Remember the home mortgage algorithm data set I talked about? People are applying a mortgage and they're trying to predict the loss, right? We're going to not pay back, and this is a result of XGBoost or gradient boosting algorithm. And it computes the variable importance and ranks all the different variables. There are some other ones on the bottom that we're not talking about. The top one is your credit score, FICO. Okay, it's very reasonable. Credit score tells you how good the credit history has been, and that's a good indication of whether you're good. Second one is your loan LTV, loan to value ratio. How much is your loan relative to the value of the house? Okay, if your loan is 90%, 95%, you can walk away. You've only put in 5% of the money. If you have paid 50% of the loan, you're not likely to walk away. You've invested on it, right? This one is indicator of current. This means have I paid off my loan all the way up to now, or am I delinquent for the last 3 months? Okay, so if I'm up to date, then I'm not likely to default, right? If I'm not up to date, I'm likely to default, right? So these are all sort of make sense. But what goes under the hood? So the way you think about it is, I have a Y and I have a bunch of X's. I fit in a model, right? So in traditional statistics, what do? We do variable selection before we fit the model. Before we fit the model, we look at forward selection, backward selection, all subset selection, and other things called AIC and BIC, right? Here I have fitted a model, okay? And then I want to know what are the important things that went into the model, right? So what can I do? Suppose I want to know, is X1 an important variable, right? So what I can do is I can take Y, I suppress this variable, fit a model with all the X's, right? And compare it with the entire set of variables and see if the model is good. But if I have 50 other variables and I have a million observations, I have to refit the model each time. Expensive, computationally expensive. Okay, so Bryman came up with an alternative, right? And what is the alternative? Suppose I'm looking at Y and so and X1. Is X1 important for Y, right? So that means what? That is the relationship between Y and X1, there must be some important relationship, right? Now, what happens if I destroy that relationship? right? If I destroy that relationship, then there's y and x1 have no association, right? So what do? I keep every row and column the same except this one, and I randomly put in those, the column values. What have I done? I've destroyed the relationship between y and x1, because x1 is not knowledge. I'll put you right? So now what do? I refit the model with these values, where the relationship between y and x1 has been destroyed. I look at the predicted performance. If x1 is not important, the predicted performance should not have changed much. X1 is very important, predicted performance would have changed a lot. So I look at the before and after. Okay? I'm not fitting a model, refitting a model. I'm using the same model. I'll just change the values and see, hey, what happens, right? It's almost like I'm using it. I'm going to do to each one of them, right? And then I'm going to now rank out of them and I display them. And that's what you see. That gives you a ranking and some quantification, right? In this case, I think we have normalized all of them to be add up to 1. So that's what a permutation-based variable importance technique that was suggested by Leopold. Now, it is not without its problems. If you have two variables that are highly correlated, both are in the short. Okay? And sometimes the answer can be garbage. This is a big problem with machine learning. Because in traditional statistics, we go through very careful variable selection, we look at multi-collinearity and all of that stuff. And in principle, we use subject matter knowledge to say, hey, these two variables, within these two variables are highly correlated, I'm going to choose this. I'm not going to choose. Machine learning offers the following promise. Don't worry. Give me everything. I'll take care of it. That's what it is. But it cannot take care of correlation. Cannot, right? But think about the following model, set of variables. X1 and X2, right? X1 and X2. X1 and X2 are highly correlated. Okay? Now look at the interaction X1 times X2. X1 times X2 is going to look like what? X1 squared or X2 squared or X1 times X2. Cannot tell. So that is what we call non-identifiable. The model is intrinsically non-identifiable. You cannot tell it, right? So any three of those models probably equally predictive. And that's what machine learning will do for you. It cannot separate. You just pick one of them, right? So you have to use some other ways of filtering out or separating those models. The other thing here is, this tells you how much important this variable is, tells you how important this variable is. But if this is interaction between these two variables, it's going to put them here and here. So interactions will be double counted. That's another problem. There are other techniques that will separate the interactions, but they're much harder to combine. Okay, so I'm just skipping. This is by far the most commonly used variable importance. And I have listed a few others here. There is a technique called Shapley that I'll talk about later, but it's a beast. It's very, very difficult. Okay. It turns out it's actually based on a technique in game theory. If you win a game, how should the wins be distributed among the participants? And they're all cooperating for the win. And that paper was written by a man called Lloyd Shapley at UCLA, and he got a Nobel Prize for that. And Otto Owen at Stanford took that idea and applied it to machine learning algorithms. Okay, the second thing that you might be interested in is, I have a model. I have fitted a model. I want to know what is my input-output relationship, right? So again, in traditional statistics, what do? We do this beforehand, right? take y, and for each x we plot it, and then we say, does it look this way, does it look this way, does it linear, whatever. Right? We try to do manually. But here it is done post hoc, after the fact, after you fit in the model, right? It tells you what is the input of the relationship is. So again, I'm not going to get into the data, but the name of the technique is called partial dependence plot, developed by Jerry Friedman in his original paper on boosting. Basically, what it does is, you're interested in, let's say, a particular variable j, and what you're taking is you're taking all the possible values and just you are summarizing or projecting over the ones that you're not interested to get a one-dimensional projection, one-dimensional summary of the relationship between x and y. Okay, right? And that's what is being plotted here. What is plotted here is load to value ratio. What is plotted here on the y-axis is, remember, this is a binary problem, probability of default. And you don't want to plot x against p hat, because p hat is between 0 and 1. You want to transform it by taking the log odds. Log odds of p hat goes from minus infinity, so the relationship is more inverted. So what you see here is load to value ratio against log odds of the predicted default probability, and you can see that it is more or less constant, meaning when load to value ratio is very, very low, it doesn't seem to make difference, but when it's higher, it does have an impact, right? So this is a kind of under the hood feature engineering or feature transformation that machine learning does. Okay. Now, caveat, what it does is it takes a high dimensional function, averages over everything else but the variable of interest. So you can lose a lot in other areas. Okay. So let me just show you an example here. Okay. Oh, now I'm in trouble. Okay, let's take a look at this function. Okay, simple two-dimensional function, right? And that's your model. Not simple, but not too complicated. Right? It's flat over here, right? And it goes up, it comes down, and goes up. Right? So this is x1, this is x2, and that's y. Suppose I'm going to you want to know what the first dimensional, one-dimensional PDP is. To get that, I'm going to take this function, I'm going to average over these things. Right? What's going to happen? This thing is going to disappear. These guy and this guy will get cancelled out. Same thing here. So this is the problem with any one-dimensional summaries or two-dimensional summaries. You fit a complicated model, and then you're saying, oh, I can't understand this model. So give me some simple summaries. What do you get? You can get garbage. Because it just wipes out the complicated stuff. Human vision cannot see anything more than about 3, and with some visual aids, can get 4 or 5 slicing. Right? So we want to do everything. With 20 variables, 30 variables, 40 variables, give them to me. Machine learning algorithm says, give me, I'm up to the challenge. I give you a model. But now you say, what's inside? If there is some corner of a 5-dimensional space where there is some interaction, there is no way you will know. Right? So what have you learned? What have you did? So you'll have to sacrifice something, right? This is what's happening in the machine learning literature. This is the kind of world I live in. But prediction is not the end all. What we're saying is, let's not go with so many complex models. Let's sacrifice for interpretation and visualization and understanding. That's what you know. Okay. Now, I talked about one DPDPs, one-dimensional partial dependence plots. This one, right? Now, keep in mind, I don't want to really beat machine learning to death because it has a lot of promise. If you have very high order interactions are not important, and more often than not, they're not. Then these low-dimensional summaries, 1 and 2-dimensional summaries are very useful. Okay, and you can live with it, right? But how do you know? That's not how do you know that? Don't really know. So you got to look at diagnostics. You look deeper. And so what that means is, don't be blind. Don't blindly use these things. Bring some subject matter knowledge to it. Be smart about it. Okay, that's very right. You can take some computer science or somebody who doesn't understand data and let them do what they want. We are smart people. We are data scientists. But I'm serious. Okay, do not apply these things blindly. Bring your knowledge. Bring all the things you've learned about data, models, science, and challenge what you do, what you learn with these tools, right? So these tools are to help you, right? But this is not like taking a SAS output and saying p-value is 0.003, so I'm good. That's not what this is. This is science. Now you can do, I'm going to skip some of this. So you can also do two-dimensional partial difference plots. What this does is it looks at the joint behavior of loan-to-value ratio and credit score, FICO, right? And against the log odds ratio or probability of default. Now what it does is it plots here loan-to-value ratio, and at each one of these lines, FICO is fixed. So as FICO varies, these lines change. And what are we asking for? If there is no interaction, those lines will be parallel, right? Not linear, but parallel. Distance between those lines. If the line is not parallel, that is an indication that different values of FICO score, the relationship between loan-to-value ratio and predicted probability is different. So there is an interaction, right? So in this case, the interaction is mild, right? So if you look at this, slightly here these things shrink, but here it's worse. Here this is the horizon over which you're predicting, and then this says the 0 means the person has not 1 means the person is current, has paid off all their loans. 0 means no, they haven't, and you can see very different behavior. Okay, and this is what you would expect. And these are some more ways of quantitatively computing the two-dimensional PDPs, and these were in genetically conservative object. All right. Okay, now I'm going to talk about techniques for local explanation. So I'm just going through some of the possible questions that you might have after you have figured them out, right? So we talked about what are the important variables? What is the input-output relationship? One-dimensional or two-dimensional? You can even do these three-dimensional, four-dimensional, but because we run out of visualization, right? So we are kind of hurting there, right? So people don't figure them out. Two, of course, because anything more than two requires a lot of computation and also a good visualization. Now let's talk about local explanation, right? There are two kinds of questions that people might ask, right? So here is the model. I fitted the model all over, right? And I'm sitting here. Let me just do this, okay? So I fitted a model all over. So I'm here. What is the model locally around me? I'm here or I'm there, right? Now here it is a nice story, right? It's flat. Flat. There is no, everything is unimportant. So that's a nice little story, right? So I want to be able to say, if you are in this region, right? -20, -20, x1, x2 is here, it's going up. Okay? Right? And there is coming down, right? So, but the problem is complicated, right? Because at different places, the behavior is different. So what do we do? What is the most important theorem in statistics? Sorry? No, I'm thinking about something different. It's a trap. Most important result in statistics is Taylor's theorem. Very complicated problem. I don't know how to do. I approximate it by a linear. Correct? Almost everything in asymptotics is like that, guys. How does asymptotic theory work? You take something and you approximate it by linear, and lo and behold, I have a linear problem. I get an answer. Taylor is the most important. You should have gotten a Nobel Prize. So there's no Nobel Prize for math. Okay. So what do? You take a point, locally you fit a linear model. If you're a little bit clever, you can pick interactions too. Or it is linear model, right? And you approximate it, and then you explain. As x goes this way, you know, as x1 increases, y decreases linearly, and this is beta 1. So I can do local linear approximation, right? That's what people do. And there is a fancy name for it called line. It's actually, in fairness, it's a little bit more complicated than that, but in any case, the idea for us is just that. Okay? So the second problem is this, second question. Okay? And I'm going to illustrate this with an example, the example of Anil not getting the loan. So Anil is really, really upset. He said, my brother got the loan, I didn't get the loan. Why? He is hopping mad. And we have to explain to him why. Okay? What does that mean? That means this is the predicted probability of default for nil. It's made up of contributions from all of his credit attributes. I want to take that predicted probability, how to break it up. Contribution by this variable, this variable, this variable, this variable. Now compare it with this brother. Now I'll explain. Look, the brother's attribute in this was so much better, right? And you were pretty much the same in everything. And this is why you didn't get a loan with brother. Okay, so that is the attribution. Now I'll talk about that. Okay. Now, of course, if your model is linear, it's very simple, right? P1, your x1 is attribute, that is a contribution. X2, that's a contribution. So I will take Anil's x1 and his brother's x1 and look at and see what's the difference. Very simple, right? But the problem is the model is complicated, right? It's a complicated model. How do I do that? There are many techniques in the literature, right? And you know, a lot of it is based on not theory, which is convenient to use. Turns out a lot of them have their own theoretical things. But there is a technique called Baseline-Shapley that was developed by people called Sundara Rajan and Najmi, right? And I have taken that technique and applied to this problem, and I'll be happy to share that with anybody. So that's really what we're doing. I'm going to talk about. Okay. Now, I told you that the Shapley result looks very complicated, right? That's really the formula. It says, I want to take these contributions and I want to allocate it, and this is the general formula, and these are different ways I can get different things and so on. So I just threw it up there to show you that the general Shapley is not very popular because computationally it's a beast. There are lots of approximations. Okay? But there is a technique called baseline Shapley, which is easier to use, and I'm going to explain that to you. Okay? Right. Okay. So here is how it works. Let me see if I can. Okay, here it is. Right. So let me go here. Right, I'm going to explain it in the context of this application where two people get a loan, apply for a loan, one gets the loan, one doesn't get the loan, and how do you explain the difference to your customer, okay? And this, in banking, is called adverse action. So when you apply for a credit product and you don't get it, there is an adverse action against you. That's the term they use. And I'm going to show you how to apply this. Now let me just digress a little bit. And I live in the US. I am as an American as anybody else, I guess. Also not my kids. And every country has discrimination, has a bad history of discrimination. US is no exception, right? You call out discrimination on racial categories of women and LGBTQ, all that stuff. But the discrimination against Black people, which is horrendous in the 1920s, 30s, 40s, and it continues. So I want to talk about what happened in the area of banking. In banks in the 30s and 40s, there was literally an organization, government body that was set up. And that was colluding with real estate agencies to artificially suppress house prices in Black neighborhoods. So they would take a map, literally, where there is a lot of Black people, and they would draw a line. The red marker. This is predominantly Black. Interest rates are very high in that region. House prices are very low, artificially suppressed, and discouraging white folks from buying houses. That was called redlining. If you're interested, you just go and Google redlining, and you'll see this amazing history. Not anything that we're proud of, right? This went on for years. Even now, there was a Black family. There's something called refinance the house, right? You paid a lot of money into the house, and and you have a lot of equity or money in the house. You want to borrow money and then fix up your house. Okay, that's called refinance. So to refinance, you got to go to the bank and you got to ask for a loan, right? So then you'll have to get an appraisal company that appraises, comes and looks at the value of the house. Okay, somebody came to a Black couple and gave them an appraisal that is $500,000 less than one of the years. $500,000 less. They were surprised. So what did they do? Talk to their friends, white couple. They removed everything that looks Black in that house. All the pictures, all the cultural paintings, everything. So they did what the people call whitewash the house. Whitewash. 6 months later, they got another appraisal. $700,000 more. Happens everywhere, right? So governments, of course, have to step in and put in laws. But when government put in laws, there are all kinds of side benefits. You don't really enforce it, you over-enforce it, people find ways to get around it. So the government, this government has actually put in lots and lots of regulations over the years. And among them, applicants are legally entitled to get an explanation for a negative decision. Okay? And they're not really asked in detail, specific main reasons, principal reasons, right? So here are some other things. For example, if the application is incomplete, then it doesn't go anywhere. But after the review, it must say insufficient income. Your credit experience is limited. Now, this is a very funny thing in the US, So my nephew works for Expedia, and he was just relocated to the US. He's trying to buy a car. He has no credit history. He got his undergraduate degree in the US, but he got no credit history is zero. Right? But the income is pretty good. He still cannot want to get a car, can't get a loan for a car. So he texts me, Uncle, I need your help. Now I got to go sign that loan for him. So if you have no credit history, you cannot do it. That's, it's a catch-22, right? That's a part of the problem. Okay. Number of recent inquiries. That means that, yeah.
How can he create a credit?
Like he's trying to do borrow money, good guys. It's a catch-22. It's like saying, right? When you want to go for a job, right? And they say you're a fresh PhD, right? That's the and they say 2 years of job experience required. Then you get the job experience. Huh? I'm looking for a job. This is the catch-22. But there are ways to get it. I like my friend Shama, whom Bala knows. They moved from Malaysia to Ann Arbor, and I go sign the loan, right? Or sometimes you pay cash, you get a credit card, and you pay off. Somehow you get it. There's no way around. Okay, so I'm now going to formulate this credit decision problem as a statistical mathematical problem. Okay. Now I want to caution you, the actual decisions on who gets a credit and not credit are more complicated because they don't rely completely on mathematics. They would then look at the results of a model, and then there is somebody called an underwriter, the person looks at the details, and sometimes you're very close, I'll give it to you. Or but the model didn't use certain other information that we had, so I'm not going to give it to you. So they will override. Okay. This situation here, you have you have some attributes. So essentially, what you do, there are a number of ways this is done. Small financial institutions use credit score from FICO. There are several companies that do credit scoring. Okay, experiential, FICO, so they use their own that model. Most big companies develop their own model. So what do? They take a look at historical data. So, for example, I will look at last year. So many people applied for the loan. This is credit card. And I'm going, and these, so many people defaulted in the first 18 months. Okay, so I'm going to look at this historical data, 0 or 1, and the axis, and I'm going to develop a model for probability of default. It's usually no more than a logistic regression model, but you can use a machine learning to develop it. Right? So that's the. So we have historical data, yi is 0 or 1, xi are the attributes at the time that they apply for the loan, and we develop a model. P of x could be an x equals algorithm. In this particular case, I'm going to show you a neural network algorithm. And then you can say, as a first cut, before the underwriter looks at it, the algorithm can say there is a threshold power. Let's say this is 0.25. If the probability of default is less than 25%, you get the loan. If it's bigger than 25%, you don't get it. Okay? There's some threshold like that. Okay, that's usually decided by subject matter experts. That's how it is. Okay, so somebody comes and decides on how, so you have an algorithm, and let's suppose in 2 dimensions, simplicity wise, this red line is a decision boundary, accept, reject. Okay, and here is Anil sitting there. He got rejected. Okay, and his brother may be over here. And we went to figure out why the two are different. So the first and foremost is we want to take, I was using Anil's brother as obviously as an example, but usually the way this works is here is a region where people are getting the loan. Here is a region where people are not getting the loan. You need to pick a reference point. Okay, banks pick a reference point. Okay? And that is usually based on subject matter considerations. You can pick a point deep in the acceptance region, or you can pick a point somewhere on the bottom. Okay, let's not get into the details of that because that's not a statistical problem. That's a decision by a decision maker who decides. Okay, so let's suppose we pick this point, a point where the loan is accepted. This is the person who didn't get the loan. And we want to take a look at the differences, right? This is a point in the x1, x2 space, and there is an f, probability of default associated with this point that is coming out, right? Remember, coming at another probability coming at. And I want to take that difference and I want to attribute it to each one of the important variables. Correct? Everybody with me? Now it turns out, as I said, probabilities are between 0 and 1, and it's usually better to model log odds, difference in log odds, and so we will do that. Okay. Difference in, we'll look at the difference in log odds. Okay. Logit of x of t minus logit, and I want to take that difference and break it up into the contributions of the different variables. Okay. That's what I want, right? So I'm basically looking at log odds of this point, log odds of this point, taking the difference and attributing x1 and x2. Right? All right. Now, let me go back in sequence here because things have been out of alignment. So what you do here is the following. I'm going to try to explain this very complicated model with a simple example, right? So remember, we're looking on here, Jack, I want to take this difference and explain it, right? How can I go from this point to this point? I can go here, I can then go there, I can go from here, go there, right? There are two different ways to go there, right? Now, if I go this way, the difference in x1 is this difference, right? F of this point minus f of this point, or f of this point minus f of this point, controlling where this other point is, right? If this point is here, at this point, this is this difference. If this x2 is here, it's that difference, okay? So what should I do? Well, I've got contributions, two different contributions to x1. What would any reasonable statistician do? Take average. Right? So I'll take that. Right? Okay? So that's what contribution to E1 is just average. Similarly, for these contributions of this guy is this and this. So I'll take the average. If the model has no interactions, this and this will be the same. Don't need to take any average. I'm going to average this and this will be the same. Okay. So what is happening here? So a very simple explanation in 2 dimensions, right? Not very complicated. What is happening here is exactly a more complicated version of this in K dimensions. K dimensions, I look at all possible subsets and where the particular variable comes up and all these combinatorial coefficients and so on. But in 2 dimensions, the answer is very simple. Okay, now let's apply this to this problem. Okay, this is an example. It's an illustrative example, but it is simulated from data that is very, very, very realistic. But when I'm actually giving talks, I'm not allowed to show real data, whatever that is. I can show imaginary data, but I cannot show real. Okay, so 50,000 accounts were simulated. The responses were the person who got the credit card before the amount in 18 months. We took as an illustrative example 10 predictors, but it turns out that the distribution of these predictors were very similar to what is in the credit bureau data. And here are the responses. default indicator. Did the account holder, credit card account holder, default means didn't pay the account for the consecutive 6-month period or not? Okay, over the last 18 months. Can you hear me? Okay. So then the other variables are average balance, average monthly debt of all credit cards in the last 12 months. Okay, so that's an indication of how much money you owe. Credit age. When was the first time you got any credit product, whether it's an auto loan, mortgage loan, or whatever, right? How much of utilization means how much of the amount that you have can take out, you've actually taken out. Because if you're near max utilization, then you're a bad credit, right? Okay. But it turns out that if you're near low utilization, you're also not that good. So the relationship would be very, very much like a machine. Right? Total balance, there are a whole bunch of relationships, right? So now it turns out from subject matter knowledge, meaning the people who do the models, knows a few things. They know that the probability of default, right? The higher your credit age is, lower your probability of default because you have a lot of credit age. Okay, so the probability should be decreasing, right? In this area, as this variable gets higher, the probability should decrease. These are all neutral. Here, the probability should be increasing, right? So these are some of the subject matter knowledge that your model must satisfy. Now, if you fitted a machine learning algorithm from scratch, it wouldn't. It wouldn't do this. Okay. So this is an example where the subject matter knowledge is important. Interpretability is important. If you gave a model in which you showed them the input-output relationship and they're not monotone, the model will get rejected because it doesn't make sense. Okay, so you have to build in this monotonicity in the model, in the machine learning algorithm, and that's what we do. Okay, there are some you can do this in machine learning algorithms where you constrain certain variables to the model. Okay, let me. So what we did was we tried to fit in a monotone neural network. So this algorithm, it turns out, is an iterative algorithm. You put a penalty for the monotonicity, and then you train the algorithm. You see if the results are monotone where they should be. If not, you increase the penalty and keep on repeating it until you reach a certain level. Okay. And what we also did was we took these 50,000 accounts, 80% of them were held out for training, and 10% were held out for validation. This should be testing. Should not be training, that should be testing. Okay. So what is validation? Validation is when you use the data set to select your hyperparameters. Any algorithm has hyperparameters. So you got to do a grid search or some kind of search over the hyperparameter space and find the configuration, the combination of hyperparameters that give you the best. Okay. But validation is separate from training. You can't do it in the training data because it will overfit. So you keep an independent validation set. Okay. So in this particular case, what we ended up with, we had 3 layers. Okay. And the first layer, 35 neurons, 15 neurons, and 5 neurons. The learning rate is close to 0. And for comparison, we also compared the model with an unconstrained feed-forward neural network. And here are the results. Okay. So the unconstrained feed-forward neural network training AUC is 0.810. Test AUC, as it should be, is lower. Monotone neural network training AUC is a little bit lower. Test AUC turns out to be a little bit higher. Okay. The reason it's a little bit higher is because the data itself had these constraints. So you fitted a model that doesn't have these constraints, it overfits. Right? So on the test data, it's less overfitting, so it does better. Right? That's sort of hand wavy answer. Okay. All right, so let's take a look at what are the important variables. And this is the variable importance. So credit age turns out to be the most important variable. Okay, how much credit, how long have we had credit for? Number of credit inquiries is 12 months, last 12 months. Okay, but it turns out that variable, well, I'll come back to that. Average balance, right? Number of accounts 30 days past due, you can see all of this, right? But I want to go back and show you something. Here are the original variables, right? Next. Look at these three variables, highly correlated. Right? X6, what is X6? Number of accounts 30 days past due. Number of accounts 60 days past due. Total amount currently past due, right? These are all different measures of how much money is past due. So they're sort of measuring the same, right? But people who are modeling it don't want to make choices. They say, let me throw all of them, right? So those three guys are really talking to each other, right? Okay. So I will show you how we handle that later. So I'm going to skip all this, so you see the variable importance, it makes sense. So now let me show you the decision rule. Remember what the decision rule is. The decision rule in this case, I'm saying if the probability of default is bigger than 0.25, then you get your loan gets rejected. Okay? Credit card application. If it's less than 0.25, it gets accepted. Believe me, 0.25 is pretty high. Okay? Not too many people will have that much. Okay, most people will be below 25%. So you do want to weed out that. Okay? Now, also, let me remind you, this is a first step in the decision process. There will be a review by a human in the loop, and that person will make final decision, right? But most credit card decisions are instantaneous. I don't know if you guys apply to credit card. You almost like in a few minutes you get an approval for most of us. Okay, so this is really not sort of not a difficult problem. All right, so let's take a look at A stands for annual, right? That's A. This is no, A is the first one. So here is the person who didn't get the loan. Okay, that person's attributes, and that person's probability of default is 0.294, right? So that's over 0.25, so person is going to get rejected. Now I'm going to compare it, the same person, I'm going to compare with one person X1, another person X2, but let me compare them with the same reference point. Here is a person who got the loan, probability of default is 0.016, that's a good one. So we're going to compare this person with this, okay? So remember what I'm doing. I'm taking the differences in the log odds, and I'm breaking it up, decomposing it, and attributing to these values, right? These points. Okay. So what are the big guys? The guys, this one. Sorry, credit age, right? Well, the person who's accepted, this has been standardized, minus 0.7. But the person who didn't get the loan is 0.88. So 60% of the difference can be attributed to that. Next one. Number of credit inquiries in 12 months. Okay. This person got accepted at 0 inquiries. This person at 3. So 31% can be attributed with this. So these are the two big differences. This and this. And this is what you would provide the person who's dealing with the loan. That is this evidence you would give. These are the two variables that contributed to this problem. Okay. Now let's take a look at this person, second person, whose probability of default is really, really low. Okay, right? And and let's take a look at the difference between this person and this person, right? Here. Okay. Now this one, credit age is again a big one, but it only contributes 26%. This one, Number of accounts that are 30 days past due, 31%. Okay. Number of accounts 60 days past due, 16%, right? Number of accounts currently past due, 28%. All right, now let's think about this for a second. This guy is fine, right? But these three guys are essentially measuring the same thing, right? So when you're dealing with these kinds of things, you got to be careful, right? Which one do you want to do, right? So one way to do this is combine all three into a single pair, and then do the attribution. So if we did that, okay, you can see that I have now taken all those 10 or 12 variables, combine them into 1, 2, 3, 4, 5. Balance, credit age, utilization, number of accounts, and number of inquiries. See, all three of those guys got collapsed into this. So there are only two guys, right? I'm sorry, I should be talking about this, right? It's this guy and this guy, positive. Positive and credit age. These are the big hitters. Okay? That's what you provide. Question. This one? This one? This one? This one?
Yes, so X6, 7, 8, they are reflecting but X9 and X10 is also because the correlation is high with line.
Right. So this is why I'm saying that when they're highly correlated, the results are unreliable. It's picking one of them. The model is just picking one of them. Okay? But if you're a subject matter expert, look at it and say that doesn't make sense. So what you do is you combine them. Right? You see what I did here? So looking at all of the independent variables, I've combined X2, 6, 7, 8, 9, and 10, 1 and 4, 4, 8. They're all measuring under the hood the same. So I'm just going to work with this variables. No, that table is for this. It's for this. Okay? And I'm going to show you a different table for this. No. Of course not. That will never be the case. Why do you say that? That shouldn't. Suppose X8 and X9 are spurious correlation. You know what spurious correlation is? Yeah. So why should the both of them have the same effect? You're not right. It may not. That's the vagaries of dealing with data. You can never tell.
I just have one other question. What's the reliability of those attributions?
Yeah.
Then my question is, what's the reliability of the attributions? Like in case of regressions, we know the significance of the coefficients, right? So what is the significance of attributions? Because we are comparing.
Go ahead.
Because we are comparing. So.
No, I mean, this is a good question. The thing about all these things is that you have to take them with a grain of salt. Okay? You don't say, I see a number 36, is 32, is 40. Okay? But I'll tell you what I mean by this, right? But let me answer her questions. Okay? So this is what we have, right? Okay? X8 and X9 together. Huh? I'm sorry, 9 and 10. 9 and 10, right? Okay. Here is 9 and 10. Number of credited words together. Right? What I said is, I looked at that, but remember, I'm giving a lecture. I'm carrying along two things. The original and what I would do in practice. Original individual variables, but my correlation matrix showed the highly correlated. So I'm also going to say, if I'm writing the report, I have multiple stakeholders. I will write the original report, but then I will also say, look, these variables are highly correlated. I don't want to look at X and X and separately. I want to do them together. Because I am not an expert in saying which one is important, but in this case, both of them are measuring the same thing. Right? You don't have to attribute. Why do you have to attribute? All it is number of credit inquiries. 12 months or 24 months. Doesn't matter. It's number of credit inquiries, right? We are measuring 12 months, we are measuring 24 months. But at the end of the day, what affects is months. And he could have measured it at 18 months. Same thing, right? At the end of the day, we are trying to give an explanation. And customer doesn't say 12 or 24. Customer says the number of credit inquiries is too high. That's all. Right? That's why it makes sense from a subject matter point. You see what I'm saying? Where is X1 and X4 combined? This one? Yeah. Balance. X1 and X4. Combined. Total balance. X1 is average balance. Average balance. Again used. Huh? It is used in a combined form as well as separately. Yeah, I think that is a mistake. That's a mistake. It should not be a mistake. Okay, you had a question. I forgot a question. Somebody had a question. Oh, I know what it is. You're asking how reliable is number 59.4, right? The thing here is, you can do the computations, okay? It's not easy, right? But you don't need to. Why? In this example, look at these two guys. They are the ones who stand out. Nobody else is close. So why do you care this 39.4 or 36.7? It doesn't matter. The two big ones, right? So this is what we mean by it's not a statistical issue, it's a subject matter issue. Now, if I had three guys who are close to each other, then I would report all three. And I would say they're more or less the same. You know what I mean? So that's what we will do in practice, okay? You can do the computations, you can do this, but they're not easy because the algorithm is very complicated. And to get any kind of prediction interval is hard. Any other questions? Okay. I think we had a long day. So actually, there is something called an inherently interpretable model. Let me just summarize this, right? What's going on here is the following. The emerging view in this area, as I alluded to, is the following, right? People in the beginning said, okay, you give me a data set, I break it up into training, test data, then I go to town with the most complicated algorithm I can. That's what Kaggle competitions in the US are all about, right? You come up with 0.000001% improvement in predictive performance. Jump up and down and they might get $100,000 price. Okay? But that's not the action. That is not where the action is. The action, if you're a real user, you don't really care about tiny improvements in predictive. You don't. The problem with that is that if you use a slightly different test data, you'll get a different answer. Everything is depends on the data set you use. So I'm not going to jump up and down because I got 0.0001% improvement, right? So people, the current view is, let's scale back. We don't really need, interactions in fifth dimension, sixth and seventh dimensions may happen very rarely, but if we happen, we cannot even find them, let alone interpret them. So I'm just going to, sacrifice that, right? So what people do, or what we do, is we fit a complicated model, like XGBoost, and then we fit a lower order model, which only has main effects and second order interactions, and look to see if the predictive performance is very big. If it is not that big, then we say, let me just go with the model that has main effects and second order interactions, okay? And these models are not parametric models, right? They are what's called functional models, meaning the main effect is a function. Second order interaction is a function. So it's non-parametric, but it's not completely parametric, okay? So it's like this, right? You can take a function of f(x), decompose it into overall main constant, main effects only, some function, second order interactions, and third order interactions and so on. Okay, we can do that, right? And what we want to do is focus just on these. Okay, because I can visualize that, I can see that, I can interpret, right? And this idea is not new in statistics. Statisticians, even when I was a student, we learned about this. Okay? But what's happened here is you can use the machine learning architecture to fit these models very fast, very quick, scalable. Okay? And so that is what we call FANOVA. FANOVA stands for functional analysis of variables. Okay? So you are doing an analysis of variance, but the main effects and the second order interactions of functions, like arbitrary functions. Okay? And you try to estimate them. You try to estimate them non-parametrically. And there are several techniques that have been developed. The first one was called explainable boosting machine. This is from the Microsoft group. And the next two are from our group. Okay. Gamma trees and gamma neural nets. And these things are really non-parametric ways of estimating this and this. And I'm not going to get into the details of that because I don't have the time. I should say I don't have the time. That's what makes me sound like I'm that important. I'm not. Besides, Ram is giving me lots of money. Right? Okay, I'm going to show this to you on one data set. It's called a bike sharing data set. Now, many of the machine learning or there are many data sets in a repository called University of California Online data set. If you want to really get some data sets and try out your ideas, you can go there, go UCI data set. And this data set is about renting bikes. Okay. So hourly rentals of bikes over a 2-year period, daily, okay, by hour, right? And what they are interested in is how does the bike rentals vary by hour, by day, by temperature, humidity, wind speed, and all this. Right? That was the model. And so here is the output of EBM by hour. This is midnight all the way, right? And you can see that there are two peaks here, right? There are two peaks, okay? Any guess as to what those two peaks mean? Why are there two peaks? This is the morning and the afternoon. What happens? People go to work. They rent bikes, go to work. And then they put it, you return it, and then they rent bikes to go back. Right? Here you guys don't, right? You just have motorbikes. If you have bikes, you'll get killed. So these are the two spikes. And you can see this is a model with piecewise constant trees. That's why it's piecewise constant jumpy. And this is a neural network. You can see it is a little bit different shape. That's one of the things. And this is by temperature, right? So this temperature here is, this is temperature and hour of the day, or how you call it. So too many things going on. But one thing that is interesting, and I'm not going to be able to show this to you, there is a very interesting interaction, as it should be, with hour and day of the week. Weekends, people don't go to work. So the peaks happen at a different time. So if you fitted a GAM model, generalized additive model, you will miss an important interaction, right? So in this case, we analyze this data set. I mean, a lot of people analyze this data set. There are all kinds of interesting things going on, but the most important thing was the hour by day of the week interaction. But I'm just trying to show you how this works, right? I'm going to skip all this. These were slides we used to teach about small, and that's I actually made a shorter version that I forgot here, and then sent to you. All right. But so what have we talked about today? We talked about in the module 1, commonly used machine learning algorithms. For most of our purposes, analyzing tabular data, those 3 algorithms are fine. Support vector machines are not in vogue anymore. People don't use support vector machines. Random forest, XGBoost, or gradient boosting, neural networks. And for our applications, feed-forward neural networks is good enough. XGBoost and feed-forward neural networks are the things that people use most. Okay. Tuning them is not that hard. I didn't have time to go over it, but I have slides that's part of it. And I talked somewhat about interpretation, and I didn't really have time to get into correlation. One of the hardest problems in this business is when you have high degrees of correlation. What do you do? Machine learning will not give you the answer. You have to use your own subject matter knowledge to try to figure out what things. Or you live with correlation. If you can live with correlation, it's fine. But you're going to interpret the model, a very highly correlated predictor subproblem. Okay. Now, there are many other more complicated neural networks that are now being used. Convolutional neural networks, recurrent neural networks, and transformers. Those are for more complicated problems in image analysis and also in text analysis model, right? And you all know about the ChatGPT, just catching the world by the storm, right? So that's it. So I have finished the formal part. If there are questions, let's please ask them. Yes.
Now that we have talked about the consumer risk specific, and we are seeing like in the recent days, all the banks are failing. Like majority of the banks are failing in the US and even in the European Union.
Can you use the microphone? Can somebody give the microphone?
Yeah, so now we have seen about the consumer risk, but if we look at the current situation in the US and European Union, a lot of smaller banks are failing. So is it because of the model deployment, whether the models are failing, or whether it's their internal policies which are harming their businesses and the banks are going into bankruptcy?
Well, I mean, I'm hesitant to answer that question because I'm by no means an expert. But I would say a big chunk of that is consumer-driven panic. These banks are not, they're not really weak. Okay, so look at what happened to Silicon Valley Bank. Right? Silicon Valley Bank had, well, at some level they had a lot of their monies in treasury securities and zero coupon bonds. When interest rates went up, zero coupon bonds don't pay any interest. You have to wait until maturity. So when interest rates went up, these things really value went down a lot. Correct? Because, you know, right now I can get something with interest. Why should I wait 30 years and get, you know, my yield, what I get back is low without the interest, right? Okay.
So to some extent, the facts are
potential implications, right? But it was also in that particular case, I don't know what happened to Signature Bank and Republican Bank and others, right? They're all small to medium banks, not small, they're medium bank, and they may be under pressures that other banks are not, okay? But Silicon Valley Bank was a special case because they were very much targeted at high-tech startups. And they were putting their money in, you know, in long-term securities, and they were not getting enough money back, right? So then people started saying, you know, so a few things happened as far as I know and I read. The IPOs, tech companies stopped giving IPOs, right? And then some of them saying, hey, your money is not worth that much, so take money out. So there was a run on the bank, right? So then it created a panic because the bank was not solidly weak. It's just a fear, right? Social media has a way of, you know, creating panic, right? Have you guys, has anybody here seen the movie called Mary Poppins? Mary Poppins. Oh my God. Huh? Mary Poppins is the movie. Do you know Julie Andrews? What is the world coming to? Julian, Sound of Music. How many people have seen Sound of Music? You have. It's a classics, people. How could you not watch these movies? Mary Poppins, okay, it's too long, too much of a story to set up. But the short version is that she works for a guy who works in a bank. And the son was playing with a coin, and all of a sudden he said, okay, let me go and take the money out. He went to the bank and asked for money. And there were a lot of people standing around listening, and they thought that people were drawing money. So it started a panic. Perfectly fine bank collapsed. It's a story. I'm not saying that this is this. Now I should also separate two things. The large banks, like Wells Fargo, you know, what they call systemic too large to fail banks, they're very highly regulated. Okay, so we are solid. We don't have the same problems we were running into in 2007 and 2008 because we have something called stress testing. End of every year, we're supposed to look at our models, push the models to extremes, high unemployment, high interest rate, high these, low this, and then see what will happen to our reserves. And we're forced by, like your Reserve Bank of India, the Federal Reserve forces them to keep a certain amount of money in liquid cash. That's what happened in 2007. Okay? So because of that, our banks are highly regulated. Okay, we cannot go to the bathroom without asking permission. Seriously, these regulators are very strict. You know? But these medium level banks are not well regulated. So that's one of the things that came out. Okay, there should be. I mean, to your question, right? The answer is yes and no. They should have been better regulated. They didn't understand the risks, right? Like SBI, Silicon Valley Bank, they didn't know their risk properly, right? Because why would they put all their money in zero coupon bonds? For example, right? Not all their money, but a lot of it, right? So this is the lesson that we are learning, right? But I don't know how it is in the Reserve Bank here, all of us are waiting for the Federal Reserve to stop increasing rates. Because my money, all my retirement money is going down in value. In Fidelity and all these places I'm investing, the stock market is going down. So, people like me who is going to retire pretty soon would like the market to come up, right? So, but the Federal Reserve is very concerned about inflation. So, they just increase it by quarter basis points or something. Right? How is it? What is happening in Reserve Bank of India? Are they doing the same thing here? Same? Yeah. So who knows, right? I have to work on that.
Last consecutive months, inflation has been on the highest.
Right? What is it, like 6%?
6.5.
Yeah, that's what it is. But the problem is, economics, as you guys know, is voodoo. It's a voodoo science. Nobody really knows how it works. Also,
Used to make fun of it. Common sense making more complicated.
I mean, it's a rip-off, right? After the stock market crashed, I can tell you why it crashed. But before it crashed, I cannot tell you why it crashed. Right? I mean, my undergraduate degree is in economics, right? It's a voodoo science.
Where is the one agree?
Small cooperative banks in Maharashtra, how that will be different from. So can you
I think small cooperative are mostly because of self-dealing. I mean, like they have vested interest people over there. You give loan to them and take money away. I have a different question. It's not a question. I have been thinking about it. See, do you think that we should change the teaching of
It's a hard question, right? Because all of us are strong. It's a good question, that's a hard question. But let me tell you one thing, right? Courses like multivariate analysis, they've always been. Correct, okay? Whether it's clustering, right? Clustering or dimensional reduction, all of that, right? Now there are new techniques available, right? Because principal component analysis, we always used it, but it's a linear dimension. Now there are techniques called autoencoders. So we should teach this. Many of the statistical techniques we're teaching regression. Of course, regression techniques are still there, right? But we don't have to spend a whole lot of time on p-values and ANOVA tables and f-tests. These require normality. You never have normality, right? So pay less attention on this very test of hypothesis, okay? But pay more attention on things like prediction intervals, right? And teach more non-parametrics regression. And in that context, I would take a course on, regression, break it into two. Basic statistics, the traditional ones, and then you teach the non-parametric method, whether it's splines, random forest or whatever, right? There's a lot of stuff. Non-parametric function estimation has been around for, but they haven't been used. But now they're used. So our students definitely should. More than that, they need to learn computing. They need to be very, very, very comfortable in dealing with large data sets, moving data sets, directing data sets, cleaning data sets, SQL, all of this stuff. The idea that I sit in my office, somebody will come and give me clean data, never existed. Never existed. Okay? If you're going to dream that's going to happen, then, and you can dream, right? You need, people talk about data science. 70%, 80% data science is data cleaning, data engineering. That's really where a lot of the work is. It's custodial work. It's like cleaning the floor or the bathroom. It's not fancy. And there is very little in science and data science. What is the science and data science? A lot of it is statistics. A lot of it is computer science. Right? Algorithms, understanding computing environment, being able to code fast and being able to be brave. That's not being taken over by the mathematics background in us. Be an engineer. Jump in with both toes. Don't be afraid. That's what some engineers are good at. They are fearless. Fearless. They just jump in and do things. They're not trying to prove theorems. There is no theorem to be proved here. Right? So I think you can take your coursework and adapt it. I don't really think there is any need for measure theory. Correct? There is no need for measure. Absolutely no need. If anybody comes to me and you say, I need measure theory, I say, you're living in a different world, man. This is not the world we live in. Okay? We need to know solid theory, inference. Okay? But we don't really need a course on Eric Lemon's book on hypothesis testing. Composite hypothesis, univariate, invariant tests, and all of that. So there's no need. Nobody uses it. I have never used it. I learned it from Berkeley, from the master himself, Eric Lemon. Nobody uses it. Right? And the asymptotic theory you want is basically Taylor series, people. That's all we need. You don't really need very complicated asymptotic theory. Okay? Unless you're in academia, you want to prove theorems like Naveen does. Right? You know, that's fine. There is a role for those people, right? And I'm told that they're not getting paid well. No, but I'm seriously though, it is not a big move from here to there. It is not. Okay, but there are some key things. We need to sacrifice mathematics for computing. Okay, I'm not saying that you shouldn't understand what is solid background and theory, things like likelihood ratios, things like inference, prediction interval. All of that is important, right? But you don't really need all the fancy stuff that came out of Berkeley in the 1960s and 70s. Really don't. Okay, that's that. Oh, no questions. Okay.
Sir, you mentioned about live match chat, both as local explainers. So, what do you think? Can we compare both as someone better than the other? If yes, why? And if no, why?
Yes. How much are you going to pay? This is a common question that people have, and a common confusion. Remember, I said questions 1 and 2. There, rhyme is for one, chat is for the other. We don't answer the same question. Line is a local approximation. Okay. So locally, I have a line, I can spit some plane on it, and I can explain, right? That's what line is a fancy. But at the end of the day, that's what they know they sample points away and all that. But can simplify. Okay, that's what line is. Sharp, very good. Sharp has many versions. There's global sharp to identify which variables are involved. Almost impossible. Okay, whereas local sharp, sometimes called sharp, some called. Okay, and that is also hard to compute, right? They computed by approximation, T sharp, kernel sharp, and then these guys from Rajan came up with baselines, which is what I do. It's very easy. Okay. Now, what is that though? That is saying I have a prediction. I want to attribute that prediction to the components. Okay. Now, if you have a linear model, both answers are the same. Beta 1 x1 plus beta 2 x2 very simple. Beta 1 x1, beta 2 x2. Answers can, both questions can be answered the same way. But if you have a nonlinear model, attribution cannot be done by shadow. Cannot. There is a lot of people who are confused, even in my own team. Okay? Reason why? Remember, we're talking about comparing the loan, right? This person got a loan, this person didn't get a loan. Okay? And I want to take the difference and I want to attribute the difference. I put a local linear model here. I put a local linear model here. There were two different linear models. I cannot compare the two. Cannot. So you cannot design comparing the attribution. The attribution problem cannot be done by line unless the 2 points are very close to each other. That is something for some reason people can't understand. It drives me crazy. Even in my own team. Sorry, I'm very emotional, guys. I get a few beers. Any other questions? Good questions, good exchange team. All right, thank you very much.
So, I would like to thank Professor Nair for spending so much time with us, interacting freely with us. From the questions that came up, I'm pretty sure that people have got interested in many of the new things that we discussed here today. And I'm sure many of you will continue working on it. And perhaps when you come up with something interesting, you could perhaps get in touch with him again. And I hope that after his explanation, you are no longer worried. You should try to get your hands dirty by playing with the real data. That would be the whole point of it if you start doing it today itself. So let us thank him once again for his valuable time. And yeah, so we are now towards the end of our workshop. So I would also like to take this opportunity to thank all the members in the organizing team who did their best to make this event successful, including the faculty members, the non-teaching staff of the 4 departments, as well as the team for live broadcasting. And I also thank all of you for being present here and actively participating in the workshop. Your certificates are available at the registration desk. Make sure you collect them. And that's all. Thank you.